In this marathon episode, we will cover all the basic physical verification methods in detail. We will start with the fact checks, why PD is important. Then we'll take a brief tour of the PDK or decay needed in physical design. Then we will cover the design rule check, that is DRC, and layout versus schematic, that is LVS, one after another in sequence. Then we will understand interconnects and the delays caused by the interconnects themselves. Next, we will talk about the on-chip inductance in detail. Next, we will get to know about decap and its importance as physical verification remedy. Going further, we will understand in detail the parasitic extraction file SPEF, that is SPEF, which is used in IR drop and electromigration analysis. Next, we will understand IR drop analysis as a major physical verification step. Followed by, we will cover the electromigration and its dependency over various factors. Next, we will cover the ground bounce as a trailing part of the IR drop analysis. Next, we will talk about crosstalk in detail. Finally, we'll run the last few miles of this marathon with topics as antenna violation and ESD protection. This is a must-have marathon for all the physical design and verification aspirants in VLSI. So, stay tuned, stay focused.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. Visualize the physical design. What is physical design? Why physical design is must? PD in analog versus ASIC or SoC design, that is digital designs. Physical design contribution towards FEOL. Physical design contribution towards EOL. So, the FEOL and BEOL are the two subdivisions of chip fabrication, physically on silicon wafer. So, that's the menu for today. Let's begin. Visualize the physical design. Now, in this slide, we will use some infographics just to correlate our basic classroom circuitry versus the silicon chip making. Here in our classroom projects, we have to do design an amplifier. Then we design its circuit, and then the flow goes in this arrow direction. We construct the circuit on breadboard, and once the circuit in breadboard is finalized, we prepare the PCB, and once the PCB comes in, we do the testing and all to finalize the design, and then the entire PCB is ready for production. So this is kind of in-house or classroom development of any circuit that we are very much familiar with. Now, in chip making, the concept I will give 1:1 steps to these steps. So here goes our chip making step. First, we have a block diagram, and we do a top-down approach or bottom-up approach, whatever approach we use to make sub-blocks or unit blocks or whatever needed. Next, we implement the design through our EDA VLSI softwares. Finally, covering the front end and the back end, the design goes up to the layout, where we study different effects of the layout to the physical design and physical verification steps. Finally, when signed off, the design goes to fabricate on silicon wafer, and once the wafer is fabricated, the chip is packaged and ready for the market. So here, with this simple example, I tried to make you understand the physical design process with a comparison to simple PCB making process, or you can call it a classroom process, because generally in class you use these methods or do these things. If you are doing project, then only you make the PCB and complete your project, or like that. So the visualization of the physical design with respect to whatever classroom knowledge you have, I have just compared here. Now we'll move into the next slide. What is physical design? PD is the process steps of transferring digital or analog circuits into silicon. PD is the back-end part of the standard design step. Now, by these 2 points, it is very much clear that whatever design we do to the computer softwares, also called the EDA VLSI softwares, that finally goes as a mask to the silicon chip preparation. And physical design is the back-end part of the whole process. PD helps circuit components and their wirings to be realized into physically fabricable mask or silicon chip. Now here you can correlate the concept that I have just shown you in the previous slide where the visualizations are made. You can understand the circuit wiring and the circuit components. Everything is realized on the silicon chip, and PD is the process through which we actualize all these things. The word physical in physical design came from the physical aspects such as spatial embedding of active and passive devices on silicon wafer, usage of wiring interconnects, that is metal or via, and separating dielectric. Now this separating dielectric is a bit different from the gate oxide. Gate oxide is at the device level, at the MOSFET level, and this separating dielectric is at the interconnect level, that is at wiring level, because we do not want any two metal wires to get shorted. In breadboard level, the wires are already insulated that you use. However, when chip fabrication, we cannot insulate the metal wires in that fashion. So we have to use dielectric coating to prevent shorting between any two different metal layers or any two metal strips that are connecting 4 different points in their own way. Induced parasitic resistance, capacitance, and coupling capacity. So these are kind of byproduct once we realize the actual circuits into the silicon. These parasitic resistance R, C and CC are not the part of the design resistance, capacitance. These are extra. However, the physical design process can predict these R, C and CC so that you can in advance calculate the effects. Evident effects of physical phenomena such as delay, noise, power, leakage, reliability and manufacturability when the circuit was made using either the RTL or the schematic. All these factors, that is delay, noise, power, leakage, reliability, manufacturability, are not there. So in the front end part, whether it is analog design or it's a digital design, the circuit is a pure circuit and it do not have all these effects. Only in the physical design and physical verification process, we encounter all these physical phenomena. Prevent or minimize fabrication issues such as design rule error, antenna issue and mask issue due to the diffraction of EUV light for lithography. So these are design related challenges. The foundry gives the DRC, that is design rule checks. All those rules are there in the DRM, that is design rule manual, and antenna rules are also there. And the third one, the mask, it is a fabrication kind of engineering issue. So also we take care during the back end of these things. So we are done with this particular slide. So let's move on. Why physical design is must? Layouting is very time consuming in both analog and digital design. A chip switching speed is critical in today's scenario and signed off by post layout static timing analysis. This is a very important point because static timing analysis indirectly verifies the speed of operation and its correctness with that particular speed of operation. And the post layout static timing analysis comes under the backend, that is comes under the physical design. On-chip electrical characteristics of logic gates depend on the aspect ratio of PMOS and NMOS. So this is kind of IV characteristics we are talking about here, and you know that the IV characteristics heavily depend on the W and L variation of MOSFETs, whether it is a P MOSFET or whether it is a N MOSFET. Current or voltage levels further affected by R, C and CC. We have just talked about these parasitic resistances and capacitances. They affect the current and voltage. Predictive detection and prevention of reliability issues due to the IR drop or electromigration is necessary. So the IR and EM, these are the very two important part of analysis inside the entire backend. And through this analysis, we can detect many issues in advance and we can take corrective measures. Chip lifetime prediction by aging analysis helps manufacturers to put the chip guarantee or warranty period. This is another kind of analysis which is called aging analysis. This actually gives timeline up to which the chip will maintain its figure of merits. layout equivalence check determine the intended functionality versus realized functionality on layout. This step is also known as LEC. We are done with this particular slide, so let's move on. Physical design in analog versus ASIC or SOC, that is digital design. In left side, we will be listing our analog design process, and on the right hand side, we will have our digital design process. These are two symbolical infographics just to imprint the analog and digital into your mind. Now, in the analog part, the physical design starts after the schematic design, which is done in the front end, and will proceed in the arrow direction as shown in this slide. As soon as we start the PD, the layout is made in analog design. There are several variation and combination of custom and semi-custom methods to design the layout. Then, once the layout is ready, the DRC and LVS check, those are performed on the layout. And we may go back again in the layouting step to rectify if any error has been detected. Next, once the DRC and LVS is clean, we go ahead and do the parasitic RC extraction. Then we go towards all the physical verification, including EM, IR, antenna, all those checks. Finally, once that is done, all these steps are done, and the final step, we do the electrical characterization, timing characterization, all those stuffs, and we are ready for the delivery. Here, if it is a analog block, then it will be delivered as a IP, and if it is a full analog chip, then the GDS2 file will go to the foundry. Now, let us look into the steps of physical design in the digital part. In the front-end design, we have synthesized our RTL, and the synthesized netlist has passed through the pre-layout static timing analysis also. At this stage, we enter the backend, that is in the PD part. So the first, we do the floor planning and PNR. Floor planning is like keeping different blocks at different places and do the area budgeting and all. And then we do the placements of these blocks and route metal wires and vias, etc. Complete the connectivity. Next, we have the DRC and LVS check here on the layout, which has come out as a product of the floor planning and the PNR stage. And then we do the RC extraction, that is the parasitic R, C and CC extraction. Then we proceed towards the STA and the physical verification. So this STA is the post layout STA. Here all the post layout effects are considered, and physical verification includes EM, IR, antenna, all these effects. And in the next step, we do the formal verification and sign off. So these are the two side-by-side comparison of PD in analog versus the digital design. So now you are ready for the answer, which I have spoken into the intro. So you can compare the analog and the digital PD steps. Only the first block is the boundary of your front end and back end. So we are done with this particular slide. So let's move on. Physical design contribution, FEOL, that is front end of line. Here and in the next slide, we will talk about the impact of physical design on the silicon fabrication process, that is VLSI technology part. So here we will talk about FEOL, and in the next slide we will talk about the BOL. Don't worry, I will explain these terms and their details, hence this slide is kept. The whole geometric representation which come out of PD is called integrated circuit layout. The wiring is termed as routing. The physical design makes room for the FEOL and BEOL during fabrication. So you can think that FEOL consists of couple of steps of the fabrication process, and the rest of the fabrication steps are considered as the BEOL. So this way you can understand. The front end of line, abbreviated as FEOL, is the first portion of the IC fabrication where transistor, capacitor, resistor, etc., that means the active and the passive devices, are fabricated as per the layout made in the physical design step. So now you can have the significance of the physical design into the actual silicon fabrication, and we are quantifying here what is done at which step, what is done at FEOL and what is done at BEOL. FEOL consists of chemical mechanical polishing. Sometimes we abbreviate it as CMP, also known as planarization and cleaning of the wafer. Calotense isolation, that is STI, or low-cos, which is for the technologies which is greater than 0.25 micrometer, comes under FUL. FUL also include well formation, gate module formation, source and drain module formation. So here in this slide we have covered all the points, and having all the information in one slide, you can understand that what is the significance of the layout that is prepared in the PD and what part of the layout are covered in the FUL, that is front end of line. We are done with FUL and let's move on to the next slide. Physical design contribution BUL. The back end of line is the remaining portion of the IC fabrication steps where the wiring is done through metallization and vias, including the dielectric separators among various metal layers. So you can see the FUL and BUL, if we add these two things together, the entire chip fabrication steps are achieved. BUL goes like this: silicidation of polysilicon and source drain diffusion. Then adding a pre-metal dielectric PMD and CMP processing it. So this PMD is a kind of dielectric which covers all the basic active and passive devices which have been made. Make holes in the PMD and create contact point through it. Then add metal layer 1, then add dielectric, also known as intermetal dielectric, IMD. So this is different from the PMD. PMD covers all the basic active and passive devices, and IMD is spaced in between various metal layers. Through CVD, that is chemical vapor deposition, we make vias through IMD to connect lower metal layer with higher metal layer. Carry on the last 3 steps as mentioned above until all the metal layers as per the technology node are done. Add final passivation layer to protect the chip. So this final layer covers the entire thing and it protects the chip from natural oxidation or that kind of damages. Hey guys, welcome back. In today's episode, we are going to discuss these below points. Complete design kit. We'll talk about all the subdivisions. Init files, these are tool dependent initiation files. Process design kit, PDK, its technology data, and process design kit, its physical verification decks. Next, we will talk about IP kit, where the major section of the cells are standard cell library. In addition, one most important IPs are semiconductor memories. Also, we need to have the high-speed interfaces to connect to the external world for that particular design. So we have high-speed. And finally, there are some analog blocks which may be necessary as per the design. So this is the menu for today, and without any further delay, let's begin. Complete design kit. Now, the design kit can be subdivided into 3 sections. First is the PDK or process design kit. The second part is init files, that is initiation files for tools. The third part is the IB kit or the library. Now, in some of the companies, there could be a little bit rearrangement among these classification or subdivisions. However, grossly, this particular classification is there. So, the PDK generally contains tech file, design rule manual, NXT-GRD file, ERC, LVS, ERC, ESD and antenna rules. Also, EMIR rules. So this PDK part comes from the foundry. The init files also comes from the foundry. The IP kit may come from the foundry or foundry partners. The IP kit contains the vast standard cell library, essential semiconductor memories, analog IPs like PLL, high-speed interfaces and IU-bad IPs, init files. So let us elaborate here. So these are basically the shell script files somehow related to the tool initiation. Some of these init files can be tool specific commands also. Now, what in general we can find the PSHRC file for license setup. There will be a license daemon and the license path. All those things will be there, compatible to your CSHRC file that will come along with the PDK or the entire design kit distribution, which you have to add into your own PSHRC file. Next comes various.rc file. These are configuration files for different tools that you are or your team or multiple teams inside your company are going to use. So they could have a .something rc name or extension. Then you can have project specific init files. Say your company, you have 5 groups. Each group is working on a separate project. There could be project specific init files. Path inclusion file. These are generally there and you have to use them to include various paths of the tool installation or licensed installation or some bare necessary files, or it could be the working path of your projects. Process design kit, PDK. First, look at the technology data. What type of technology data that comes along in the PDK? I again tell you that PDK comes from the foundry. So the technological data that comes, that is compatible or must use for the semiconductor fabrication process, or somehow it is related to the fabrication process. First, there will be a tech file. This is a must. It will be there. Sometimes there could be a variant of this as per the tool, or it may be the basic tech file. Metal, via, contact layer, etc. information will be there in the technology data. Intrinsic and extrinsic silicon layer information will be there. Layer names, layer purpose, pairs here will be there, and layer maps will be there. Colors, fills, and display attributes will be there. Process constraints will be there. Next, another important file is the GRD file that will be there. And the most important part is the human readable design rule manual will be there. Generally, this is in PDF format. So this will be there, which you can read by yourself. So this is a gross content of the technology data inside the PDK. Now, let us look into the physical verification decks part of the process design kit. What all type of verification decks will be here? Design rule check. Here, so this is a basic thing. When you do a layout, this thing will be there to check whether you are making any mistake as per the rules set by the foundry. Layout versus schematic LVS check. So this is your layout versus schematic check that is also done. So these rules will be there. Antenna and electrical rule check. These two are also very, very important. Antenna is a kind of fabrication error that happens, and the electrical rule check is checking the electrical connections in the circuit. Electromigration rules. I have already one episode on the electromigration, so you can go ahead and watch that. IR drop rules, aging rule or models. These are used for degradation, performance degradation calculation over time. PDA tool specific rules. Here you can have a good ensemble of what type of physical verification decks are. Many times these things could be tool dependent, so there could be 2-3 variants of same rule or 2 to 3 different EDA vendors. IP kit. We have covered the physical design kit. Now let us go into the IP kit and we start our discussion with the vast part of the IP kit, that is standard cell library. What all there in the standard cell library? It's difficult for me to capture everything in one slide. However, I tried to put in a concise form wherever I can. First, we have the primitive gates library. Next, we have the power management cells and have some names like isolation cell, level per cell, retention cell, power switch cell. All these will be there. Some special cells will be there like cap cells, filler cells, SPO cell, antenna diode. These are used for various particular needs during physical design. Some more to this special cell list are decap cells, end cap cells, tie cells, and spare cells. Power performance area based architecture variation of cells. Now, here is a kind of figure of merit. So, standard cell can have their variation based on the power, performance, and area. If you consider 3 different words, there could be variation in each of them, and based on that variation, the standard cell library can expand a lot. Track, that is cell height based architecture variation. This is another parameter which can expand the number of cells in the standard cell library. We have a OR gate and it has multiple cell heights, so there will be 5-6 variation of the particular gate, and in that case the total number of cells in the library will be increased. And imagine if this kind of variation is happening for each and every cell, so entire library will become very fast. Next we have the Verilog VHDL system Verilog views for the front end, and we have the timing library which may be in either of the formats like LDM, CCA, CSM, and there could be corner wise vary like fast, typical, slow corner. I have created already one episode on the library. Go ahead and watch that episode. Finally, we have the LEF, EDS2 views for the backend. So these are individual cells view. These are not the entire layout that is you are going to make in the backend. These are the unit cells views which you will be using as is, that is kind of ready-made fashion in your end design, that is physical design. That's all with the standard cell library. Let's move on. The next part in the IP kit is the semiconductor memories. It is very important. Start with the cache memories really you can find in the CPUs. There could be a SRAM compiler. Generally, the SRAM memories are generated with a compiler. Next comes the non-volatile memory cells. Next comes the DRAM cell. Next comes the flash memories. So, the DRAM memories are battery-powered RAM. Let's move on to the next part, which is called the high-speed or interface. If these IPs are needed, connect your design to the outer world. There are various types of IP like SATA IP, EMI IP, IO pad IP, network on chip, Bluetooth IP, Ethernet IP, serializer, deserializer, commonly known as SerDes IP, universal serial bus, commonly known as USB IP, VP5 families of IP. There may be a case that in your design kit, all of them may not be there. Whichever your design needs, those things will be there. Same is true for the memories that I have shown you just previous slide. The next part in the IP kit is the analog IP. Based on your design, analog IPs may be required, may not be required. So you can find them, you may not find them based on your design requirement. Phase lock loop, PLL-IP is a good example of a DC to DC converter, that is DC-DC IP is a good example. Analog to digital converter, EDC is also a good example of that. And digital to analog ESC is also example. Now, there could be lot other is there out there. As I mentioned that it's your need basis. Your design, if needing some kind of analog IP, that will be there. Otherwise, they will not.
Hey guys, welcome back to the computer screen. In today's episode, we are going to discuss the below topics. What are design rules? DRC in backend of analog and ASIC design, both we will discuss. Then we will go to the topic of various mask layers and their alignment with respect to the significance of DRC, that is design rule check. Next, we will determine the design rule and its various category. Next, we will focus on the factors that influences the design rule. Next, we will do a classification and comparison of micron versus lambda rule. Then, we will see some example of intra-layer and inter-layer design rule. Finally, we will summarize our entire discussion. So, that's the menu for today. Let's begin. Understanding the mask layout transfer. Here is your design layout or GDS2, which you generally draw by hand, and in case of ASIC, you do it by your PNR tool. Finally, the layout or the GDS2 is ready, and you can see it's a hazy image. The reason I will tell you, this GDS2 goes to the foundry and where we develop it on silicon. And finally, the circuit is realized in a HD quality version. That is, you can see the Mario character at left, it is hazy, and at right, it is the HD quality. Now, the reason I have kept this slide is to make you understand the importance of the mask layout transfer. The mask layout transfer does happen through the light diffraction, and we use several mechanisms in mask making process which are interlinked with the design rule check, and that makes the mask ready for the light diffraction process, so that when we develop the mask onto the silicon wafer, our circuit under consideration becomes properly fabricated, you can say, in the HD quality. So here the left hand side and the right hand side, left hand side is your mask, that is the GDS2, and right hand side is your silicon. It's a typical analogy I have placed here. So now we will go back to the root where we will talk about what DRC does to make the layout or the mask to proper shape, so that it gets developed with the light's diffraction process, so that the actual silicon image of it is proper. This is not the only single thing that we do, but also we do the basic electrical safety guidelines to the design rule check. And there are many safety guidelines that are covered by DRC. We are done with this introductory slide, so let's move on to the next slide. What are design rules? Design rules specify minimum feature size or spacing requirement or some geometric constraints between layers or masks of the same type or different types. So this is design rule. The next point is the design rules are mentioned in ASCII or PDF format in the design rule manual, or sometimes it is also called the design rule document. Each physical verification tool have its own format of reading the design rule. This point you must be very cautious, because the design rule decks that you use for tool A, you may not use them for tool B. For tool B from other EDA vendor, you need a separate set of files. However, fundamentally, the rules will be same in the two files. These two will be different because of the file format accepted by the physical verification tool. Design rule set are usually supplied by Foundry and comes along with the PDK or DK distribution. So generally when you order the standard cell library or your PDK or both, you will get the design rule decks inside those distribution. In case you do not have, that time you have to consult your DRM that is discussed in point 2, and you have to write your own design rule decks. Generally, this language of writing design rules is TCL, or it may be a proprietary language which may vary from one EDA vendor to another EDA vendor, and it may vary from one tool to another tool. Technically, the design rules are the interface between design engineer who is working at the SoC design house and the process engineer who is working in the foundry to make the wafer. So design rules acts as the missing link in between these two engineers. Design rules are written in a way that they can be forward compatible to upcoming generations. That means whenever we have a next technological progress in terms of technological node, they can be ported into the next technological node with minimal modification. Thus, the rule decks are written. It may come from your foundry, or you may write your own as per your situation. Design rules ensure that design made through EDA software will perform reasonable after your circuit is fabricated. This means when the circuit is fabricated, you can get the expected performance and expected functionality from the circuit. So the design rules also ensure these things for your design of the circuit under consideration. We're done with this particular slide. Hope you have understood what are the design rules as an introductory point. Let us move on to the next slide. VLSI design flow. Our entire VLSI design flow is split into two parts, that is front end and back end part. So generally the DRC, that is the design rule check, using the design rules which are derived from the design rule manual are taken care into the back end part. So let us move on to the next slide to elaborate these things. So here we will talk about the backend flow in both analog, that is IP design part, and the SoC design part. So at left hand side there will be the IP or the analog design part, and right hand side will be the SoC design flow, that is the backend only. Here in this direction of the arrow, the flow will proceed. So in left hand side you can see the analog icon, and right hand side you can see the SoC. So these are signifying what is placed where. First, in analog or IP design we have the schematic design. Next, we do the layout design using handcrafted layout. Next, we perform the DRC and LVS checks once the layout is finished. Next, we do the RC extraction on the finished layout and clean the DRC and LVS on that layout. Then we go thorough physical verification of the layout and the RC extracted netlist. Finally, we go for its electrical characterization and or its delivery. This is the backend flow. Mainly, only the first line is for the front end and the rest of the part is for the backend in the analog or the IP design. And right hand side here, we start with the front end design. We are not talking much more in the SOC part and we are directly jumping to the backend. The backend start with the floor planning and PNR. And next we have the DRC and the LVS. And next we have the RC extraction, STA and physical verification, formal verification and sign off. Now all these things will go through and your design will pass through all these stages, which is very similar to the analog part. Only the difference after the RC extraction is the STA, which is not present in the IP design. And also in the right hand side you can see the formal verification and sign off. So here you can see that the both cases, the DRC and LVS in a single step we have mentioned. So this DRC is very important if you're doing a block level design, that is a IP design or an analog design or a SOC level design. In both cases, the DRC checks are mandatory. You cannot skip the DRC because it will harm your layout in final performance on silicon. So the DRC here we have pinned out where in both in the analog or the IP design backend as well as in the SOC design backend at what stage the DRC is performed. Now let us move on to the next slide as we have finished our discussion on this slide. Various mask layers. Here we will talk about generally present various mask layers which are used to create the layout. Now we talk about the layout. Layout is nothing but the layout of the mask and each part we create in the layout is a single mask. So what elements we can have in a layout, we will go through a brief description. This is a very limited example. However, in actual case you may find many layers in addition to whatever we are sharing here. So we start with the metal and then here we can have the metal 1, metal 2, metal 3, metal 4 and we can proceed further on as per the metal layers permitted in a particular technology node. Next we have the wells, we have the poly, we can have different type of wells and we can have the poly gate. Then we can have the contact as a cont layer and we can have the via which connects the two metal layers. Contacts generally do the contact with the silicon say source or drain gate. There you need a contact layer to make the contact, and via will connect the two metal layers in the routing stage, that is in the BUL stage, and contact is used in the FUL stage. In case you do not know what is BUL and FUL, I have explained in one episode. You can find in the same playlist where you are watching this, or you can go to the playlist of this channel and there you will find the VLSI FAQ. Here you will find about the BUL and FUL processes under the silicon fabrication process. Let us proceed with our discussion here. Active layer. So here is NDIF and here is PDIF. And we have NFET and PFET. So these could be there, some could be not present and some could be present. So it depends upon technology to technology. Generally the NDIF and PDIF will be there. Next we have the select layers, so N plus and P plus. And we go further on. So these are few typical layers that you will see in a layout or mask design generally, and there might be additional layers or variation of a particular say metal. You may find metal 5, 6, 7, 8, 9, 10. So this you may find there. However, these are the typical layers that will come across. Now we are done with this example. Let us move on to the next slide. Determining the design rule. Here we have a NMOS and we have a PMOS. We are about to draw a layout of a PMOS circuit, that is a NMOS and PMOS. Here is our N well. You already know about the N well from the previous slide. And here is the P select layer. So each layer which I am right now drawing contributes or act as a mask during the actual fabrication process. And DRC, that is the design rule check, plays a very important part when we are drawing this each mask like N well, P select, one on top of the other. DRC plays a very huge role. We will come later. Let us now see what we do sequentially and which mask we create by our hand. These things we create by our hand and we proceed like that. So here it is our diffusion layer, and next we go to here, it is the N select layer. This is what the NMOS, and here we again have the diffusion layer. Next we have the contacts. Here we also have the contacts. Next we draw the poly get connection. So you can see we draw different mask layers one by one in a layout tool in the same fashion that we are doing right now. And each of these layers, segments, they will contribute to the mask process during the fabrication. So each individual part that we are drawing will be taken as a mask and light will pass through that mask, and accordingly the layer will be formed in the silicon through the semiconductor fabrication process. Now this is poly, we have already talked about. Next we make the connection with the metal 1, and here we go towards the VDD. This is metal 1, the first metal, and here it goes to the ground. So you also see the metal is here, and we place a contact here again on the metal. Here we have drawn it, and one more thing here, that when we are drawing here, everything is not on scale. However, when we are drawing, generally the PMOS is double the size of the NMOS. That we take care because of the mobility matching of N-type carrier and P-type carrier. Now here we are done the drawing. Here you can see that we have used several layers and created their instances while making a CMOS. While fabricating, each individual layer, or rather we call them mask, will be used for the fabrication. And one more thing here, when we use each mask, they will be used in a batch process. Say we are processing for metal 1, so every metal 1 will be processed in one go. We are processing for poly, every poly mask will be processed in one go. So these are kind of batch processing for all of the segments that is present in a single layout which has come as DDS2. Now we are done with this particular slide, so let's move on to the next slide. Mask layer sequence alignment. So this is a very important slide. Why we are going through this? It's a very simple slide, simple to understand. However, you will understand the significance of DRC when we draw each of the segment. How the mask sequence is introduced while the fabrication process. First, we have the N-well. It is created first the N-well mask segment. So you can imagine this, all these segments we have used in the CMOS layout drawing. From there, we are taking one by one, which are the sequence in actual semiconductor fabrication process. So N-well is first done. Then we have the poly, we have the N diffusion, we have the P diffusion, we have the contacts, we have the metal. So this way, each individual segments are picked up from the layout and they are fabricated on the silicon through the semiconductor fabrication process. Whatever layout you are drawing by hand as a block level or the IP level, that will finally be used in the semiconductor fabrication process. That is the main motto of this slide. However, I am not saying that every sequence here mentioned is a correct one. For that, you have to follow a foundry process, how they are processing, what comes first and what comes second, and what is the sequence. So this is a typical hypothetical example how you can have the each segment that you have drawn getting fabricated and used as a mask on the actual silicon. We are done with this example. Let's move on to the next slide. Factors influencing the design rule. Mask alignment accuracy. In the previous slide, we have shown you the different masks separately picked up and used for the fabrication. Now their alignment accuracy, we will talk about the importance. Inter and intra spacing of the mask, which are very important. How accurate is one mask aligned to another mask? So there are two different mask layers, say metal 1 and poly, how they are aligned to each other. Now the DRC engine, which will read the design rules, will check the followings: active to active spacing, well to well spacing, minimum channel length of the transistor, minimum metal width, metal to metal spacing, metal field density, or process using the CMP. It is a part of the semiconductor fabrication process. Next, it will check the ESD and the IO rule. So all these things the DRC will check. So ESD is also very important in circuit fabrication and its sustainability. All these things are checked through the design rule check. If you consolidate the previous slide and this slide, the meaning comes clearly to your mind why the design rule is very much important. Now we are done with this slide. Let's move on to the next slide. Design rule classification. Here we will categorize the design rules. In this direction, the flow will go down. So first, if we try to segregate the design rule with respect to the unit, we will find the micron rule and we will find the lambda rule. So micron rule is there and lambda rule is there. These two rules are there. Rule spacing. If we want to segregate or have variation with respect to the spacing, we will have the intra-layer rules and we will have interlayer rules. That means we will have some rules that will be for two different kind of layers, which we will talk about their spacing and all. And we will talk about the intralayer. That means for the same layer segments, how their spacing between them will be there. So these are the two typical type of categorization of the design rules. We are done with this slide. Let's move on to the next slide. Micron versus lambda rule. Each semiconductor process step imposes a set of design rules on the geometric component size, relative position, etc. These rules have subtle differences, however, the common theme remains the same, mainly to use the proper geometric shape and separation to create a reliable manufacturing process. There are two major types of the design rule category. Micron rule. Here the layout constraints such as minimum feature size and minimum allowable feature separation are stated in terms of absolute dimensions in micrometers or nanometers. So this is an absolute unit, the micron rules. The lambda rules. Here the layout constraints are expressed in terms of a single parameter lambda, hence allow a linear and proportional scaling of all geometrical constraints. So this is a relative rule. So micron rule is an absolute rule, lambda rule is a relative rule. So these are the two rule categories. Now we are done with this particular slide. Let's move on to the next slide. Design rule example, intra-layer rule. Here in this particular slide, we will have some example. Let us begin. Here are three blocks of the drawn wells, and for each we have the minimum length is 12. Its unit I am not specifying here. Whatever the unit may be, 12 unit of it should be the minimum dimension. Now, if two, the leftmost and the next one are on the same potential, they will have a difference of 5 unit, and in case they are on different potential, they will have a difference of 10 unit. So this is a typical example. Now we move over to poly. And these are the two poly segments if we draw in a layout. So the minimum size will be 5 units and interspacing will be 5 units. One thing has to be mentioned there. Values shown are here fictitious and educational purpose only. So here whatever value I am giving, these are for your education purpose only, and these are not taken from any design rule manual. However, if you go to a design rule manual, you will find similar examples with real values in actual design. So let us continue with our example. Here is an active layer, two active layers are there, minimum width is 4 and interspacing will be 4. Metal 1, here are two segments, minimum width 4, here spacing will be 4. Select is there, here are two select blocks, minimum width is 4 and their intermediate spacing is 3. Similarly, metal 2 is here, two segments and minimum width is 6 and their intermediate spacing will be 6. So here I have given a hypothetical example with hypothetical values. If you consult a real design rule manual, you will find this kind of rules with real actual values. Why I have given? Because you can see the patterns are very repetitive for each and every layer. So their minimum width, their minimum spacing. So these are kind of things you will find in the design rule manual, which is in ASCII, that is in the text format. So we are done with this particular slide. Let's move on to the next slide. Design rule example, interlayer. So here we will give a similar example as the previous slide, and here we will talk about the interlayer design rules. So this is NWEL, this is PDIF, this is our poly. Now here I emphasize again, values shown are here fictitious and educational purpose only. So values are not from real design rule manual. However, if you consult a real design rule manual, you will find actual values for similar cases. So between poly and PDIF, the minimum spacing should be 2. This direction, this should be 8. And here this should be 4. And this should be 6. So this way, the values of interlayer design rules are specified. You will get explicit details in the design rule manual. If you cross compare the design rule decks and the design rule manual, you will understand all these things in terms of the actual layout as well as in written text. So we are done with this particular slide. Let's move on to the next slide. Typical category of DRC rules. Here in this slide, we will talk about the different subcategories of each of the design rules that we can find. Intralayer. What the intralayers here design rules will contain: width, spacing, length and width of transistor gate. Interlayer. It will contain enclosures, overlaps, separation between two wires on the same level, widths of wires, contact pad for vias, well and substrate contacts, cross-section of vias, size of wells, area, antenna rule, and density rule. So antenna rule is another special thing. I can make another separate episode on antennas. For now, you can have this set of typical category inside the design rules. So once you have the real experience of the design rules, you will understand the significance of this slide. So these are the types of the design rules. Otherwise, if you go through the entire design rule deck and compare the design rule manual, you will get lost. There will be so many rules because they are split into each individual rule. However, if you want to categorize them for your easy remembrance, then this slide will be very important to you. We're done with this particular slide, so let's move on to the next slide. Summary. So let us summarize whatever we have discussed so far. All design rules are predefined by Foundry. Design rules are available through Design Rule Manual, abbreviated as DRM, in text, that is ASCII format. Design rules are interpreted by any physical verification tool through tickle coding or tool-specific proprietary language. Layout tools may have on-the-fly live DRC check during your layout drawing process. So this is a very advanced process, and nowadays I think all the layout tools have this thing inbuilt. To understand any DRC violation, you need to cross-reference DRC rule code and DRM. So this is the very important point, because if you have a DRC deck of say any physical verification tool, to understand that you have to cross-reference the DRM, that is the design rule manual or design rule document. That's how you interpret or understand the rule, and in the same way, this thing you will be using when you are debugging any DRC error. We are done with this particular slide. Let's move on to the next slide.
Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and LVS. Next, basics of LVS. Third, process overview and challenges. Next, layout versus schematic flow. After that, LVS issues and debug. Design flow and LVS. So this is the standard design flow, starting from design specification, then RTL coding, verification, synthesis, DFT. And after that, it's entering backend from flow planning, partitioning flow planning, power planning, global placement, detail placement. That flow planning, power planning, we have already done partitioning, and along with power planning, pin assignment is also done. These are the steps: global placement, detail placement, clock tree synthesis, we have done it. Global and detail routing, layout, generation or changes, and next comes DRC and LVS. This is basically backend verification. DRC and LVS, always we heard these two terms very closely. Always it's uttered together. DRC means design rule check and LVS means layout versus schematic. These are very basic and important steps of backend verification along with EM and IR. So these two steps, in most of time we heard this DRC and LVS, these two terminology together. Today we will discuss about LVS. We already have an episode about DRC. Link is in the description. Watch it or read the article. Both the links are provided in description. So today we will talk about LVS. So in nanometric era, designs are becoming more complex and chip sizes are growing. Know that to make sure design is correct, larger layout databases need to be checked during physical verification process within the same tight project timeline. It's a competitive market and we have to launch our product within predicted time, otherwise we might lose the package. If an error is found after the design is built, it will lead to costly mask changes and delays in releasing the SoC. We need to check, we need to make it sure that whatever we intend to do here, that is when we do a design specification, we have certain target in our mind that we want to achieve this kind of performance. That should be done by our chip. Building the mask is a costly affair. Time-wise, material-wise, it's very expensive. Before tape out and before making the mask, we have to make it sure that whatever design we are taking towards tape out exactly representing what we have intended here. That means design specification is perfectly translated into the mask or layout. LVS is one of the way to take it. Physical verification ensures that the design layout matches the schematic and changes if the layout follows manufacturing rules from semiconductor fabrication labs, ensuring it can be produced correctly. There are some rules. When we have a design, we have a layout, it's good. Although, since we are following a technology node, according to a technology node, when it is going to get fabricated in foundry, it has to follow some rules. These are the rules. We cannot change it. These are the unchangeable rules set by foundry. These are basically design rules. In DRC step, what we do, we check whether our layout, what design we have done is following that guideline. We cannot break all those rules. Otherwise, it will create problem while manufacturing. DRC are the checks if the design layout follows the rules needed for it to be successfully manufactured by the fabrication lab. We have to follow it. Although it doesn't mean that layout is doing exactly what we as intended in design specific. We do it in LVS. LVS verifies that the design layout works the same way as the schematic of the design. Yes, it does not guarantee that the layout will work as intended. It only checks if the layout follows the fabrication rules for error-free manufacturing. DRC focuses on ensuring the layout can be made correctly, but it doesn't confirm that the circuit will perform as expected. The need for LVS came from this limitation, as LVS checks if the layout matches the intended circuit design. From here, we can understand what are the importance of DRC and LVS. Both are important for successful tape out, and since we have already discussed DRC in some other episode, here we will concentrate about LVS only. Next slide. Now, basics of EVS. A EDA tool performs LVS using a set of code instructions. Those set of instructions are LVS rule deck. LVS rule deck guides the tool by providing necessary instruction and identifying required files for the process. So obviously LVS is done by so many proprietary EDA tools from famous EDA vendors. Now we have another tool which is free and open source. We don't have to pay for it. That is NetGen. So here we will use NetGen for LVS purpose. There are so many tools are used in industry. Those are industry standard, and also in NetGen has a standard. We will discuss it later. That is quite good for our study purpose, our practice purpose. It's quite good. So we have chosen NetGen. Now LVS is done in 2 steps: extraction and comparison. We understand that when we need to check whether the layout is working as per the schematic, there is a comparison. There are 2 steps: first extraction and comparison. Design inputs needed to run LVS include GDS layout of the design, schematic netlist of the design, cell definition file including IP files and standard cells, pad reference file. The GDS layout is required. From there we extract a netlist. That netlist is compared with schematic netlist of the design. Both are compared. The LVS rule deck is written in formats like SVRF, Standard Verification Rule Format, or TVF, that is Technical Verification Format, and helps the tool extract the devices and connections of the circuit. It defines the layers used in the layout and matches layer descriptions to their locations in GDS file to identify electrically connected regions known as nets. The rule deck also includes definitions of the device structures. This is the basic knowledge about LVS. Before we start studying LVS, we need to know all these are the prerequisites we required. We are done with this slide also. Let's move to the next slide. Now process overview and challenges. Now process overview. Circuit designers create a schematic using fundamental devices like resistor, transistor, the basic components we use in our circuit. Circuit designers create a schematic using all these fundamental devices. The schematic is converted into netlist, that is SPICE format. For simulation and comparison, we already have a series of SPICE. Watch that series. Link is provided in the description box, playlist of SPICE. Watch that. When we will discuss about netlist, we need to understand which part of the netlist which is written in SPICE format means what. So for that, watch it to understand properly. Now layout engineer generate a layout based on the schematic, considering placement, sizing and design rules. The layout is extracted into a netlist, which should represent the same circuit as the schematic. The layout is extracted into a netlist. So one netlist we get from layout. and another is from the same circuit as the schematic. So we have to compare these two. Purpose of LVS: identify error introduced during layout process. The schematic is usually assumed to be correct because it's used for simulation. The LVS is essential for checking manual correction or verifying automated layout synthesis. What are the challenges? Challenges are errors in layout or synthesis can create incorrect circuits. LVS helps pinpoint these issues. Full chip verification through simulation can be time consuming and complex. So LVS is a quicker alternative. Full chip verification is a step and it's get done. Post simulation is a process for that. So we are done with this slide. We will move to the next slide. Now layout versus schematic. This is layout, at least expected from that. That is schematic netlist, extraction and comparison, LVS report and analysis of the result. If it's matched netlist, then finished. If not in unmatched, then there should be some change done the layout. So LVS flow work in two major phase: extraction and comparison. Extraction phase, verification tool takes the DDS file and breaks it down into basic design components like transistor, diodes, capacitor and resistor. These components are identified by recognizing the layers and shapes in the GDS file or by using cell definitions from the IP blocks or the LVS rule day. The tool also extracts connectivity information between these components from the GDS file. GDS file is full of geometrical structure. All the devices and everything is represented. That is layout basically. So represented with geometrical structure. Layers after layers after layers. So extraction of information is done from those layers. So during connectivity extraction, each electrical net is given a unique node number for easy identification. Otherwise, it's not very easy to identify. They look all same. Color code is only used there. All look same. Layers after layers. So unique node number is given. Net names can also be assigned based on text object in the layout or control file. This device and connectivity information is written into layout netlist file is called the layout extracted netlist. The step is known as extraction. Now what is comparison phase? The verification tool compares the electrical circuits from schematic netlist and layout extracted netlist using the LVS rule day. After a successful comparison, a one-to-one match between elements like instances, nets, ports and pins in both netlists is established. The goal is to ensure the layout accurately represents the functionality in the schematic. If the netlist doesn't match, discrepancies are reported in an LVS result database, listing issues like incorrect nets, ports or instances for debugging. The verification tool prepares net to net, port to port, pin to pin, one-on-one match between elements. It's done. If the netlist doesn't match, discrepancies are reported in the LVS result and we have to work on that. Like how many incorrect pins or ports or instances that is reported, we have to debug based on that. So we are done with this slide. LVS issues and debug. Now let's try to understand what are the common LVS issues. The source SPICE netlist would match the SPICE netlist extracted from layout. That is the core of LVS. Now, what are the common LVS checks we do? That compare the number of devices in both the schematic and layout. Number of devices. Check the types of devices in the layout and schematic. Compare types of devices. What types of devices are there? Resistor, capacitor, transistor, all. So, compare the number of nets in the schematic and layout. Compare the number of ports. Connectivity issues. Ambiguity points in the designs, cell comparison. These are the common LVS check. And what are the common LVS issues we face? Short between different NIC. Very common. Power short. There is a representative diagram we tried to show here. That is a power short. Another one is power open. Similar type of power line, although there are gaps. So that is power open. Now power short with signal. Multiple wires that should not be connected together become connected. Those wires which should not get connected to each other, they get connected to each other. Now signal open. Wires or components that require to be connected are left floating or partially connected. Deleted instance. Accidental deletion of some particular instance that should be there, it's got deleted. So when we are checking or comparing one to one, then in one point we will find that one instance is less. So there is something missing that will get reported. Now missing will tap. Tap cells provide a substrate connection N-well to VDD and piece up to VSS. So that That means if N-well is used for a connection, missing well tap means basically discontinuity in connection. Overlapping filler cells, missing filler cells. Since filler cells provide power or ground and N-well continuity, missing filler cells will result in power or ground opens between standard cells. Filler cells missing, overlapping filler cells, missing well tap, all this will create discrepancy in the design and that will get reported in the LVS. These are the most common LVS issues. Short, power short with signal open, deleted instances, missing well tap, overlapping filler cells, missing filler cells. These are common. We are done with this slide. We will move to the next slide. Now let's move to the pointers we will cover in this episode. First, basic of VLSI interconnects. Next, VLSI interconnect, local and global. Third, desirable or expected VLSI interconnect. Next, real or fabricated VLSI interconnect. Then, interconnect parasitics in VLSI, back end of line or BEOL. Resistance and reliability, capacitance and reliability, inductance and reliability, and finally, impact of scaling. So, let's move to the first slide. Basic of VLSI interconnects. In a IC or integrated circuit, active designs and regions are electrically connected to each other to make circuit. When these active regions or devices are isolated, they cannot work as a circuit. So they need to be connected and that connect is called interconnects. And these interconnection of active regions, when they will perform, they must connect to the outside world through their input and output bonding pads so that we can insert input data and get the desired result from the circuit. So that is the need of interconnects. So active devices and regions in IC are electrically connected to each other to make circuit. They are also connected to the outside world through their input and output on bonding pads. Contacts, vias and interconnects used for such connections. Depending on the position of the electrical connection, we call them as contacts or vias or interconnects. Next, contact is connection to source, drain and poly. This is source to drain. This is the channel region and this is the contact to the active region. This is the gate region. When the contacts or the electrical connections are directly to the active region like source, drain or poly, we call this contact. Next, via. As we can see in this diagram, this is via. Connections between interconnect levels. This is the metal 1 level, this is metal 2 level. As the technology has progressed, the number of metal layer has increased. Complexity of design has increased. Complexity of connection has increased. So, metal layers has also increased. Between interconnect levels, the connection is called via. And interconnects are separated from each other by dielectric layers. So these are not actually in the vacuum. This area are oxide are there. Dielectric layers separating global interconnect levels are called IMD or intermetal dielectric or ILD or interlevel dielectrics. These are basically the nomenclature of dielectric layer to separate it from the gate level. Next, vias connect interconnects through these layers. Obviously, as we can see, these are perpendicularly. Metal is running from left to right or in lateral direction and vias are perpendicular to it. These components are part of metallization or backend or BEOL. We will elaborate this point. It's very important point that BEOL, when chip is fabricated, first the active regions are fabricated, then these are local connects, these are local connections are made, and then after that last come this metallization process. Fabrication of device is known as the FEOL, front end of line. These all metal interconnects making is called back end of line. Chip surface doesn't have enough space for all connections, so vertical interconnects are built. Active regions are laterally fabricated on the chip surface, so on that these connections are built. Number of metal layers increases with IC complexity. Technology is progressing. Device numbers are increasing because we want to realize more complex functionality, and number of metal layer also increasing accordingly. Aluminum interconnects were used as the standard for long time in chip making, and it's sometimes still it's used. In the late 90s, chip makers switched to CU because it conducts electricity better than aluminum. CU interconnects improved IC performance and can match transistor scaling. This whole fabrication method and nodes that's followed Moore's law in last few decades to increase the number of transistors in the same area. Device dimension have been scaled. So when device dimension is scaled, obviously these via disconnects, these also have to be scaled. Otherwise, it will be a kind of this kind of structure. If contact is like this wider, make contact with half with the source region, some with the drain region, then it will not get proper connection, or proper signal will not go to the upper level. So obviously the metal layer need to be scaled down along with the devices. So obviously we need a material which can match the transistor scaling. Let's move to the next slide. VLSI interconnects local and global. This is the diagram. Well, there are two types of interconnects. Depending on their position, we call it local and global. Look at this diagram. It will help you to understand. This is the silicon layer. These active regions, they are up to this zone. That is the FEOL, front end of line, and then back end of line, this one. There are three parts: local, intermediate, and global. Shown, although we will cover it like local and global. Intermediate layer is very small here. The steps to fabricate this active region and these interconnects are completely different. Their position is different, and that's why there are some issues and concerns are there which are also different for these two layers. Local interconnects at the first or lowest level of interconnects. This is the lowest. Local. These are short. They cover short distances. They connect gate sources and drains in MOS technology and emitters, base, and collectors in bipolar technologies. Local interconnects are small and short. Polysilicon, silicide, titanium nitride, tungsten can act as local interconnects. There are many choices for interconnect material. The reason behind is that local interconnects can afford to have higher resistivity since they do not travel very long distances, but they must also be able to withstand higher processing temperature. Now there are two very crucial points. Local interconnects, as we said, they are very small and they run for short distances. If resistivity of a wire is higher, heating can happen. Longer the length of the wire and higher resistive material, then obviously it will resist the current more. For local interconnects, we must choose a material which can withstand higher processing temperature. Temperature handling capability of that material with which we are manufacturing these local interconnects is higher, then it can handle higher temperature of fabrication of this process or this area. While we are fabricating all these steps, these metal layers, if metal layer or interconnect layer here will break down, then there is no point of making or doing that, because that's a failed chip. It will not work accordingly. Global interconnects are usually made of aluminium. They are above local interconnects. Obviously, physically we can see they are above local interconnect level. Global interconnects are thick, long, and widely spaced. They often travel over large distances between different devices, different parts of the circuit, and therefore they are always metal with lower resistivity. They run longer distances from one corner to other corner. So if resistivity is higher, that resistivity of the material will resist the current, and also heating will be there. So let's move to the next slide. Now, desirable and expected VLSI interconnects. We have some ideal assumptions like where only connects functional elements and does not affect design performance. It's absolutely wrong. They have a huge impact on design performance or chip performance, and that's why we are discussing this topic today here. A voltage changes at one end appears at the other end without any delay. That is where is an equal potential region. We think that it's instantaneous. That's not. Obviously, a function of time, a function of frequency. These are the basically ideal assumptions. In reality, it doesn't happen. There are a list of desirable properties of interconnects. Low electrical resistivity, it's always good to have lower electrical resistivity. Low capacitance, that is low dielectric constant for low RC delay, crosstalk, power loss. High electromigration resistance. What is electromigration? We will discuss it later. Electromigration is a reliability issue for interconnects. Occurrence of electromigration actually leads to chip failure. Ease of deposition of thin films of the materials. Sometimes we need to deposit thin film of material, so not all material is good for this purpose. So the metal we will use that must have that property, ability to withstand the chemical and high temperatures required in fabrication process. We have already covered this point in previous slide. Stable contact structure, there should not be any kind of chemical reaction with the material with which the metal is going to get connected. Then there is no point, because once a chemical reaction starts, most of the time the resulting material will not be that metal or that material, it will be some other materials. Adherence to insulating films. Silicon dioxide is as an insulator the most choiceable one. Later on many other also have been added in the list, although silicon dioxide is the most go-to oxide. The adherence should be good to stick to that material. Low internal stress and surface roughness. These are basically chemical properties. When we are manufacturing an IC, it's basically a lot of materials and their chemical properties, and they should stay side by side to make the design work. Next, easily etched using plasma processes. That material can be easily etched using plasma process. Compatibility with all other semiconductor processes. And finally is low cost, because cost is concerned. Next, real or fabricated VLSI interconnects. Now let's see how real or fabricated VLSI interconnects behave in real world. Interconnects have resistance, capacitance and inductance per unit length. Wiring of IC forms a complex geometry that introduces capacitive parasitics, resistive parasitics and inductive parasitics. All the basic rules of electrical networking get applied. A real material has resistance, they have some capacitance and inductance value. A layer of metals, they are separated by the electric layer and current value is really low. When we consider the dimension of the geometry, flowing current in different nearby two conductor, they impact on each other. What does parasitic do? Increases propagation delay, causing a drop in performance. Impact on energy dissipation and power distribution. If the long interconnects have all these parameters, these resistive, capacitive and inductive value, then obviously current travel from one node to another node, there will be some changes which is not desirable and introduces extra noise, resulting in reliability of the circuit. We need to model the resistive, capacitive and inductive parasitics of wires, and accordingly we must do our checking and steps so that the chip doesn't fail. So what we do, the back end, there are so many reliability steps are there that actually includes this effect of resistive, capacitive and inductive parasitics. So modeling of wire capacitances is a non-trivial task. It's a really tough work. There are two types of capacitance occurring: parallel plate and fringe capacitance. Capacitance of wire is a function of shape, distance and surrounding wires and substrate. The resistance of a wire is proportional to its length and inversely proportional to its cross-section A. We all know that R is equal to rho L by A. Inductance in interconnects is represented by voltage drop due to rate of change of current with time. In earlier days in research, only R and C components used to take in consideration, and later on in higher frequency this L component is also considered in doing modeling and all. It's a real tough modeling and very necessary and very crucial. Now, parasitic extraction. That's an important part. Parasitic extraction, there is a file format called SPEF, S-P-E-F, parasitic values of a circuit that is written in its IEEE format, obviously tool generated, not human written file format. It's written in that file. Standard EDA tool is used to extract parasitic values, and it's a part of back-end, part of basically physical design. Parasitic extraction is to calculate the parasitics of wires and create an analog model of the circuit. Extracted parasitics are included in timing power analysis to get more realistic result. When we consider there is no realistic hindrance like resistance, capacitance and inductance, our study is something. And when we include all this delay and all, then performance will be completely different. Before sending the final layout to the fabrication unit, we need to analyze it from all angles so that after fabrication, after putting all the money, it doesn't fail on the realistic world. The chip doesn't fail. Standard Parasitic Exchange Format is an IEEE standard for representing parasitic data of wares in a chip in ASCII format. We already have an episode on SPEF file format and its impact and importance all. Link will be given in the description. You can watch it. Now, interconnect parasitics in VLSI. We said that resistive, capacitive and inductive. So this is the resistance. The resistance of a wire is rho L by A area, this cross-sectional area, the height with width. And this is the basic formula we all know. Now let's move to inductance. Inductance of a section of circuit states that a changing current passing through an inductor generates a voltage drop. That voltage drop is proportional to change of current with time. Delta V or change of that voltage drop is proportional to di dt. An important source of parasitic inductance is due to bonding wires and chip packages. If that is the circuit, that must be connected to the outer world. So from there, and this connectivity, their inductance value is not very negligible, and in transient and in switching mode, current need to change. That time, that inductance comes into place. Again, interconnect parasitics. Now capacitive. There are two types of like parallel plate capacitance and fringing capacitance. This is parallel plate capacitance. This is substrate dielectric. The simpler model, that is C is proportional to epsilon 0 epsilon RDI, that is the dielectric layer, divided by TDI and then WL. Width and length of the wire, TDI and epsilon DI represent the thickness and dielectric layer and its permittivity. Fringing capacitance is between sidewalls of the wires and the substrate. This is the equation. So when we consider total wire capacitance, so total wire capacitance would be fringing and parallel plate. CPP plus C fringe. This is the total. Now let's move to the next slide. Now back end of line. So let's see what are the steps by which we make these interconnect levels, that back end of line. The back end of line or BEOL is a portion of IC fabrication where the wiring is done through metallization or vias, including dielectric separators among various metal layers. BOL steps are like silicidation of polysilicon and source drain diffusion. It starts from there. Then adding a pre-metal dielectric or CMP, processing it. It's a step. Make holes in PMD, pre-metal dielectric, and create contact through it. A pre-metal dielectric is fabricated and then a hole is made through it and contact is done through it. Then add metal layer 1. First metal layer is fabricated. Then add dielectric layer, that is intermetal dielectric. One metal layer is fabricated. Now intermetal dielectric is done. Then through CVD makes vias through IMD. A metal layer is done and then we are adding intermetal dielectric. Suppose it's a metal layer and now whole area we are oxidation and now dielectric layer is done. So even if we vertically, if that is the vertical direction, we make another layer of interconnects. We need to connect. There will be a separator. So we have to make hole through it so that this layer and that layer get connected. Carry on last 3 steps until all metal layer as per technology node are done. When a technology node is defined, it always the process is optimized. When a fabrication unit release their data regarding one new technology node, they include all the metal layers and everything. Last 3 steps means add metal layer, then add dielectric layer or IMD, and then make CVD and build these vias through IMD. If 7 or 8 metal layer is there, so this process will get repeated for that many times. Then add final passivation layer to protect the chip from weather and outer world. Now BOL corners, that a very important part. What are BOL corners? Back end of line corners. It's part of RC corners or PVT corners, process voltage temperature corners. We have detailed video and articles on that. So link will be given in the description. I'm going to tell here in short. parameters of a semiconductor fabrication are generally statistically distributed because it's not an ideal process. It's a real world. Not all two devices have all the properties same. Some variation occurs in length, width, oxide thickness and all. Since in a wafer, ICs we fabricate, they are not identical. We must judge their merit within a range of data, not a particular one data. Because when a device is very small in dimension, half of nanometer is even crucial factor. For a batch of ICs, we define basically a range of values. And these are some corners like this extreme values. Some value comes from BOL steps also. These are basically C worst, C best, CC worst, RC best, RC worst. In detail, you can read the articles or watch the video. So let's move to the next slide. The impact of parasitics. Now resistance and reliability. Electromigration. In operating condition, a chip may go above 100 degrees Celsius during practical operation. High frequency power loss and consequent heat dissipation contributes in increased temperature. Since the interconnect have resistive properties, so heat dissipation is always there. Continuously, the temperature of the chip increases, and rise in temperature enhances solid state metal ion diffusion. It's basically material level performance. So electromigration is caused by scattering of moving electrons with the ions, that is by momentum transfer between electrons and ions in metal interconnects. While in operation, chip temperature increases depending on how long it's open to that situation. The moving electrons within the interconnects, they scatter the ions or the metal molecules. So momentum transfer happens between electrons and ions in metal interconnects, and this ion-electron interaction is sometimes referred to as electron wind. This causes the wire to break or to short circuit to another wire. Such situation create void in interconnects that can lead to open circuit. If ions from this zone is moved, either there will be a void, and if it's moving to and getting to another wire, so it's basically doing the short between these two. In both the cases, the electron flow or the current flow will not be in the desired direction and chip will fail. EM is one of the most menacing and persistent threat to interconnect reliability. So these are some pictures. As you can see, there is a void in via. The electron is traveling, and you can see this zone, right? Metal layer has, if it's go a little bit more, it will touch it and there will be a short. There is no point. This black dark area is basically in intermetal dielectric, but this electromigration process is doing that. Look, it's connecting. So here it's creating an open circuit, and here it's almost going to make a short circuit. So in both the cases, the chip will fail. And we have 3 episodes on electromigration, link provided in description. Now, ohmic voltage drop. Current flowing through a real wire results in an ohmic voltage drop that degrades the signal levels. It's a real wire, so ohmic voltage drop will be there and degrades the signal level. Chips are basically operated at lower voltage level. Even from that, if some voltage get dropped at the interconnects, at the destination, the voltage level degraded. If it drops below the driving current of a system at the destination, the device will not perform accordingly. Suppose there is a signal is traveling a longer path from here to here. This is a block, that is a block. Here block 1 and that is block 2. So if this length is longer enough and voltage drop is enough, when the signal travels from here to there, there will be a significant amount of voltage loss. And if it very higher, then sometimes it may happen that the reaching voltage of signal just fall below the switching value of components here, present here. So desirable performance we are not going to get there. The affected value of voltage reduces noise margin and changes the logic level as function of the distance from supply terminals. As the distance changes, how much voltage is getting dropped there, the voltage margin level gets changed, and that change all the thing. IR drops on supply network also impact the performance of the system. A small drop in supply voltage may cause a significant increase in delay. These are the effects. Now RC delay. Signal doesn't travel instantaneously in wires, and that wires and delay of wire grows quadratically with its length. So length increases, delay also increases with that. The signal delay of long wire is dominated by RC effect. This is becoming even bigger problem in modern technology, because we said the more the technology is advancing, length of interconnect is increasing and layer of metal layer has increased. This leads to situations that take multiple clock cycles to get signal from one side of a chip to its opposite end. Its delay becomes so much, multiple clock cycles required to reach a signal from one corner to another corner. Next, capacitance and reliability. In real world of IC, each wire is coupled to both grounded substrate and also to the neighboring wires on some layer and on adjacent layers. Through via the layer of interconnects are connected to each other. It's not completely isolated. So some capacitive components connect to other wires with dynamically varying voltage. Capacitive components, they are connected to other wires where the voltage level changes. So effect of that change have some impact on the capacitive components also. And such variable or floating capacitor causes crosstalk and a negative effect to the circuit. This varying capacitance value have a deep impact on the circuit performance. Delay in the signal transmission through wire is proportional to the capacitance charged. And more capacitance means more dynamic power. Coupling capacitance is an increasing source of noise and make delay estimation hard. This coupling capacitance, it's an increasing source of noise and makes delay estimation really hard. In a practical situation, a wire is surrounded by wires from other sides and in between dielectric layers. So many parallel capacitors in all sides, and they all are within ambience of IMD. When we take the whole picture, it's a very complex model. Even if all the capacitance have smaller contribution, the overall contribution, and even with changing voltage, switching effect is happening, voltage level is changing, because we are not designing a system for keeping it idle. It will work. Voltage level will go up and down accordingly. Our design, when the total picture is there, it's a tough thing to calculate. What are the steps we can take to reduce interconnect capacitance? Use of low K dielectric, which reduces permittivity and hence capacitance. Low K means lower than silicon dioxide, and in high K we consider it as compared to silicon dioxide, because for many years silicon dioxide has been considered as the golden one. Increase the spacing between wires. We are downsizing the transistor dimension. When we are trying to adjust more devices in a IC or in a wafer, at that time increasing spacing is not always possible. Separating two signals with a power or ground line acting as shield, that might be a method. Use minimum wire width wherever possible, which in turn will increase the resistance. R equal to rho L by A. So in denominator there is A. A means height into width. So if width they are decreasing, so R value will be increased and then the ohmic effects will be higher. So we have to choose between these two. It's a trade-off. Now let's move to the next slide. Now crosstalk. It occurs due to unwanted coupling from neighboring signal wire to a network node. The resulting disturbance acts as noise source. It's not desired. Here unwanted voltage interference is basically noise. Capacitive crosstalk is the dominant effect at current switching speed. Potential impact of capacitive crosstalk is influenced by impedance of the line under examination. The design functionality and its performance can be limited by noise. The noise impact can limit the frequency of operation of design and it can cause functional failures. Crosstalk may lead to setup or hold violation. Setup or hold violation, basically two major timing violation taken care in backend timing. Then propagation delay. Capacitive crosstalk may result in data-dependent variation of propagation delay. Coupling capacitance is a large function of overall capacitance in the dense wire structure of advanced technology node. This increase in capacitance is substantial and has a major impact on propagation delay of the circuit. Inductance and reliability. Inductance with LDIdt voltage drop. During each switching action, a transient current is sourced from or sunk into the supply rails to charge or discharge the circuit capacitances. In our basic circuit analysis, we have studied that the transient effect happens during the switching. Here also, transistors or MOSFETs are basically used at switch. So when signal switches from 0 to 1 or 1 to 0, transient current is sourced from a sunk into the supply rails to charge or discharge the circuit capacitances. So with that transient current actually either charge or discharge the circuit capacitances. Both VDD and VSS connections are routed to the external supplies through bonding wires and package pins and possesses a non-ignorable series inductance. That bonding wires, VDD and VSS, finally they are connected to bonding wires. They are supplied from outside. Change in transient current leads to large current surges. That's not negligible. And then transmission line effects. When an interconnect becomes sufficiently long or when the circuits become sufficiently fast, the inductance of wire starts to dominate delay behavior and transmission line effects become significant. So actually the change of current, rate of change of current, that is getting resisted by the parasitics, and that is become very crucial when the wire becomes sufficiently long. So if long, it takes a longer time, so effect will be more. Now, impact of scaling. Scaling is basically downsizing the device dimension. We have followed Moore's law and downsized the device dimension or MOSFET dimension and packed more devices into the same area. But that has impact on interconnects also. Here we will, in this slide, we will discuss that. Dimension of interconnect scale down by a factor calling scaling factor. It's not abruptly changed. It's changed with a factor that is called scaling factor S. And this scaling factor is an integer. The resistance, capacitance and inductance are affected by scaling because all are function of that length, height and width. Wires, there are two types of wires, short and long. Short wires are typically used for local communication between gates, local interconnects, and long wires are used for long range communication at the different corners of IC. There is a table for full level scaling, short wires and long wires, and R value change with a factor of 1 by S, scaling factor. And long wires, it's 1 by S square. For C, for short wires, it's S, and long wires, it's scaled by factor 1. That's same, remains same. RC delay, these are the values. And scaling with thickness, keeping thickness constant, the value will be different. So we can see that with scaling, the value get changed. So if we compare this RC value, RC delay value over two different technology nodes, they will be different. So that's the impact of scaling. So that we all had for today's episode. We will discuss delay models and their calculations in a later episode. Now let's take a look at the pointers we are going to discuss in today's episode. First, delay in IC. Second, delay models. Then lumped C model. Then lumped RC model. Next, pi and T models. Next, L mode delay model. Then RC tree network with L mode delay, RC chain with L mode delay model, distributed RC line model, transmission line model, and lossless transmission line model. So let's move to the first slide. Delay in IC. Input to output delay in IC has two components, gate and interconnect delay. In previous episode, we have discussed about delays, that when signal is applied at the input of the IC, it takes some finite time to get the desired output, expected desired output at the output pin of the IC. So that is the delay, input to output delay for an IC. And this delay in IC has two components, one due to gate or cell, and another component of this delay is contributed by interconnect. We call it interconnect or wire delay. First, gate delay. Signal transmission through a gate is not instantaneous. That even signal transmission, this is a NOT gate, input of this NOT gate, and get the desired output, we don't get that instantaneously. It takes finite time shift. When this 1 to 0 transition is happening, the desired output should be 0 to 1 transition, and we get it, although after some time delay. That is gate delay. The time required for signal to travel from input of the gate to output of the gate is gate delay or propagation delay. We also call it propagation delay. The figure shows gate or propagation delay of a NOT gate. Output changes after a delay of delta with change in input. As we can see, gate delay is not equal for high to low and low to high transition. This high to low or low to high transition, the delay is not exactly same. We will discuss it in some later episode. Today, we will mostly concentrate on wire delay or interconnect delay. Now, let's move to wire delay. So wear delay interconnects or wires connecting active devices at delay while carrying signal. This is wear delay. So between two gates, there is gate 1 and there is gate 2. They are connected by wire. So when signal is applied here, we get desired output, but the desired output will not reflect or will not reach from this point to that point instantaneously. We know why. Because of interconnects add delay because of their parasitic effects. So there is a finite time, and that finite time is denoted by this delta, that is the wear delay. Wear delay is also known as transport or flight delay. Wear delay becomes dominating with higher operating frequency, that is lower device dimension. Now that is a table. In mid-80s, gate delay was 85% and 50% of the total delay was contributed by wear delay. While we have moved to more small devices in mid-90s, the ratio became 50-50. Now post-millennium, the situation has worsened so much that gate delay or cell delay only contributes 20% of the whole delay, whereas 80% comes from these wear delay. So although we have today discussed this gate delay, what is gate delay and wear delay, we will mostly concentrate our today's episode on wear delay. So let's move to the next slide. Delay models. We have already discussed about cell or gate delay and wear or interconnect delay. So let's know the name of the delay models. NLDM, ECS and CCS. These are delay models for gate or cell delay. And for wear or interconnect delay, we use lumped C model, lumped RC model, distributed RC model, transmission line model, wear load model. Now NLDM is nonlinear delay model, ECS is effective current source model, CCS is composite current source model. These all delay models and their data all are mentioned, usually get mentioned in leaf file. We have episodes on characterization. Link is provided in the description. Watch the episode. You will get better and clearer idea about all these models. So since today's episode is concentrated on wear or interconnect delay, it's just what I'm doing is just touch base for these names and all, but actually we will discuss in detail about these models. RC network and gate delay modeling. RC circuits are frequently used to model the timing characteristics of ICs. Here also we will talk a little bit about gate delay modeling because of this RC network. Why RC network? In coming few slides we will discuss in detail about RC network and delay modeling. So here we are just giving you an idea why RC network. In gate delay modeling also we use RC network. RC circuits are frequently used to model timing characteristics of ICs. When one logic gate drives another gate, the input circuit of the second gate can be modeled as an RC load. For electrical modeling, we do the approximation of the active devices as passive device and then do the calculation. The propagation delay through the first gate is calculated by assuming V in as ideal square wave and the RC load. These models, we just try to be as close as possible to the real-time scenario. This works really well for EDA tool and design purpose. Gate delay is inversely proportional to the switching speed of the gate. So obviously, if delay is high, or it will take a lot of time. If delay is less, though, the gate will switch quickly. Next, RC network and wear delay modeling. A wear can be modeled as many cascaded sections of simple RC circuits. When a square wave is applied to one end of the bus, it takes time to propagate. This delay time due to wear can be calculated based on value of R and C in each section and number of sections used to model the wear. The longer the wear, the more sections are needed for accurate model. Now, why RC network is important? It gives us a good approximation of a long wear. A wear can be modeled as a many cascaded section. So first, what actually we do, we take a smaller model of RC and keep on repeating that thing again and again and again. When square wave is applied to one end of the bus, it takes time to propagate because of delay. Obviously, the delay time due to wear can be calculated based on values of R and C in each section. So we break it in smaller section and calculate and then do the summation. We will see it later. The process, this is the basic process. And the number of sections used to model the wear. So if the number of sections of such RC basic structure sections are more, the result will be bigger. number, so delay will be more. The longer the wear, the more sections are needed for accurate model. Now wear load model, we said that wear load model is used to estimate delay based on area and fan out. Semiconductor vendors develop wear load models used in pre-layout design cycle. So here we will not consider wear load model in our discussion in detail. Whatever timing model and estimation we are discussing today, this is completely for post layout design cycle, that is PD. Wear load model we will discuss in some other episode because that is not part of physical design. So let's move to the next slide. Now lumped C model. Circuit parasitics of a wear are distributed along its length and are not lumped into a single position. So at every point when a signal travels from one point to other, it faces effect of parasitic at each point. Although for our ease of work, we adopt some model. One of them is lumped C model. Although we know that is the parasitic is not lumped into a single position, but still we follow such rule for ease of calculation. Lumped model is considered in a circuit where single parasitic component is dominant. If a single parasitic is dominant, in many cases in maths we do it keeping one parameter, tending it to 0. So we keep one parameter off there so that the calculations become easier. Interaction between the components is small. And third, one aspect of the circuit behavior is considered. We are considering single parasitic component is dominant, others are not. Interaction between components is small. One aspect of the circuit. So when which one is predominant, we will consider that one and accordingly we will model. This is the driver. This is V out, and that happens on the higher node, more matured node. Capacitive action is more predominant compared to the resistive parasitic. So there we can approximate that there is no resistance, only capacitive actions are there, that is modeled by some capacitance. So this is the driver and this is the V out. So that scenario is modeled as this is the signal. Then when it's on, we consider it as a resistor, and altogether all capacitance are lumped, their values are lumped into one, and that is the V out. This is the easiest or the simplistic model. Effects of parasitic can be described by an ordinary differential equation. That's one point. If parasitic R is negligible and circuit is operating in low to medium range, only capacitive component is considered. Distributed capacitance lumped into single capacitor. There is a condition that it's operating in low to medium range, and resistance is negligible if the technology node is on the matured side. That is lumped C model, suited well for older technology node where wires were wide. High cross-sectional area, A means less R. So resistance is not that dominant. In this model, where is equipotential region and where does not introduce any delay due to resistance. Impact on performance is introduced by loading effect of the capacitor on the driving gate. This capacitive lump model is simple and effective. Model of choice for analysis of most interconnect wires in older techno. For older technology nodes or matured old technology nodes, this is the most choiceable model. Now let's move to the next slide. Lumped RC model. Lumped RC model is used when wear length L is greater than few millimeter and resistive component is considerable. With scaling, where cross section is reduced and R become considerable. Lumped C model is inadequate because the assumption for lumped C model was that R is less. If R is increasing, then R is also becoming a considerable and dominant factor. So we cannot use lumped C model there. Now interconnect is modeled with resistive, capacitive or RC model. Multiple approaches are there depending on complexity and operating condition of the circuit and verified with accuracy of the result. For lumped RC model, there are multiple approaches depending on the complexity and operating condition. And now lumped RC model, the total resistance of each wire segment is lumped into one single R and global capacitive is combined into single capacitor C. Within driver and receiver, this is the model. Total resistance of each wire segment is lumped lumped into one single R, and global capacitance is combined into single capacitor C. Again, approximation, although they work really well, this model is pessimistic and inaccurate for long interconnect wires, which are more accurately represented by distributed RC model. If its interconnect wires are really long, then more accurate model is presented by distributed RC model. So next slide, RC networks. Studying lumped RC network is important as the distributed RC model is complex and no closed form solution exists. Distributed RC model is a better approximation, although they don't have any closed solution and solving is complex. The behavior of the distributed RC line can be adequately modeled by a simple RC network. So when the model is accurate, although solving it as a complex situation, we go for another approximation. So we approximate it as simple RC network and then try to find the solution. A common practice in the study of the transient behavior of complex transistor wire network is to reduce the circuit to an RC network. We reduce them to a simple RC network. Analyzing such a network effectively and to predict its first order response is important for designers. We try to keep the answers simple. So we try to predict the first order response of the system. Two popular network are tree network and RC chain or ladder network. This is the tree network. This one. This is S or input node. From there, at each node, they are grounded by a capacitor. And this is a ladder or chain structure. These two networks are popularly used in modeling. Now let's move to the next slide. Pi and T models. The distributed RC delay can be modeled by breaking up a wire into one or more segments and using lumped model for each segment. Getting solution to distributed RC delay model is complex and tough, so we approximate it by simpler form of RC network. What we do that we break up a wire into one or more segment and using lumped model for each segment. Next, popular lumped models are Pi and T models, named obviously after their shape. There is another model, L model, which is not really good approximation. That's why we have not included it here. R and C depend on length of the segment. We are breaking the wire in smaller segment, and for each segment we are applying that lumped RC. So resistance and capacitance of that segment is lumped into single R and single C, and then it become a network of series of R and C. So value of R and C depend on length of the segment. More the segment value keep on adding. Pi and T model are both good models, although Pi model is slightly more convenient because of fewer circuit nodes. Most circuit simulators have built-in distributed RC model of high accuracy. So these models are, everything is included in circuit simulators. The Pi model, Pi 2 model, Pi 3 model, as we can see, T, T2, T3 model, these are models, popular models. So let's move to the next slide. L-mode delay model. L-mode delay model is derived originally in 40s for circuit applications and applied in 80s for RC trees. L-mode defined delay through linear network as the first moment of network impulse response. It gives the first order solution. The L-mode delay formulas are immensely useful and simple model, easy to use model. Layout people use in algorithms single time constant. The solution we get is basically single time constant solution and more accurate compared to simple length based scheme. Although it's not super accurate, it requires some later verification with higher order model that incorporate more than one time constant. Simple RC model provides general approximation of timing behavior of digital integrated circuits. L-mode delay model is used in order to improve accuracy of RC model. So RC model provides general approximation of timing behavior of a digital IC. L-mode delay model is used to improve the accuracy. We need to be closer, as much as closer possible to the real-time scenario. Here the RC segments made up of series resistance Rn and capacitance Cn are created. Think of current like real water flowing in tree. This is current in, this branching out. It's a tree-like structure, main branch, then smaller branch, then going towards leaf. From any component of tree looking at the source, it's upstream, and look towards leaves, it's downstream. So next, RC tree network with L-mode delay. Now we will apply L-mode delay on RC tree network to get the result. Wire branching into many destination modeled as RC tree. A wire branching into many destination like this, we model it with RC tree. It's a tree of resistors obviously. Root of the tree is at source node S, where input signal is applied. There is no loop. At the branch end, output is measured. Each intermediate node is grounded with a capacitor. As we can see, there exists a unique resistive path between the source nodes and any node I of the network. There is an unique resistive path between any node and the source node. Like S and 2, the path is this. S and 3, path is this. S and 4, R1, R3, R4. And to I, R1, R3, Ri. This is the path. The total resistance along this path is called the path resistance, Rii. The path resistance between the source node and node 4 is expressed as R4. So this is the node 4. So what would be the path resistance? When signal will travel from this point source node to this node 4, they will travel through R1, R3 and R4. The path resistance of the shared path can be expressed as resistance Rik. There are shared path resistance is calculated by a formula that summation of Rj, where K is from 1 to N. Basically, the expression is like this is the expression, and this is effective resistance between the input and node K in common with path between the input and node I. If we want to calculate shared path resistance between two different node K and I, that would be, we have to take effective resistance between the input and node K, 1, and effective resistance between input and path I. And we have to take common of these two. Like this. Rj belongs to path S to I, intersection path S to K. Not union, intersection. I hope we all remember the set theory. If that is a set and that is a set, this is the intersection. A common point. So using above formula, Ri4 is R1 plus R3. How it is happening? So Rs to Ri is R1, R3, Ri. And S to 4 is R1, R3, R4. So common part is R1, R3. That is the shared resistance of these two nodes, 4 and I. Similarly, 2 and I, it's the common resistance is R1. So this is the Ri2 equal to R1. The Elmore delay from source to node I of an RC tree is given by summation of Rki and Ck. Ck capacitor on node K and Rki shared resistance between node K and I. So first calculate this Rki calculated. Now this Elmore delay model for network is R1 C1, R1 C2, R1 plus R3 C4, R1 R3 Ri Ci. This way it goes. So let's move to the next slide. RC chain with Elmore delay model. It's a special case of RC tree network, non-branched RC chain or ladder. In digital circuits, similar structure is found, represents an approximate model of a resistive capacitive where the delay component of node 1 is C1 R1. R1 is the total resistance between node 1 and the source. Node 1 and source, this is the total resistance. And C1 and R1. Then node 2, R1 plus R2. And delay is summation of capacitance I into resistance from source to capacitance I. So if that is the ith capacitance and the ith node, so R1 C1, R1 R2 C2, this way it goes, and that R1 R2 R3, then Ri C1, this way. This gives the right answer for all values of C and R unless these both have equal to 0. Its only equation is that is correct in all the limits. Now let's move to the next slide. Distributed RC line model. Distributed RC line model is more appropriate model. R and C stand for resistance and capacitance per unit length. We know that parasitics are distributed across length. Here the resistance and capacitance are per unit length. The voltage at node I of this network can be determined by solving partial differential equations. C delta L del Vi del T equal to Vi plus minus Vi plus Vi minus 1 minus Vi divided by R del L. By reducing delta L asymptotically to 0, we will assume that delta L tends to 0, and then we will get that RC del V del T is equal to del square V del X2, where V is the voltage at a particular point in the wire and X is the distance between this point and the signal source. These equations are difficult to use for ordinary circuit analysis. The distributed RC line line can be approximated by a lumped RC ladder network, which can be easily used in computer-aided analysis. So again, we are taking different approximations, like first delta L will tend to 0, and then it will become a function of RC, and we will try to approximate it by a lumped RC ladder network because it's easier to solve and then use in computer-aided analysis. Let's move to the next slide. Now, transmission line model. Inductance is also there. The inductance is distributed over the wire like R and C. A distributed RLC model of wire known as transmission line model becomes most accurate approximation of the actual behavior. In transmission line model, a signal propagates in the interconnection medium as a wave. In the distributed RC model, where the signal diffuses from the source to the destination governed by the diffusion equation. In the wave model, a signal propagates by alternatively transferring energy from electric to the magnetic fields or equivalently from capacitive to inductive modes. So, when we consider RLC, R, L and C, it's a transmission line model. We are considering a point X along the transmission line, as the figure is showing here. At time t, the following set of equation holds. These two equations we get two partial equation, del V del X equal to minus IR minus L del I del T, and del I del X equal to minus GV minus C del V del T. Assuming that leakage conductance G equals to 0, which is true for most insulating material, and eliminating the current I yields the equation. It's reduced to this equation where R, C and L are the resistance, capacitance and inductance per unit length respectively. This transmission model has more parameters and more complex. Let's move to the next slide. Now, lossless transmission line. For the lossless transmission line, R is 0 and the previous equation simplifies to ideal wave equation. So, R component is also 0. So, that is reducing to this equation, and if we apply step input, so that propagates with speed v, which gives a solution of this L and C. Values of both L and C depend on the geometric shape of the wire. Their product is constant and is only a function of surrounding media. The propagation delay per unit wire length of transmission line is the inverse of the speed. So this is the equations for lossless transmission line. Today we will conclude here. So that we all had for today's episode, and today we concentrated only on the delay models for interconnects. We have not included cell delay here. That's altogether a different discussion, and we will cover it in some other episode. So let's take a look at the pointers we are going to discuss in today's episode. First, how on-chip inductance becomes significant. Second, interconnect model mapping with technology node, loop and partial inductance, transmission line model, a small recap, dependence of impedance on frequency, impact of on-chip inductance, first, second and third slide, then difficulties with inductance, then techniques to minimize on-chip inductance, first 2 slides, then techniques to minimize on-chip inductance, more 2 slides, and significance of termination, and finally modeling of interconnect at high frequencies. Now let's move to the first slide, how on-chip inductance becomes significant. On-chip inductance effects have become increasingly significant because some global signal and clock wire have large widths and thicknesses at the top level of metal to minimize delays. To minimize the delay, some top level metal layers like global signal and clock wires, their widths and thicknesses are kept wide. They have larger widths and thicknesses, so these decrease the resistance of the wires, making their inductive impedance comparable to the resistive part. Now, impedance of metal interconnect is expressed with Z equal to R plus J omega L. If resistive part is less and at increasing frequency, this part is comparable to R. So, when one part of impedance is comparable to the other part, we have to consider the both. We cannot any longer ignore this part. Next, as the clock frequency increases and the rise time decreases, electrical signals comprise more and more high frequency components. components, making the inductance effects more significant. Clock frequency increasing and electrical signals, they are comprised of more high frequency components, and from this first point, this frequency portion is increasing, so inductance part is increasing, so we cannot ignore inductance effects anymore. And this is a table. It's showing over the years how frequency has increased from 1.25 gigahertz in 1999 to 13.5 gigahertz in 2014. Signal transition times become more shorter comparable to the signal time of flight, and devices become faster. So speed has increased, devices become more, their dimensions have become smaller, their switching speed has increased, so devices became faster and signal transition is becoming faster. With the increase of chip size, it's fairly typical that many were long and run in parallel, which increases the inductive crosstalk and delay. Just look at our smart devices, our consumer electronics. Our device is as smart as much its processor or their processing unit is smart. So we want more and more complex operation in our devices or in our consumer electronic devices. So just to cope up with that, the chips are increasing in size and they are accommodating more and more devices into the same chip. So what is actually happening? The wires or interconnects, they are connecting. There are many operating blocks are there on the same design, same system, and they are connected for complex operation. So wires are running for longer length and they are running in parallel. So that increases the inductive crosstalk and delay. And with the push of performance, some low resistivity metals like copper, they have replaced aluminum in order to minimize the RC delays. That increases inductive effect more because resistance becoming less. So this portion is again becoming more significant compared to R. So that's a point. Now let's move to the next slide. Interconnect model mapping with tech nodes. There is a diagram. It's showing two pieces of interconnects, and just to remind us that an interconnect is not just a piece of interconnect or piece of metal, it's basically capacitor, resistor and inductor. So this is the model for the first piece of interconnect, and this is the C2, R2, L2 for the second piece of interconnect, and they are moving parallel. There is a mutual capacitance and there is mutual inductance. What we are saying, so this is the scenario. And if for interconnect models, look, the technology node is moving towards smaller size. Resistance was initially ignored, then lumped, then distributed, and finally it's distributed. And capacitance models also consideration also is changing from area capacitance to area and 2D fringing, then 2/3 dimension fringing, then lateral coupling. And now when it's less than 25 micron, its lateral coupling is dominant. And inductance, first up to this it was ignored and now it's become important. And circuit model lumped C, lumped RC, distributed RC and distributed RLC. These are the circuit symbols. So we are done with this slide and let's move to the next slide. Loop and partial inductance. So loop inductance is defined as the induced magnetic field in the loop by the unit current in other loop. This is a loop, J loop. Current Ij is flowing. So this flow of current in this J loop is inducing a magnetic flux in this I loop where I current is flowing. So L, that is induced loop inductance from one loop to another. It's a loop. So magnetic flux is induced from one loop to another. This is the loop inductance where psi Ij represents the magnetic flux in loop I due to current Ij in loop J. Now problem with loop inductance. Calculation of loop inductance require knowledge of return paths. When we are considering loop inductance, we need to know the return path because it's a loop. As long as we do not know the return path, the loop is not closed. Calculation of loop inductance is incomplete. It's really difficult to determine return path for on-chip interconnects explicitly since there is no ground plane. So it's calculating this one is return path calculation is tough. Almost everywhere coupled to many wires and there are multiple return paths. Because it's a complex 3D geometry on the level of interconnect. So many interconnects running parallel, up, down, both sides. So it's a
complex 3D geometry of interconnects. So determining a single return path is difficult. Almost everywhere is coupled to many wires, and we will see that this inductance property is basically it's a long range effect. For capacitance, we can consider the nearby elements, but for inductance, the effect decreases very slowly with distance. So almost everywhere coupled with many wires. So there is a complex 3D geometry, and at that situation, confirming a return path is difficult. So what we do, we take partial inductance in consideration. What is that? It was proposed by A. Rueli, the partial element equivalent circuit method, PEC method. This is based on partial inductance. Partial inductance is the portion of loop inductance for a segment when its current returns via infinity. So it calculates based on that the return path is infinity. It returns from infinity. It can be directly applicable to circuit simulator like SPICE, because ultimately we need to use them in tools. All these mathematical calculations and everything, we don't, with this complex geometry and tight time to market, we cannot do all these complex calculation by hand. So tools have to do it. So this is the model. We will talk about it later. And now properties of partial inductance. Partial self and mutual inductance are based on geometry only. They may be solved by using 2D and 3D field solver. 2D and 3D field solver are basically, they calculate that Maxwell's equation. They solve Maxwell equation. The return path of the current loop may be determined through SPICE simulations. The partial self and mutual inductance may be frequency and proximity dependent. These are the properties of partial inductance. So we are done with this slide, and let's move to the next slide. TL model, a recap. We have discussed about transmission line model in last episode. It's just a small recap, because after that we will talk about termination of transmission line. Inductance also distributed over the wire like R and C, and the transmission line model is at high frequency and state of art devices. It's a almost most accurate approximation, and signal propagates as a wave. These are the equations, and for insulating material, leakage conductance G is 0. So wave equation, that finally we get this equation where R, C, L, everything is per unit length, because it's distributed per unit length value. And for lossless transmission line, R equal to 0, that is resistance 0 with step input, propagates with a speed root over 1 by LC. So from there we get delay per unit length EP. This is the LC. It's just a small recap. We have discussed it in detail in last episode. And this is the wave form. This is the input waveform, and transmission line, this is lossless transmission line, and this is lossy transmission line. Just a time shift. If there is lossless transmission line, not any part of the input signal is lost, almost transmitted like as it is. Although for lossless, its shape is changed. Some portion of the signal is lost. So we are done with this slide, and now we will move to the next slide. Dependence of impedance on frequency. In a circuit with multiple current paths, the distribution of the current flow is frequency dependent. When a circuit have multiple current paths, distribution of the current flow become frequency dependent. How? At low frequency, current path is determined by resistance of the path. At high frequency, current path is determined by the inductance of the path. Low frequency, where we have that Z equal to R plus J omega L. At low frequency, this part is very small. R is much greater than Z. So, in forward current is going when return path is dependent like this, that low R, low resistance path, most of the current return through low resistance path, and a small portion of it returns through high resistance path. Although what happens at high frequency is completely different. For high frequency, R is much less than J omega L. So, for return current, it's like most of the current return to a low inductive path, and smaller part of the current returns with low resistance and high inductive part. And these are the current distribution equation. At low frequency, the equation is governed by R2 because this portion is negligible, and at high frequency, the equation is governed by L value because this portion is considerable and this is negligible. So this effect is primary source of inductance variation with frequency in integrated circuits. So now let's move to the next slide. Impact of on-chip inductance. So any current passing through a conductor creates a magnetic field. This magnetic field then induces a parasitic current either on the same metal, that is self-inductance, or on another metal crossing the magnetic field, that is mutual inductance. And if we focus on the resistance and inductance, we can express interconnect impedances and just see impedance. Omega L part is increasing like that and R is increasing like that with frequency. And now skin effect. It's a high frequency phenomena. As frequency increases, the current tends to flow closer to the conductor surface or skin, between the outer surface and a level called skin depth. At low frequency, it's homogeneous. At high frequency, no more homogeneous. It flows between outer surface and a length called skin depth. So skin depth is defined as the depth where the current density is just 1 by E, that is about 37% of the value at the surface. So from surface, the current density is decreasing, and when at each depth it becomes 1 by E, that is 37% of value at this surface, this is called the skin depth. And just look at this graph, skin depth is decreasing with frequency. That means more the frequency increasing, the skin depth is decreasing. So more and more current is concentrated towards the surface. Skin effect increases the resistance parasitics of a conductor at high frequency. They also lead to frequency dependent value for the effective inductance and resistance seen by the current. Such effects must be included in the parasitic extraction to achieve accurate results. So skin effect not only increasing the resistance parasitics of a conductor, also changing the effective inductance and resistance seen by the current. Here we are done with this slide, and let's move to the next slide. Impact of on-chip inductance. Now proximity effect. So when two or more conductors carrying AC are close to each other, then distribution of current in each conductor is affected due to varying magnetic field of each other. The varying magnetic field produced by AC induced eddy currents in the adjacent conductor. When the nearby, this is important, when the nearby conductors carrying current in the same direction, the current is concentrated at the farthest side of the conductor. When current, these are two conductors adjacent to each other, current is flowing in the same direction, so current concentrated towards the farthest. When the nearby conductors are carrying current in opposite direction to each other, the current is concentrated at the nearest part of conductors. This effect is called proximity effect. So opposite direction, current is, suppose it's flowing this direction, it's coming this direction. So these are the close, concentrated at the nearest. So this side, close to each other. Current is flowing in opposite direction, current is concentrated here in the nearest part, and when it's in the current flowing in both the conductors in the same direction, the current is concentrated on the farthest side. This is proximity effect. The proximity effect also increases with increase in frequency, and effective resistance of the conductor is increased due to proximity effect. So we are done with this slide. Now we are moving to the next slide. Difficulties with inductance. First is it depends on frequency. Second, inductance of wire requires knowledge of return path with this complex geometry. The VSS or VDD closes loop for each piece of interconnection. The return path is decided by signal pattern and interconnect geometry for a large range. Often a return path is not easily identified, particularly at layout stage. It's not necessarily through the silicon substrate. And silicon substrate cannot be considered as ground plane, as the resistivity of the doped substrate layer is very high compared to the metal, and the substrate is too far away from the high-speed buses or clock wire. If we take the cross section, so these are the top metal layers here, then at somewhere here it's the substrate. So basically from top level wires, substrate, this is quite far. This is one reason, and another is silicon substrate, although it's doped, lightly doped, still its resistivity is much higher compared to the metal. So it's not a very feasible solution. Mutual coupling between wires decreases very slowly. Magnetic fields die out at a far distance as compared to the electric fields. It's another problem because for capacitance, what we do that considering near neighbors which is enough for capacitance is not enough for inductance. We consider only near neighbors. Mutual inductive coupling between wires decreases very slowly. We have to consider that quite far wire also. Calculations become complex. Reason of concern for high frequency designs because it frequency dependent. Inductance is not scalable and inductance results in many high frequency poles and zeros, making reduced order model approximation difficult. We always make a trade-off between accuracy and time. We have to make it as much accurate possible and we have to complete it within time also. A very accurate, at the same time very complex methodology to solve it, to model it, is not always a very viable solution. And inductance in the equations or when we solve in the system equations, inductance results many high frequency poles and zeros. And while discussing about Elmore delay, we said that Elmore delay might not be a very good approximation, although it works really well because it's quite simplified and it gives us first order solutions. Presence of multiple poles and zeros make the situation tougher because reduced order model approximation become very tough. So inductance creates quite a difficult situation in modern ICs. Now let's move to the next slide. Minimizing on-chip inductance. Dedicated ground wires. Increase the mutual inductance by making the signal wire and its return path to be as close as possible. Decrease the self-inductance by increasing the width of return path or by adding one or more ground wire between signal wires. First, it gets a return path and it increases the mutual inductance and decrease the self-inductance. Next method is differential signaling. This method has high signal to noise ratio due to common mode noise rejection. However, requires double the number of signal paths as compared to single-ended transmission network. The transmitter at the near end of the network converts the single-ended signal into an opposite polarity differential signal, while the receiver at the far end of the transmission line converts the differential signal into a single-ended form. So first, this is the single-ended input. When the transmitter get it and transmit it transmit in the original one and change the polarity, transmit both. That's why we are talking about that it requires double number of signal paths. And at receiver, it again convert it and make it a single-ended input, although it has a benefit of high signal to noise ratio. Now let's move to the next slide. Splitting of wires. There are two ground. These are two ground path and this is signal wire. Splitting a wide wire into several n parallel wires of about 2 skin depths with each may reduce the total reactance by a factor of n. That's a method. Another method is continuous power or ground plane. When signal travels a long distance for a current return without planes nearby, that causes inductive coupling. So ground and VDD. Continuous power or ground plane greatly reduces the coupling because it's provide a return path. This impedance control low loss line, these are the multi-layer interconnect and this is substrate. These lines are closer to the interconnects. That is a viable solution. Now let's move to the next slide. Buffer insertion. With inserted buffers, inductive coupling decreases slightly faster than linear rate. Each segment becomes more RC line than RLC line because L per segment scales down at a rate faster than RLC. So we can insert buffers to reduce inductive coupling and that reduce inductive coupling slightly faster than a linear rate. Now shielding. Another method, shielding techniques are widely used to reduce capacitive and inductive coupling. Isolates an aggressor or noisy line from sensitive neighboring lines. Increases the noise tolerance of a sensitive line. The voltage of the shield line typically doesn't switch. By inserting a shield line between signal lines, changes in the effective interconnect capacitance is significantly reduced, resulting in less delay uncertainty. Inductive coupling and self-inductance can also be reduced by inserting shield lines since the shield line provides a nearby current return path. So here a signal line is on both sides shield line and between signal line, and here shield line is in between two signal line. So it actually reduces coupling and obviously the delay is decreased. Let's move to the next slide. Now termination. We said that we will discuss about transmission line termination. At this high frequency, obviously the wires behave as transmission line and the behavior of a transmission line is strongly influenced by termination of line. The termination determines how much of wave is reflected upon arrival at the wire end. it must be R. This is expressed by the reflection coefficient rho that determines the relationship between the voltages and currents of the incident and reflected waveforms. Rho equal to R minus Z0, R plus Z0, where R is termination resistance and Z0 is characteristic impedance. So if R equal to 0, if the transmission line is terminated with the characteristic impedance, rho becomes 0. That means no part of the incident wave is reflected back. That's a perfectly matched termination. And when R is much greater than characteristic impedance, rho becomes 1. So the circuit will behave like it's open circuit termination. The whole part of the wave is returned. So the total voltage waveform after reflection is twice the incident one. And if R is 0, that is short circuited. The total voltage waveform after reflection equals to 0. Rho becomes minus 1. The total voltage waveform after reflection becomes 0. These are 3 typical cases. Now let's move to the next slide. Significance of termination. To reduce the coupling noise at the inputs of victim receivers, different termination methods are used like shunt RC, series R and shunt C, series R termination and diode termination. There are different types of termination and each of them have their own advantages. Depending on the usage, we select them. And termination is really important to prevent ringing effect when signal or data traveling long path. Ringing is generated on the transitions of digital signals when a portion of the signal is reflected back down to the line due to a mismatch between the line impedance and terminating impedance. We know when it's perfectly matched, no part will be reflected back. If there is a mismatch, then obviously a part is reflect back. And if the mismatch, kind of a similar mismatch, is at the driving end, will re-reflect a further portion. Like here, if this is the input driver, it has a characteristic impedance. Driver also has an impedance, and if it's not matched, then again a part of it will get reflected back. This kept on happening. This creates the ringing effect, and look, it gives a oscillation kind of structure to the waveform. That's not desired one. The amplitude of the ringing depends on the degree of mismatch at either end of the line, while the frequency depends on the electrical length of the line. So how much it's mismatched depends on that amplitude of the ringing. So we are done with the slide. Now let's move to the next slide. Now finally, modeling of interconnect at high frequencies. So these are some models we use. At high frequencies, circuit dimensions become comparable to signal wavelengths, and it's not always possible to identify discrete parasitic element. There are some models used to extract parasitics at high frequencies. Field solver, we already mentioned it. Actually, field solver solves Maxwell's equation. Finite element method, moment method, boundary element method, finite difference time domain method, transmission line matrix, partial element equivalent circuit or PEEC method. These all are used. We already have mentioned about PEEC method. So these are standard methods used to solve this, and the EDA tools use different models inside them. So these are the basically models used to solve the equations and to get the parasitics at high frequencies. Today we will conclude here. Today we have discussed about on-chip inductance. So we will conclude here.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction. We will introduce you to the concept of the decap, that is the decoupling capacitor. Next, we will talk about the reason why the proper decoupling is necessary in a circuit. Next, we will talk about intrinsic and extrinsic decaps. Next, we will talk about the different positionings of decaps in a chip. That means the entire chip from the silicon up to its packaging. Next, we will talk about the on-chip decoupling capacitor that is used in your VLSI design. Next, we will talk about the decaps and the physical design process. That means where we use the decaps in the physical design. Next, we will talk about the decaps that are used in FPGA designs. Next, we will show you the simple architecture of a decap using a NMOS capacitor. So that's the menu for today. Without any further delay, let's begin. Introduction. A decoupling capacitor, that is decap, is a capacitor that is used to decouple one part of an electrical network, a circuit, from another. Basically, we are making a electrical isolation between the two parts of our electric circuit. both off-chip and on-chip decaps are used in VLSI, we will restrict our focus on the on-chip decaps in today's discussion. However, we will cover different type of decaps through a diagram in a later slide. As per our circuit theory, including the KCL and KVL, that is the Kirchhoff laws, if the voltage level of a device is fixed, the changing power demands are manifested as changing in the current. This is true for one single element, and this is true for a sea of elements that is connected in a VLSI circuit. When the current draw in a device changes, the power supply responds to that with the transient change, or it is called a transient response of a circuit. That means it is not instantaneous. It takes some time and follows some graph for the change based on what type of circuit element are there. Such noise caused by the circuit elements is generally shunted to the decap. So decap acts as a shunt, thus reducing the effect of the noise to the rest of the circuit. These decaps have to be manufactured into the chip, and their placement has to be decided at the design time. Hence, we are having this episode that in the design, the ASIC design or the FPGA design, when the decap are useful and where at what design stage we are inserting them and where. So we are complete with the introduction. Let's move on to the next slide. Why a proper decoupling is necessary in a circuit. Generally, here we are talking about a silicon chip. However, in a circuit perspective, let us understand why a decoupling is here necessary. For high performance, that is the high frequency digital ICs such as ASICs and FPGAs, the allowable tolerance for the supply is typically 5%. That means the VDD and VSS, if we allow the change, it should be there within 5% only. This includes the sum of the DC error, ripple and noise. So from your class book text, you know about the DC error and the ripple, and noise is something that you come across in the VLSI only. The noise is something you might be familiar with, the crosstalk noise. That means one line is carrying the current, another line is getting induced by the noise. And sometimes the circuit, if it is used in some, maybe in the space application, there will be cosmic noises. So generally the noise can come from anywhere that is within the circuit or from external sources. Altogether, it can impact the circuit performance. The digital device will meet specification if this voltage remains within the tolerance. That means 5% we have talked about. The tolerance will decide whether the digital operation, that is 1 or 0 operation, is proper of the digital circuit or the sub-circuit or the sub-chip, whatever we are analyzing. So it is necessary to keep high frequency noise from entering into the chip in the first place. For this reason, we have various type of decaps. This slide I will show you all the type. However, we will restrict our discussion to the on-chip decaps, that is which are used in the VLSI design, specifically in the ASICs and the FPGAs. This is generally done with a combination of electrolytic capacitor for low frequency decoupling, ceramic capacitor for high frequency decoupling, and possibly using ferrites. Now here, this point we just discussed is for the entire set of decap, not for the on-chip, there is the silicon decap. At the end of the slide, that means the last slide, we have the silicon decap. We will show how the structure is there and you will understand the basic structure of a NMOS decap. All the decoupling capacitor must connect directly to a low impedance ground plane in order to be effective. That means it should act as a shunt and it should pass the noise to the ground. That's how it prevents the tolerance to jump off the upper or lower ceiling. That means the plus or minus 5%. So here we are done talking about the reason where a proper decoupling is necessary for a circuit. Circuit means entire chip, not only the silicon wafer, but the entire chip or maybe the entire circuit that is being used in a particular device. This kind of decouplings will be there. So here we are done with this slide. Let's move on to the next slide. Here we will talk about intrinsic and extrinsic decaps. So intrinsic and extrinsic, you will come to know the meaning. These are not the internal and external decaps. These are not those. So you will understand the meaning as we proceed through this slide. Capacitors between the power and the ground networks are referred to as the decaps or decoupling capacitors. That means they decouple the power and the ground and shunts the noise. There are two types of decoupling capacitor found in a power delivery network, PDN. intrinsic decap. Parasitic capacitance between the metal interconnect of the supply lines, device capacitance, and the capacitance between the substrate and the end well are intrinsic decap. So these decaps are there while the chip is getting manufactured. That means we have not put extra decaps, that means the design decaps. These are intrinsic decap. The intrinsic decoupling capacitance is not sufficient to constrain the voltage drop within the prescribed safe limits. If we have talked about 5% plus minus 5%, these intrinsic decaps which are getting created during the fabrication are not sufficient to maintain the limit. So designers have to add explicit decaps on the die at supply points. This is here our design decaps enters into the picture. Extrinsic decap. The explicit decap that are added and occupy more area and consume more power in a chip. So this is the extrinsic decap. We will talk about this today. And this is, as a designer, you have to place to minimize the noise in the circuit. We are done here with this particular slide. Let's move on to the next slide. Positioning of the decaps in a chip. Here in this slide, we will talk about the entire chip, including the chip packaging, where all the decaps are there. So these are not all the standard cell design decaps. These are some other decaps also. This just to clear your overview and give a bird's eye view to the family of decaps that we generally have in a chip. So here goes our VDD line, that is the power line. And here goes our VSS line, that is the ground line. And here we have multiple components in the chip that are the motherboard, the socket, the package, P4 and die. So where all those decaps are there in the entire chip assembly, these are our bulk decaps. Next we have the motherboard decap. Next we have the package decap. Next we have the on die decap. So these are the entire set of decaps that are in a chip assembly. You don't have to be in a headache about all this type of decaps. You have to just focus. Today's discussion is on the silicon decaps that you use during your VLSI design, maybe in the front end or maybe in the back end, wherever it is applicable. So here we are done with this slide. Let's move on to the next slide. On-chip decoupling capacitor. So now we are zooming into our focus of the decoupling capacitors that are used in a VLSI design. Simplest form of decaps are generally the NMOS transistors. We build our decaps using the NMOS structure. The top plate is polysilicon, the bottom plate is inverted channel insulator, and the gate insulator is the gate oxide. To make the decap, you connect poly to the VDD and source drain to the VSS. Later, we will show the diagram in some other slide. Generally, standard cell libraries contain these necessary decap cells. These are pre-designed and available in your standard cell library. You have to pick and use during your design. And in case you are a standard cell designer, we have a later slide where we show the structure of this kind of decaps. Adding decoupling capacitors, that is decap, between the power network and the ground network is effective and widely adopted approach to reduce the power network impedance and therefore reduce the power network noise. So this is about the noise cleaning inside the silicon. The on-chip decoupling capacitor, their positioning during the VLSI design is all about reducing the noise that are created or coming into the chip in the entire set of the silicon. That means we are not talking about only the silicon. The silicon, that is the FUL layer, MEUL layer and BUL layer. In case you do not know about the three layers, we have a video on FUL, BUL and MEUL. The link is given in the description below. So go ahead and watch that so you will understand what I am talking about. We are done here talking about the on-chip decoupling capacitor, and let's move on to the next slide. Decaps and physical design. Optimization with decaps has two stages. The first stage is pre-place decaps before placing the standard cells. First, we have some decaps which we place in the design before even we place our standard cells. The second stage is a post-placement refinement to the existing floor plan in an incremental manner. And what is about this? In the post-placement refinement, decap placement is done to meet both the IR drop, also the power-related timing target. The decaps are also effective in IR drop violations because already we have talked about the IR drop and the ground bounce in two different episodes. The link is provided in the description below. In case you do not have the knowledge of them, please go ahead and watch the two episodes. So here, the post-placement things which is done during the physical verification, especially in the IR drop stage, there we place the necessary decaps. Next is when decaps placed far away from the noisy nodes, it leads to insufficient noise reduction. That means the noisy nodes have to be identified, and that is identified through various processes like airdrop analysis and other physical verification processes. An optimal placement of the decap has to be done in the standard cell based ASIC design for proper noise reduction. This is a tough job, obviously. However, the physical design engineer takes care of this. These are the challenges. Before you dip out your chip, you have to be over sanguine that proper decoupling has been done so that the noises are grounded. So here talking is done about the decaps and the physical design. Let's move on to the next slide. Now, FPGAs and decaps. We have talked about the ASIC design where we use the standard cells. Now, the question is the FPGA. How we deal with the decaps there? FPGAs have current consumption profile which is unknown at the design time. So FPGA is like that. We have a comparative episode on the FPGAs versus the ASIC design, that is our SoC design. So there you can go ahead and watch that episode in case you do not know the differences between the FPGA and the ASIC. You will clear your fundamentals there. The link of the video is given in the description. The mapped designs decides the current consumption profile of the chip at the configuration time. This is something we do in the FPGA. That means during the configuration time, we decide a lot of things. Hence, a large number of on-chip decaps are necessary to achieve robust power grid design in FPGA, catering to different designs mapped onto it. Because the FPGA is ready, then we implement the design onto it. Consequently, there will be more unused on-chip decaps in the part of the FPGA where a design is not mapped. Next, these unused decaps have leakage overheads associated with them, and the leakage power for the decap is expected to rise exponentially with the reduction of the oxide. Now here you see the differences of the decaps between the ASIC, which we have discussed in previous slide, and the FPGAs in this current slide. And you see there are some less decaps are there, ready decaps are there, and we have their benefits and we have their cons also. That means the pros and cons both that we have just discussed. So let's move on to the next slide. Coupling capacitor using NMOS. This slide is for the standard cell designers who want to have a look what is there inside a standard cell decap, the basic structure. However, nowadays the companies may make a advanced structure based on the technology downscaling, and those designs are proprietary to the company in which you are working. So those you will only see there, not here. This is here where you will get a general concept, the basic building block, and let us see what is the structure of a decap. A standard cell decap is usually made from the NMOS transistor in a CMOS process. And here is our structure. The gate of the NMOS transistor is connected to VDD. So you can see this is our NMOS transistor and this is our gate and this is connected to VDD. Generally this is poly, right? The poly is connected to VDD. The source and the drain and the substrate of the transistor are tied to PSS. So here you can see there is source, this drain, and here the substrate is there. All of them are tied together and that is connected to the VSS. This approach is considered effective because the thin oxide capacitance of the transistor gate provides a higher capacitance than any other oxide capacitance available in a standard CMOS fabric. So here we take advantage of the gate oxide as the dielectric of the capacitor of the decap. So you can view this is as a capacitor and this is getting placed, right? This acts as a capacitor and that is getting placed at different places as per your physical design need. That means whatever need is coming from the physical verification process. One we have talked about is the airdrop, and there might be some other things, maybe timings or maybe crosstalk noise analysis. Many things could be there. So from whatever analysis, the physical design analysis, you are getting the need of a decap, you place the decap there. And as a standard cell designer, you can have this basic structure designed as per your technology node. So the gate oxide here will be as per your technology node. The length of the channel will be for as the technology node. Everything will be as per your technology node. Even if you have a SY technology, so there will be some changes here, okay, in the structure that is there that you can explore once you are inside in a company where you are designing a standard cell, or you can use the standard cell as a ASIC designer in your physical design process. That time you will have some knowledge from the standard cell datasheet of the decaps, and there you can have a clear idea. So we have couple of episodes on the standard cell and their structure, and we have talked about a free PDK where you can go ahead and see the datasheets how are there. So all the links are provided in the video description. So here we are done with this particular slide. In today's episode, we will discuss about SPEF file. This file contains the details of the parasitics such as resistor, capacitor, and coupling capacitor due to the metal or via interconnection during the place and route stage. First, we discuss the introduction to the SPEF. Next, post-layout parasitics visualization, extraction, position in the ASIC design flow, SPEF and the entire design, various sections of a SPEF file, details of each section of a SPEF file with example. Overall, standard parasitic extraction format snippet. This is basically a short and sweet example of an entire SPEF. So we are done with this particular slide, so let's move on. Introduction to SPEF. Now, let us have a general introduction to the SPEF file. Standard Parasitic Exchange Format SPEF is an IEEE standard for representing parasitic data of wires or nets in a chip in ASCII format. That means it's a human readable format. Metal or via in routing have parasitic resistance, capacitance, coupling capacitance associated that are captured by SPEF. These nets also have inductance that is excluded in SPEF. SPEF is used for delay calculation, signal integrity check, crosstalk analysis, EMIR analysis of a chip, which eventually determines its speed of operation. This file cannot be hand created. So this is a very important point. We cannot write a SPEF file by our own hand. This file is created using industry standard extraction engine. This is very much important. In the design flow where we are placing the extraction, you will see that at what stage this extraction is done and how critical that stage is. So we cannot write the SPEF file by hand. So we are done with this particular slide, so let's move on. Post-layout parasitic visualization. In this slide, you are going to visualize the difference that the SPEF file makes on top of the actual design. In this slide, we will overlay the content of a SPEF file over our design. This slide is for educational explanation purpose. Hence, the circuit diagram are kept over simplified format so that you can grab the meaning quickly and easily. This is our pre-layout synthesized netlist. You can see that these are several logic gates and their interconnection. Now, this is the post-layout parasitic RC annotated netlist. Can you spot the difference? Yes. This and this. These are parasitic resistors which are contributed by the SPEF file. Now you can see that the number of nodes have increased in the circuit. This increment is due to the addition of the parasitics. For simplicity of the diagram, we have not shown the parasitic capacitors. The added nodes are often called subnodes because these expands the existing node into many more new nodes. Another avatar of the SPEF file is SBPF, which is binary file and hence cannot be read by human being. This is for the STA tool consumption only. For very large design, SBPF is useful because of its faster loading time. Now, one thing I would like to say before concluding, this annotation is done by some of the EDA tools. The SPEF file contains the information of these additional parasitic R and Cs. Those are highlighted in this diagram. So we are done with this particular slide. So let's move on. Extraction ASIC design flow. Since already I have mentioned that the SPEF file cannot be hand created, you must know at which stage of the VLSI ASIC design the SPEF file is generated. I will describe the ASIC flow and point out the stage where the SPEF file is generated. This will make things clear for you into your mind. Here we start. First, we have the design specification, and in this direction the flow is going forward. Next, we have the RTL coding, which you know, that is HDL coding. Next comes the verification. Next comes the synthesis stage. Next to it, we are entering into the backend stage, that is power routing, and sometimes there could be a pre-layout ACA just between these synthesis and power routing. Next comes the global placement. Next to it comes the detailed placement. Next we have the clock tree synthesis. We have covered this column, so we'll move on to the right hand side. The next is global and detailed routing. We will proceed in the upward direction now. The next is layout generation or changes. Next to it, we do the DRC and LBS of the generated layout. Next, we have the parasitic extraction, that is PEX. At this stage, we extract the SPEF file. Next, we have the static timing analysis, that is post-layout static timing analysis. Next, we go for the EM and IR verification or EM/IR analysis. Next, we do the AEC and final tape-out checks. And finally, the design is ready for tape-out. So folks, you have noticed that, let me bring my mouse pointer here. So these are the front end stage, and here it is entering the back end, and after so many steps comes the parasitic extraction stage. Here we extract the SPEF file. So it is so many level down. So at this stage it is very critical, because now you have all the previous steps done, and sometimes each of these steps may iterate one more time because to eliminate the errors. So multiple times these steps can iterate and or reiterate, and finally when we come up to this stage, we have consumed a huge time. So at this stage we extract the parasitic extraction. So at this stage, this is very crucial design turnaround time, and at this stage we extract the SPEF. This guides you one more thing, that the SPEF, if we try to hand create, we cannot, because there are a lot of dependency here, so many steps before this, so we cannot create it by hand. Whatever we create by hand is at the very beginning, when we are at here, okay, something at this stage, maybe in front end something we can hand create, but after crossing so many steps, we cannot do anything by hand creation. Everything has to be as per the design flow and through the proper tools, that is EDA tools. So guys, we are done with this particular slide, so let's move on. SPEF and the entire design. You may wonder that we have taken care of the parasitics of the metal via interconnection through SPEFs. An obvious question comes, what is about the interconnection inside each standard cells? Here goes our diagram. As you can see that the standard cells are interconnected by nets. The PEX file, that is SPEF file for net, is called PEF. Similarly, the PEX file for the cells are extracted in DSPF format. These are used during the standard cell characterization to calculate the internal delay. The delay and timing data for these cells are captured in the timing library file, that is .lib file. We have covered this file in detail in one of the previous episodes of this series. I'll provide the link in the description. So guys, if I bring my mouse pointer here, all these nets which are interconnecting the standard cells in the design, they will go to the SPEF. So when they go to the SPEF, each net will have its R and C, the parasitic R and C, all those data will go to SPEF. And the design have the standard cells, all those cells have their respective DSPF file where they have their parasitic data. But whenever we use the static timing analysis, we are concerned about these nets, because these cells have already characterized and their data for timing is already captured in the .lib file. So we are done with this particular slide, so let's move on. Various sections of a SPEF file. The SPEF file is a very large file with huge amount of data. However, it is divided into 4 distinct sections for clear interpretation of the huge amount of data. Here are the 4 sections. The first section is a header. The next section is name map. The next section to it is the port section. And finally, we contain all the parasitic information of resistor, capacitor and coupling capacitor in the RCCC section. In upcoming slides, we will describe each of these sections with definition and example. We will append one more optional section called layer map in the last slide of this video. The purpose of this slide is to imprint the 4 sections before we plunge into the detail. We are done with this particular slide, so let's move on. Header section. As the name suggests, this section resides at the top of the SPEF file. However, we do not have a footer section in SPEF file. Header section is a kind of identity card of the SPEF file. Let us see in detail. The header section contains information about design name, the parasitic extraction engine name, naming convention, and units. So let us see the thing with an example. First, it goes the first line of the header, that is SPEF, and it gives the IEEE version. Next goes the design name. Here it is XA5017. By the way, all these data are imaginary data. These are not from any actual data or design. So date is something here, the date on which this file was generated. Vendor is ABC Imaginary Corporation. Program is the parasitic generator. Here the name of the parasitic extraction engine will come. Version 0.0. Design flow netlist type Verilog. This has a specific data of values. You can consult the respective extraction engines manual for this particular field. Next comes the divider. Divider means it's a hierarchy separator. If the design is a hierarchical design, the text will be separated for each hierarchy with this particular delimiter. Next comes the delimiter. That is a usual text delimiter. Bus delimiter is the rectangular brackets. Time unit is 1 picosecond. Capacitor unit is 1 femtofarad. Resistance unit is 1 kilo ohm. And L unit, that is inductance unit, is 1 microhenry. Although we have kept it here, but generally in practice the inductor is not present. So we are done with this particular slide. So let's move on. Name map section. For multi-million gate design, the SPEF file will contain huge number of nets interconnecting them. Thus, the SPEF will be very bulky. The name map section provides a way to use shorthand method for net names, which are usually very long for a hierarchical design. Thus, to reduce the overall file size. Let us see how. To reduce the overall file size, SPEF convention is to convert long name of the nets to be mapped to a shorter numbers preceded by an asterisk. The mapping or lookup table is defined in the name map section. Here goes our example. Start the star, then in all caps the name underscore map starts the section. Next comes the 509 is the mapping number, and the actual net name is here is F underscore C underscore EP2. Similar way, we have the other mapping numbers for all the subsequent nets like this. So let me just bring my mouse pointer. So these are shorthands and these will be used in the entire SPEF instead of the full net names. And here you can see this is a hierarchical net name. So when all these long text or alphabets, you can count how many alphabets are there. They are replaced by only 3 digits and 1 asterisk. So that will help the reduction of the entire file size. So if you have to know in a resistor or capacitor about this particular net, you have to come back to the name map section and you have to follow this lookup table to know what is the corresponding net name. Later, these shorthand are used instead of the large net names as like star:509:16538 means an internal node of the net F underscore C underscore EP2. So guys, we are done with this particular slide. So let's move on. Port map section. The chip talks with the outer world with its pins, which act as ports to exchange the signal between the internal circuitry and external world. These are captured in the port section. Let us have a look to the port section. The port section is simply a list of top level ports in a design. The direction of the ports are marked
with I, O or B for input, output or bidirectional respectively. So these will be always in upper caps, this I, O or B. Now let us see one short and sweet example of the port section. The section start with star, then ports, it will be on all caps. Next we have star 1, then I, star 2 as I. So all these are ports. And we have star 3, the value is O. The star 4 has value O. Star 5 has value O. Star 6 has value O. Star 7 has value O. Star 8 has value B. And star 9 has value B. So please don't confuse this I and O with 1 and 0. So these are I and O. Whatever you have in the port section, those are I and O on the right hand column. And don't confuse them with 1 or 0. So let's move on. The DNet section. The largest part of the SPEF pie is the RCCC section, which is subdivided into DNet, that is D_NET, then con, CONN, RES, and cap sections. In this slide, we will talk about the DNet section. DNet means the distributed detailed net. Sometimes in RSPF format, there can be a similar section of RNet, that is R_net, meaning the reduced net. Let's now focus on the DNet section. Each extracted net will have a DNet section. This will contain a DNet line that start with R, then in all caps D_net, a con section, a cap section, a res section, finally an star end line to end the concerned net section block. So the DNet starts with star D_net and ends with a star end. In between it will contain the con, cap and res sections. Single pin nets will not have a res section. Nets connected by abutting pins will not have a cap section. The DNet line tells the net name and the net's total capacitance. So when this DNet line is there, the last field will contain the total lumped capacitance of this particular net. The capacitance will be the sum of the all capacitances present in the star cap section. So this lumped capacitance is the sum of the all capacitors present in the cap section. The con section, the connectivity of a net specified in detail in the con section. This section is very important for the STA as well as the EMIR tool. So let us get familiar with the con section. The con section lists the pins connected to the net. A connection to a cell instance starts with a star I. A connection to a top level port starts with a star P. The syntax of con entries is star I, then we have the field pin name, then we have the field direction, then we have star C, which follows next two values, that is X and Y coordinate, and finally we have the loading or driving information. So it could be either loading or driving, cannot be both at the same time. Where the pin name is the name of the pin as per the design. The directions could be I, O or B as per input, output or bidirectional signals respectively. The XY coordinate will be the location of the pin in the physical layout. For an input, the loading information will be star L and the pin's capacitance. For an output, the driving information will be star D and then the driving cells type. So we have the short and sweet description of the con section here. Now we are done with this particular slide, so let's move on. The res section. This section have resistor details. Resistor due to the metal or via both come under this section. During extraction, if you turn on the tail command to be dumped, then you can identify a metal or a via simply by its layer number from the additional layer map section coming just after the name map section.
We will talk about the layer map in the last slide of this presentation. Now, let us focus on the rest section. The rest section provides resistance network for the net. Entire entries in the rest section contain below fields: an identifying integer, two node names of the resistor terminals, resistance value between these two nodes. So one single rest line will contain these things: an identifying integer, two terminal node names, and finally the resistance value. The rest section is very much important section for the EMIR analysis. For EMIR analysis, the tail comment is a must. For STA, it does not matter whether we keep or remove the tail comment. We are done with this particular slide, so let's move on. The cap section. The cap section contains the simple capacitors and coupling capacitors. This coupling capacitor is very much important in signal integrity and crosstalk analysis. For STA, this section contributes the RC delay calculation of the metal or via interconnection routing. Let us take a tour of the cap section. The cap section provides detailed capacitance information of the net. Entries in the cap section come in two forms: capacitor lumped to the ground and a coupling capacitor. A capacitor lumped to the ground has these below fields: an identifying integer, a node name, and the capacitance value of this node. A coupling capacitor has four fields: an identifying integer, two node names of the two end terminals, and the value of the coupling capacitor between these two nodes. So we will discuss this through an example. All of these sections, all these things will then come clear into your mind. We are done with this particular slide, so let's move on. RCCC section example. We have discussed the theory so far. Now let us dig into the example. Here is our DNet line. There are three fields. The first field of the DNet denotes that this is the beginning of a dnode block. So here it is the beginning of the dnode block. The next field is the net name, including the hierarchy. The hierarchy separator is forward slash here. So this is the hierarchy separator and this is the node name final. This field can also be a number if the number is mapped with this net name in the name map section. So if we have a mapping of this particular net, so it could be a number instead of the name, and then there will be the node name. This last field denotes the total lumped capacitance of this net. Unit of this capacitance have to be obtained from the header section. This line starts the con section, that is connectivity section. This line gives the first connectivity information of the concerned net. Here, this I refers to the internal pin. The pin E and the total hierarchy up to E is also included in the name. The next field I, here you can see the I, means it's a input pin. The next field star C means that the next two fields are X and Y coordinates. So this is X coordinate and this is Y coordinate. The star L means we have a loading value. The next numerical value is the load value of the P. This is the input load of this particular P. This next line is very similar to the previous line we have just discussed, and this is for pin A. And here you can see that up to this the hierarchy is, and here it is I, and here the X and Y coordinates, and here is the load capacitance value. In this next line, we see a bit of difference. Let me explain. The pin name is Z. We can see the hierarchy down to Z. Here we go down hierarchy to Z. The next field O means it is a output pin. Then star C denotes the next two fields are X and Y coordinate. This is X coordinate and this is Y coordinate. These are coordinates in actual layout. The next field is star D. This gives the driving cell name of this pin as the next field. Here the driving cell name is OR2M1P. So this is the driving cell. The next line starts the capacitor section. This means the star cap starts the capacitor section. In this section, we will encounter capacitance and coupling capacitances. The normal capacitances has only one net name followed by its capacitance value. The coupling capacitance has two net names in between which the coupling capacitance is connected and calculated. The coupling capacitance numerical value will be the last field of the line. The first capacitance of the cap section is a simple capacitance. The first field is the capacitance count number, which here starts with 1 and it is incremented by 1 for any subsequent capacitors. You will see as the example proceeds. The next field in the line is the net name including the pin name with a colon separated at the last. This field is a number. Then it will denote an internal node instead of a pin, which is usually an alphabet. So here instead of an alphabet, if we have a number, it will denote an internal node. The next field is the capacitance value for pin or node, whichever is applicable. This is the capacitance value. This is the lumped capacitance value or the capacitance with respect to the ground, because this is a simple capacitor expression. The next capacitance, we can see the first field is incremented by 1 and it has become 2, as I just mentioned. Here we have two net names. One has a pin name A, another one has the pin name Z. If we had numbers instead of A or Z, that would mean these are internal nodes. The last field gives the numerical value of the coupling capacitance. So this is the coupling capacitance in between these two nodes or pins here rather. And the example before, it was the lumped capacitance with respect to the ground. So here is the difference of the two kind of capacitance expression. This next capacitance again is a simple capacitance to the ground. You can interpret this as same as before. The next line, that is star res, denotes the beginning of the resistor section. Here in this line, the first field is the identifier, also known as the counter, which increments by the value 1 for any further subsequent resistors. The next two fields are two nodes in between the resistor is connected. So this is node 1 and this is node 2. Here in this case, these are two pins. In case these E and Z are integers or alphanumeric value, they will denote a node instead of pin. The last field here is the resistor's numerical value. The unit can be found in the header section. So the resistance section is very much simple at it has only one particular format, that is two nodes in between the resistor is connected and the last field is the resistance value. The next resistor has the same format as just we have discussed. And again, this has the same format too. Here comes the star end, which ends the dnet block that we started with the dnet text. Here we started the dnet block with this d_net, and here we end this particular dnet block for this particular net with the star end. So this is the opening and this is the closing of the dnet block. Before concluding here, few more things I would like to mention. When a metal routing is breaking into several pieces, it creates multiple resistors. Now this breaking into is done by the extraction engine. No designer does this, but the extraction engine, for its calculation purpose and the algorithm, it breaks it down for a long metal piece into multiple shorter metal pieces, which are also represented as resistors. Such two neighboring resistors will have one node common in between them. Their order may be anywhere in the entire res section or the block, but the common thing will be they will have a particular node common. So if you see such resistors inside a single res block, you will understand this is the two section of the same metal routing piece. For EMIR, we dump additional tail comments of all the R, P or CC, that is resistor capacitance and coupling capacitors. From this tail comment, we also get the XY coordinates in the actual layout. For resistors, we get the metal or VL layer number also. We are done with this particular example and we can move on to the next slide. Standard Parasitic Extraction Format snippet. Here we will go through a miniature version of a SPEF file. Okay guys, one thing to be very frank here, we cannot quiz a entire SPEF file in a single slide. I have tailored it and removed the bulges and make it oversimplistic for you just to grasp the entire SPEF in one single shot into your mind. Here is our total SPEF file. This is a snippet. This is not a real SPEF file. This is just for your understanding and educational purpose. Here is the snippet we included in the layer map and the tail comment, which are interdependent. Here you can see that we have the header section, then we have the name map section, then we have ports, and this layer map section is contributed by these tail comments. Whenever we put tail comments, we get this layer map. Then we have a dnet section which has the con, cap, and the rest section we have just described sometimes back. The purpose of this slide is just to imprint the SPEF file structure into your mind. Let me rephrase again. Here goes our header section, then comes our name map section, then comes our port section. The layer map section comes the next. This is associated with the tail comment. Whenever the tail comment is there, we need the layer map, otherwise we don't. Next comes the dnet section, in which we have subsections as con, cap, and rest. And here you can see that if there is a LVL, it is 23, means here if we go back to layer map, it will point out that here 23 is metal 2. So this register is a metal 2. Such tail comments, and again I have trimmed it down. There will be XY coordinate values from which you can actually go to the layout. And since this is a metal piece, there will be W and L, that is, it will be a rectangular piece. So length and width, this is length and this is width. So if it is a via, then instead of W and L, here will be A equal to some value, that is the area. For vias we have area because vias are square generally. I think I have given enough details about this snippet.
Hey guys, welcome back. In today's episode, we are going to discuss below points. Power delivery network, its significance on IR drop analysis. Next, we will cover the definitions of IR drop and ground bounds. Next, we will show the position of IR drop in both the design flows of the IP design as well as ASIC design flow. Next, we will touch base on some of the fundamentals of resistance, ACL, AVL, and circuit and parasitics. Next, we'll do a classification of static and dynamic IR drop analysis. Next, we will show the IR drop and its impact on the timing analysis. Next, we will talk about the IR drop effects to be found for multiple power domains. Finally, we will talk about the IR drop thermal hotspot detections and its mitigation methods. So, that's the menu for today. Without any further delay, let's begin. Introduction. For continuous downsizing of the technology nodes, the chip operating frequencies continuously increasing, at which the timing related defects coming out of high-speed tests are high in proportion. Now folks, you might have noticed that today your mobile phone processor, the gigahertz processing speed is increasing with every new generation, and IR drops are very much relevant for this high-speed switching operation. We'll come to that point later. DFT techniques may cause the test vectors to contain non-functional states, which result in higher switching activities compared to the functional modes of operation. Specific scenario. Excessive switching activity causes higher power dissipation, which in turn may cause IR drop hotspots that could damage the circuit. Due to the higher IR drops, which increase signal propagation delays during the test, causing field loss. Power delivery network. The power grid simulation in ASIC causes power delivery network, abbreviated as PDN, to turn on all the leaf cells inside any VLSI circuit. Here is a short and sweet diagram of the power delivery network, which is easy to understand. Now let me point out the parts and components of this power delivery network. This is power ring. There are two types of power rings, since we have shown in two different colors. One is VDD, another one is VSS. Next is the power strip. Here, these take out lines from the power rings into the cells. So there are again two colors because of the two different supply voltage, that is VDD and VSS. This one is called IO pad.
This one is called IO pillar. This one is called corner cell. And this area is the core where our silicon chip resides. So the power delivery network, as you can see from the figure, distributes the power, that is VDD and VSS lines, into the core area. IR drop is excess voltage drop caused by parasitic RLC of the metal routes from the PDN, happening even before the desired voltage can reach the target power pins of the standard cell, IP blocks or macro blocks. So as per this particular definition, the IR drop happens well before the actual voltage from the power rings, as shown in the right hand side, could reach up to the specific standard cell or macro blocks or any IP block to the power strip. Power buses carry large DC current, causing the large IR drop, which in turn gradually reduces VDD towards the center of a chip when the power supply is driven by pads around the perimeter. So here in this slide, we have shown you the short and sweet diagram of a power delivery network and explained in a nutshell how IR drop happens through this power delivery network. IR drop and ground bounce. The total IR drop is further divided into resistive and inductive subcomponents. Here is a simple graph to explain the two subdivisions. This is our VDD line. This is our ground line. Now, the resistive voltage drop, also known as on-chip IR drop, is mostly due to the voltage drop because of the on-chip metal or via interconnect resistance. Here in this diagram, this small drop is called the IR drop. The inductive drop, also known as the DIDT noise, is mostly caused by the in-package inductor. The DIDT noise, often referred to as simultaneous switching noise, also known as ground bounce, which is caused by rapid changes in the current passing through the parasitic inductors in the power network. And here in this figure, this bump is the ground bounce. So you can see the two components of the IR drop, the total IR drop, are shown in the right hand side figure with a drop and a bump for the VDD line and the ground line. Both of these contributes to the IR drop as a whole. So we are done with this particular slide. Let's move on to the next slide. IR drop in IP or analog design and ASIC design. Here in this slide, our flow proceeds in the direction of this arrow, and in the left hand side we will keep the IP design or the analog design flow, and in the right hand side we will keep the ASIC design flow. Here the graphics are used as a symbolical meaning so that you can identify easily whatever I have just mentioned now. So first, in the IP or the analog design part, the schematic design is done by the designers. Next, we draw the layout by hand. Next, we do the ERC and LVS check on the layout and make sure that the layout is clean of any DRC or LVS violations. Next, we do the parasitic extraction, abbreviated as EX, and other set of physical verification. Next, we do the EM and IR drop analysis. Generally, these two are paid or analyzed side by side because of their similarity in their nature. In this channel, I have already created one episode on EM analysis in both the IP or ASIC design flow. Next, in this flow comes characterization and delivery. So, because this is a IP, you have to characterize it, means the electrical characterization and final packaging of this IP. So, we are done with the flow of the IP design. Let us move on to the ASIC design flow. First, there is a front-end design part. We are not going in a detail because that would take much more space and not very much relevant in this particular case. Next, we do the floor planning and PNR. As we proceed further in the back-end side, we have the ERC and LVS check after the floor planning, PNR, and the layout is done. This step makes sure that the layout is ERC and LVS clean. Next, we have the parasitic extraction, abbreviated as PEX, and rest of the physical verification checks. In the next step, we do the EM and IR drop analysis. Finally, we do the formal verification and we proceed towards the sign-off. So, you can see that the IR drop analysis is performed in both IP level as well as the ASIC design level in this particular highlighted step. The purpose of this particular slide is done. So let's move on to the next slide. resistance of metal strip and KCl AVL. Here in this slide, we'll look back and touch base some of our fundamental concepts which will help you to understand IR drop analysis and phenomena altogether. We have a very close relation of the current, resistance and voltage, that is I, R and V. You can see the triangle, and we can have several combination with these three particular components in multiple expressions of a circuit. Next, this is a metal wire, and this is very much similar to the metal routes where the resistivity rho is A into R by L. A is the cross-sectional area, A is the length, R is the resistance. This is a very fundamental concept, and this concept is used as is in the resistance calculation of the metal routes in the BEOL part of the chip design process. So the next one is KCL, that is Kirchhoff's current law, where we know that sum of all the currents reaching to a particular node is 0, which we can express by an equation that is I1 plus I2 is equal to I3. As per the direction, whatever current is coming towards the node, here shown in the picture, leaving the node. All these concepts are very much important in the IR drop analysis, and we are going to give further in further slides. The KVL, that is Kirchhoff's voltage law, also we can imagine from this circuit here. You can see some of the all voltage drops equal, that is I in inverse as well as the recipe. So I have touched base the basic physics here in this particular slide so that you can now correlate in a very fine gradient concept of IR drop analysis in upcoming slides. So we are done with this particular slide. Let's move on. Simple circuit diagram and parasitic. This is our simple circuit diagram where we are using the MOS, and this is without parasitics. This is just for your understanding here. And once we have the post layout version, that means layout is done, we are done with the DRC LVS, and we have extracted in the parasitic extraction process, that is PEX. We have with parasitics, that means circuit plus extracted parasitics because of the actual layout or the wiring that come in a real picture of a chip. Simple circuit shown in the left hand side becomes like this, where you have a lot of resistance and capacitances here. You can see in the right hand side, it's very clearly shown here, although this is not explicit. However, this is a very exemplary purpose. This is how the resistances and capacitances will come around any node that we are working. Also, again, I emphasize this is not an actual case or actual circuit. This is just for your understanding how the parasitics in the post layout process will come and get attached to different nodes, because these parasitics will contribute for the EM and IR. We're done with this particular slide. Let's move on to the next slide. IR drop classification. So we have our IR drop grossly aggregated in two parts. First one is the static one, that is static IR drop, and the next one is the dynamic IR drop. So this very simple classification. Now in upcoming slide, we will touch base both the static and dynamic IR drop analysis one by one. We are done with this particular slide. Let's move on to the static IR drop analysis. The IR drop is defined as the I average into the resistance segment, that is R where segment. Here I mentioned the word static. Here IR drop static means the static IR drop, and I average well-known quantities, the average current you have come across already in your textbook. And resistance R where segment, we have just shown you in the pictorial representation what the resistance segment looks like for a metal drop. Now this I average is all factors out of the linkage currents. Here you can see a simple representation of various metal layers that is going through. So if we say the horizontal ones, the first one here it will be 1, metal 2, B, and this could be metal 4. However, you can see inside I have drawn the resistances. Once the parasitic extraction tool prints up any of the metal out, it will split into multiple resistors, and they will be connected in the either in the TSPF or in the F file as like this. So resistance 1, resistance 2, resistance. If you see their nodes, they will be also in the synchronous of connectivity. So this is a simple picture of the R-wire segment that you can imagine, and the power delivery network part. When the power comes in, I have shown few slides back as a pictorial. With that and this in the mind, and then proceed for our next explanation points. Static IR drop is an average voltage drop for the design, hence it is stimulus vector dependent. Vectors are taken from 1, the switching probabilities of each cell, and number 2, applied switching probability of initial cell. The average current depends totally on the time period of the clock. This is very fundamental. If you go back in the definition of I average current, you will find out in the mathematical expression. Static airdrop is dependent on the RC of the power grid connecting the power supply to the respective standard cell. That is what I mentioned, that we already have shown a PDN few slides back, and this metal route, you can see that all these things will be coupled together for airdrop analysis. We're done with the particular slide. On to the next slide for few further points on static airdrop. The PDN reduced to a resistive network, and a voltage drop across this resistive network is calculated based on a given current source. Loads are assumed to be driven by PDN. The static airdrop is performed around all the production RC and PVT corners combined. So I have two separate episodes about the RC corners and the PVT corners in the same VLSI FAQ. You can find out them in the FAQ playlist. In case you are not familiar with the RC and PVT corners, please go ahead and watch to have an in-depth knowledge. In VLSI, the static airdrop is performed across all the combination from RC and PVT corners so that we have the full coverage. Next, gate channel leakage current is the major reason for the static airdrop. Another good point. Static airdrop was good or sign of analysis in older technology node, where the sufficient natural decoupling capacitance from the power network and non-switching logic was available. About the nodes which are beyond 130 nanometer, higher than 130 nanometer, or 90, all those technology down below. Right now, today we are on below 10 nanometer. Dynamic airdrop is a lot of significance. That's why we have a point. Sometimes switching factors can derive from the functional waveforms of the SPEF or the VCD files. We are done with this particular static airdrop analysis. Now let's move on to the dynamic airdrop analysis. Dynamic airdrop. Unlike static method, in reality, no two cells inside chip receive the same supply voltage due to placement, nearby cell activity, and dynamic nature of its operation. So here you can see one simple diagram. Here is our clock pulse. The black line horizontal is our ideal VDD, and the red line with the wings is our real VDD, which is in sync with the clock pulse. You can see here. Here in x-axis we have kept the time, and in y-axis we have kept the voltage. Although you cannot see the x and y-axis here. Now I have shown you the VDD, and the black line horizontal is our ideal ground. And the line with the wings that is shown in green, that's why I have kept the color same, is our real ground. So these are the two things you are going to get explanations in the upcoming points. Thus, each standard cell have its unique dynamic voltage signature for the power or the ground pin. Cycle to cycle, the dynamic voltage variation depends on overall change in the peak current, which causes the RLC oscillation or noise in the board or IC packaging. You can understand the swings that shown in the right hand side picture, that is in the real VDD and real ground, comes from the RLC oscillation or noise. Number 2, change in the toggle rate of the local cells, which could result in temporary depletion of charge and high frequency noise drop. We have covered some points. We are yet to cover further more points on dynamic airdrop. So let's move on to the next slide. Here, the PDN is modeled as a network of the impedance and time domain or transient analysis is done. And see in the right hand side, I have said that we have kept the time in the x-axis. And when we do any analysis with respect to time, it referred as the transient analysis. So because of the RLC and we are seeing the swings, we do the transient analysis on the PDN. And the PDN is seen as the combination of the RLC. Those are parasitics. Those are not from the design intended point of view. Here, the airdrop is caused by high-speed switching transistor inside logic cells. Peak current demand puts off when a large number of circuitry switches at the same time. Hence, dynamic airdrop is less dependent on a clock period and can't be modeled by pure traditional static timing analysis. So you can see from the right hand side, there will be a lot of swings that is coming out of the RLC, and this would cause a peak current shoot off, and that's very much related with the dynamic airdrop analysis. And this is dynamic in nature, that is time, so it cannot be modeled with the static timing analysis where we are performing everything in static manner. That means all are pre-characterized values and not in the on-the-go analysis that we do in our transient analysis. So in case you have some confusions about the static timing analysis, we also have a playlist in this channel. So go there into the playlist and start from first episode. There are a couple of episodes which contains the theoretical part, and as well as we cover the hands-on practical lectures here in the playlist. So go ahead and watch them. Preventive IR drop analysis and investigative analysis is test pattern specific. Here, whatever the dynamic thing we are dealing with is very much dependent on the test pattern. Why we talk about test pattern? Because the high switching frequency that we are talking about in the context of dynamic IR drop comes from various test patterns that we can generate. Those detections of the dynamic IR drop will be through the test patterns of various kinds. So done with this particular slide. Let's move on to the next slide. IR drop and timing analysis. Undetected IR drop can be compensated by means of increasing the supply. Extreme cases, this would lead also to timing analysis failure, whose root cause is higher voltage drop above specified threshold or margin. Dynamic IR drop neither can be detected nor can be modeled by static timing analysis. Altogether, the IR drop can cause setup violations on the data path signals. Here is our example from the STA playlist where we have shown the setup violation using the OpenTimer tool. And IR drop can cause hold time violations on the clock tree network. Here in the playlist, we have also shown the hold violation using the OpenTimer tool, and these are the explanation or snapshots from the episodes in the STA playlist. Delay of a cell depends on the voltage difference, that is VDD minus VSS, both functions of T, that means both are transient as we have shown in the slide before. This delay increases with the increase of standard cell threshold voltage, while we vary the threshold voltage in a manner for the standard cell for the different categories like ULVT, LVT, SVT, HVT and UHVT. These are various standard cell packages for different threshold voltage. ULVT is the ultra low VT, LVT is low VT, SVT is the standard threshold voltage, HVT is the high threshold voltage, and UHVT is ultra high threshold voltage. So keeping all the points in mind and see that with the hit on the setup and hold violation as well as in the delay, altogether the timing analysis is get affected by the IR drop happening in an actual check. We are done with this particular slide. Let's move on to the next. IR drop with multiple power domains. Power distribution among multiple power domain, P is the abbreviation, in a single chip is significant in floor planning and placement phases. So here you can see one diagram, that is a block diagram for a power domain blocks in a chip. So let me bring out my mouse. So whenever we have different power domains, we have a controlling block called the power management block, and here PD1, that is the power domain 1, will have VDD1, PD2 will have the VDD2, PD3 will have the VDD3. So I have just named it maybe a digital block, analog block, and some macro that you have purchased from your another vendor. This is a typical representation of the different power domains. I have explained about the power domains in detail in the UPF series, and you can find the lectures on the UPF in the UPF playlist of this channel. Proceeding forward, the next point is the PNR tool synthesizes the power distribution network based on the power budget specification for each domain while keeping the power network constraint under consideration. Because of all the blocks you can see in the right hand side picture, budgeting has to be in a proper way so that proper voltage, if there are 3 different VDDs in a single circuit, they will receive in a proper manner. IR drop map is used to analyze the power network. We'll later come to the IR drop map. If analyzed maximum IR drop is not acceptable, then reconstraint and resynthesize are done. So these are engineering changes that we do as per our analysis the IR drop. After the IR drop becomes acceptable, the new floor plan is created with added power or ground pads. I have shown the pads in the first or second slide in this particular lecture. So we are done with the cases of multiple power domains and how the budgeting and all the things we deal with the different power domains when we have in a how we approach the situations. It's just discussed here in this slide. We are done here. Let's move on to the next slide. Thermal hotspot by IR drop. The heat produced in a chip is proportional to the dissipated power. That is what I touched base in the fundamental slide where I have shown the relation of V, I and R. So I square R is power dissipation which causes the heat, and all those things we have done in our fundamentals in our textbook. An excessive power dissipation during the operation will increase the circuit temperature well beyond the safe zone, causing the permanent physical damage. Such zones are predicted by dynamic IR drop analysis and referred to as hotspots. Now, how do they look? They look like this. So you can see different colors. And these are heat signatures predicted by IR drop analysis inside a chip. So you can see there are different color gradients here in the right hand side picture. Generally from green towards the red, we more approach, the more hot regions are there. So this thermal signature is kind of similar to if you see the infrared detection of heat, sometimes used in medical sciences. The videos where a human body temperature is scanned by the different scanners. So there you also find some similar heat signature. There then kind of color gradients are used. Here we do it by the IR drop analysis tool, and we have a similar kind of heat signature happening inside the entire chip. We have some zones which are less heated. We have some zones which are extremely heated here in the highest color, the red. So obviously the tool will give you the legends about the power ratings and dissipations happening for each of the color. So this is the heat signature. These are called the thermal hotspots. There are different spots inside the chip can get heated, and over time they are not cured, then they will cause the permanent damage. That is the purpose of the IR drop analysis, to detect these hotspots and correct them way before the sign off. Thermal gradients are hotspot due to the various different functional blocks with different power dissipation over current or voltage stress for a long time of continuity. Generally, our chips, if it is a handheld device, they are switched off. But in case of, say, network routers or servers, they will be kept on and on for a long time. So these are under the constant current or voltage stress. So if any hotspot generates in such a chip, over time, they will grow and become fat. And the damage will happen to a larger part of the circuitry. All these thermal hotspots are detected by dynamic IR drop analysis, and they are cured by the engineering changes so that things are well taken care before the chip goes into the hands of the end customer. Here we are done with this particular slide. Let's move on to the next slide. Here in this slide, we'll talk about the IR drop mitigation. So far, we have discussed about all the reasons behind IR drop, how we detect the IR drop, and our detection procedure theories we have covered so far. Now, here in this slide, we'll talk about some of the mitigation methods in the upcoming points. High IR drop impact on the clock tree network, causing the hold time violation, while the IR drop data path signal nets are caused data time violation. I've also touched with this particular point, few slides back. To deal with such situation, one may separate the standard cells with high switching activity apart so that the burden on a given bump feed many standard cells can be mitigated. The lines coming from IO pad into the power wings and then going for strips, those will be well taken care if separate out zones where there is a higher switching activity and there is a less switching activity. So chances will be less of getting hotspots, and the circuit will be cured of the IR drop violation. And these are the methods, the engineering changes we are going through in this IR drop mitigation slide. With padding, clock cells technique, clock buffers or inverters and clock gate cells are given extra space to keep out regions to avoid placement of standard cells and any excessive cell density around them. Decap, that is decoupling capacitor, insertion around the cells within a dynamic IR drop hotspot region is another way of mitigation. High driving strength standard cell create a dynamic IR drop issue, because if the driving strength is high, it will draw more current and cause a more dynamic IR drop in the long run with respect to the time. Self padding is used for these cells, or we insert the decap cells around them to mitigate the IR drop. So these are few examples of the engineering changes after we detect the IR drop hotspots through a preventive analysis. In case we find the hotspots, we apply one of these techniques. Sometimes as per the design and case by case basis, here you can find a different solution as per your own work experience. So please let me know in the comment you have used some other techniques for IR drop mitigations to share with others. We're done with this particular slide. Let's move on to the next slide. Summary. Here let me summarize the entire discussion we have done so far in the past slides in this episode. Most of the times, the undetected silicon IR drop may lead to appropriate voltage not reaching the transistor in CMOS. Very simple point, because if the drop happens, that amount of voltage is subtracted from the power line, and the end cell, the lip cell, will not get the desired amount of voltage because of the KVL, right? This can be compensated by increasing the supply voltage, but may contribute to the timing analysis failure for extreme cases. If the IR drop exceeds a specified threshold, typically say 10% of the VDD, the chip could become defective, the kind of de facto standards that we use in a design house. IR drop analysis is necessary for both at the block level and the chip level to assimilate preventive design strategy. IR drop gets to be bigger problem as lower supply voltages are used in lower technology node. IR drops in metal routes cause the wires to heat up. Oxide is a good heat insulator, so over time, IR drop may build up heat in the metal routes. This can degrade metal wires resistance and performance over time. When the wires get hotter, they become more resistive, causing more IR drops and more heat until the wire melts down. For thermal runaway, this may cause burnout problem. So we are done with this particular slide. Let's move on. Today we are going to discuss about electromigration in analog and digital designs. So what is electromigration? Let's see. Electromigration or EM is a aging cum failure mechanism associated with the average and RMS current densities in metal or via interconnects. EM analysis is performed on cell external interconnects as signal and power nets. EM goes in a very positive feedback loop with temperature Joule heating. If left undetected, it can lead to performance degradation and finally chip failure over time. So let's see the physics happening in electromigration. A phenomena of molecular rearrangement happens in the solid phase caused by electromagnetic field. In addition, when current density gets too high, the momentum transfer from electrons start to happen. This result collision, which causes drift of metal ions from their original position, depends on conductor, crystal size, magnitude of forces, temperature, and mechanical stress. So, we have just talked about what EM is and what the physics happening. Now let's see in VLSI how the damages are caused. In this photo, we can see a void is getting created in metal via metal connection. So here we can see this will cause a open circuit in long run. Here in a single metal wire, we can see it is causing the open circuit failure. Here we can see hillocks are getting created and they will finally join the two parallel metal lines causing short circuit failure. So we just have seen that what is the physics and what the damage causes. But when we design any circuit in VLSI, we have to predict these things in advance so that the circuit don't go and damage over time. So for this, we have some predictability. This predictability comes from Black's equation. So Black's equation is a mathematical model for calculation of mean time to failure of any semiconductor circuit under the influence of electromigration. So this is the mathematical form we can see in the screen, and these are the components of that equation. This Black's equation is used to predict the mean time to failure for electromigration. Here, another important point, there is a basic thing, it's called bleach length. What is this? Anywhere that has a length below this threshold length will not fail by the electromigration. So, if any metal strip or any via is less than the bleach length, it will not harmed by the electromigration. Let's see how EM damages a metal or a via. What happened inside? First, the Joule heating I square R caused by the currents in metal interconnects. If this heat is low, heat gets dissipated through the metal interconnects. If this is high, void or extrusion get generated in metal interconnects or vias. Void or extrusion narrows the metal route. This in turn increases the resistance. This again increases the heating effect. So, it acts in a very cumulative positive feedback and it goes on increasing. So one is increasing another and finally the damage happens. So here let's see the pictorially what happens. First, increase of the local current density. This causes increasing in Joule heating. This in turn increase the temperature. This starts the growth of void or extrusion. Now, these last two steps marked by red arrows keep on going in a positive feedback loop, and finally, whatever was getting created, void or extrusion, that finally causes a disconnect or a short circuit, and the circuit performance is damaged. And in between stage, the performance is getting slowly degraded. Now, let's come to the method of EM detection. In VLSI design, we have to detect the EM in very advanced in the design stage.
there are two different methodologies are there. One is for the analog or the semi-custom, and second is for the digital. The EM analysis, the physics behind is same, but when we predict it during our designing process, we have to follow different methodology for the prediction or the violation detection. Before we go in detail of each of them, let's see in a general bird's eye view what is a circuit and how it is detected. And the violations mean the EM violations. So a circuit we can imagine as a interconnection of different cells by different nets. So nets are shown in purple color. Here you can see here the purple color, these are the nets, and sky blue color, these are the cells. So generally the nets are extracted in SPEF format and the cells are extracted in DSPF format. So these are parasitic extraction. Later I will exemplify the SPEF and the DSPF. These are one of the prerequisites that we need to do. So both type of analysis is done. One is at the interconnect level and as well as the cell level, because inside a cell there will be some metal wires and they can contribute to a EM violation. So we have to do both. What inputs are required? Number one is RC parasitic, SPEF for DSPF. These are two different formats. I will differentiate them at later stage of this video. Cell or net specific data. These will I also share what the data is, and technology specific EM rules from the foundry. Okay, this third point is very much important. This rule actually gives the capping level after which a metal doesn't show the current, the RMS current or the peak current, whatever the current we are seeing in a net. This threshold, if not crossed, it doesn't show the violation. But if this threshold is crossed for any of the net, metal, via whatever, that will be predicted as a potential EM violation. Now I just give the overall bird's eye view of what things are needed and how we analyze in nets as well as cells. So now let's jump into the analog or full or semi-custom designs. Let's describe first the flow and let's see where the EM stands in this entire flow. So design specification, then comes the schematic design, then the basic circuit simulation is a functional simulation, then the floor planning or partitioning, then placement and custom routing, then layout generation or changes, then we do the DRC and LVS, then we extract the parasitics, also abbreviated as PEX. Then in the next stage, we do the EM and IR analysis. Now, a violation is there. Yes. So, we get the violation map and we go back to the layout, overlay it and see the different hotspots and we do the necessary changes. If there is no violation, then we proceed towards the next steps. So, from layout generation or changes till the EM analysis, it happens in a loop until all the violations are cleared. This is overall picture or the bird's eye view at what stage we analyze or predict the EM and what things happen for a designer. Now let's see what things we do and the nature of the analysis. In analog designs, EM has a unique flavor because currents in analog circuit vary from design to design. Yes. So if your design is a PLL, it will be different. If your design is a band gap, it will be different. If it's a DC-DC, it will be different. So each design, the analog circuit currents, the levels of current, I mean to say, will be different. It can vary from nanoamps to a few amps. Amps means where we are dealing with the power circuitry, high power applications we are using. In analog circuit, it is important to note power rail, VDD, VSS and signal interconnects carry currents nearly the same order. So, power nets and the signal nets have more or less same amount of current. Total number of nets pretty less than a digital design because analog semi or full custom design are handcrafted and so the designs will have less number of nets overall. In analog designs, say whether it is a full custom, semi-custom, in any case, we extract a DSPF netlist from the layout which includes R, C, CC plus the tail comments. This is a very important point, the tail comment and also the LVS log. This netlist is then used to simulate the currents in the power nets as well as interconnects, signal interconnects. as I mentioned earlier, if any of these resulting currents densities exceed the EM safe boundary, a violation is flagged for that particular net and a violation map is generated. So this could be GDS, RV, whatever, and we overlay this violation map, the hotspot map, over the actual layout, and we point out the faulty points. So this was for the analog designs. Now let's come to the digital designs, generally the SOC or ASIC, whatever we call, how EM is done here. Before jumping to the details of the EM methodology, let's see the flow and where the EM is standing, at what stage we do the EM analysis to predict the potential threats. So first the design specification, then RTL coding, then verification, this is a functional verification, then synthesis, then the power routing, global placement, detailed placement, clock tree synthesis, then global and detailed routing, then layout generation and changes, then DRC and LVS, then the parasitic extraction, then EM and IR analysis comes. So at this stage, the EM and IR analysis is done. If a violation is reported, yes, so we go back to layout generation or changes. This continues until all the violations are corrected. Once there is no violation, we go towards the next steps. Now let's see in a digital design what are the important points for a EM analysis. Unlike the analog design, the power rails VDD VSS in a digital circuit carry DC current of nearly fixed magnitude, and this is the most important point in a digital design. Clock and signal interconnects carry AC currents. AC mean to say like pulse or PWL. Hence, the current changes direction with respect to frequency. In a digital design, generally it's a huge as compared to analog design and massive amount of clock and signal interconnects connecting a sea of logic gates. So here count of nets is huge. So first, the EM critical nets are filtered out. So this is the methodology inside the tools and it's their proprietary thing. Then the SPEF is extracted from the layout, including R, C, CC plus tail comment. The tail comment is the most important thing that must be there, extracted for these EM critical nets. Then SPICE simulations are performed on these nets to get the currents, that is average current, RMS current, peak current, whatever we are having. Now we have the EM thresholds from foundry, and if any of the resulting currents or the current densities exceed the EM safe boundary, a violation is flagged for that particular net and a total violation map is generated. Then this violation is overlaid onto the actual GDS and hotspots are identified and corrected. Now let's talk about the EM detection fundamentals. So we have seen both analog and digital. Now we are doing the crux of the analysis. So what inputs we require? Parasitic, netlist, SPEF or DSPF, test vector based on the functionality, SPICE model, SPICE options. Because to generate the currents, we have to do the SPICE simulation, the average, RMS, peak, this kind of currents. These are combined into a SPICE deck. Then transistor level SPICE simulation happens. In analog, we know that we do the SPICE simulation, and in digital, we have just discussed that for EM critical nets, we do these things. This results peak RMS or average current. The worst current of each resistor is compared with the EM threshold, and this threshold comes from the DRM. As a result, we generate the violation map. The metal or via which are having higher current than the allowable boundary limit as per the DRM are flagged as violations. So it could be current or it could be current density, both. We just discussed the general methodology, and now let's look into the SPEF and DSPF, the similarities and the dissimilarities. So here is a short snippet of a SPEF. A SPEF contains a header section, then a name map section. So these nets are numbers, and these you can see the hierarchies are also here. There will be a port section. Ports means the ports of the design. Layer map will be there. This layer map comes from the technology also, because each layer in your layout will have a number, and correspondingly it will have a layer name. So like 21 is metal 1, 22 is VIA, and 23 is metal 2. Then for each net, each particular net
net, there will be a dnet section. So if we see dnet, here number 5 is there, and this corresponds to net 1 from the name map. So the details of this net, including the parasitics, will be there. And in the register section, we'll see this red color tail comment. It will contain width, length, and LVL. LVL means this is the layer map, layer number. So 23 here means metal 2. In case of VR, instead of width and length, there will be area reported. The LVL will be still there. So this is just a snippet of SPEF. How does it look with the tail comment? Here, the snippet of a DSPF is shown. It will also contain a header section. The difference between the SPEF and DSPF is the DSPF is a ready for SPICE simulation. So there will be a sub-circuit definition. There will be a net section. So this net section, the nets are described like ground net. It will have its parasitics here. The register is having the tail comment. Other nets are also there. So I have just given a snippet, and here there will be the tail comments also, another net. And finally, there will be an instance section. So this is used in a SPICE simulation directly. So here the SPICE instances of the different internal parts will be there, and there is a .ends at the end. So this ends the SPICE sub-circuit. This is for a buffer, right? So sub-circuit buffer ends here. This is how DSPF is different, because in SPEF there will be no instance section. In DSPF it will be there. A DSPF is a SPICE ready format, while the SPEF is not a SPICE ready format. Now we have discussed the EM, its physics, its detection methodology in both analog and digital. Now comes the mitigation part. Now mitigation part is same in either of the cases, because we have to make the changes in the layout. We have to avoid 90-degree corners on high current nets, even distribution of multiple vias. We have to avoid abrupt wear width reduction. We have to double or multiple vias have to be used instead of single via, which are getting violated. Length shortening of a metal or a via below the bleach length. Increase the wear width to reduce the EM. Avoid using the parasitic extraction RSPF. This is a reduced format, so we have to avoid this at all cost. We must use DSPF or SPEF with tail comments. So here, after the violation are detected, we have given the scenario how the violations are mitigated. This is not only the exhaustive list. As per technological progress, we have different more scenarios, and we act according to case by case basis. So, in today's episode, we will be covering these topics. First, introduction. Next, we will revisit the Black's equation. We will discuss Black's equation interpretation in EM in VLSI. We will also do the graphical tour of the temperature versus mean time failure, that is MTF. Next, we will look into the temperatures, all of which coexist inside the chip. Next, we will consider all the heating effects inside the chip. Finally, we will summarize the entire discussed topics. So, here is the menu for today. Without any further delay, let's begin. Introduction. So, this particular introduction will be useful for those who haven't also watched that particular episode in which the question was asked by Satyanshu. You can go ahead, watch this episode, and then you can go back to that particular episode. There is no issue. Many of the IC failure reasoning either thermally activated or related. The IC failures are maximum impacted by the thermal reasons. Hence, predictive analysis is much more important in VLSI reliability analysis. Just to support the first point, I would like to emphasize here, you might have seen that in our CPU, we have a fan over it and we use the heating paste. Also, in normal PCBs, if we have a IC which have a heatsink, we attach an aluminum piece to it to dissipate the heat. And also, we use a thermal paste inside for the good conduction. All these observations you can have from your day-to-day life, and you can now focus on to the actual VLSI reliability analysis, because at the end it is made on silicon and the heat has to be tackled, and that heat is a much more damaging factor than anything else. In VLSI we use the predictive analysis. Predictive means we use mathematical models inside the simulator, and hence we predict that how long this particular chip will run before fail completely or before a significant damage is there. This is the importance of the predictive analysis. And when we do this predictive analysis in the physical verification stage, we take the help of the tools. Those are able to judge the long-term effect coming out of electromigration and can detect which and where all these failures may come. Accordingly, we take corrective actions so that we can mitigate the effects. Let's move on to the next point. There are various temperature generation mechanisms in modern ICs. When you see that a IC particularly getting heated, you may think, okay, it is getting heated, but that heat, if we split into components, it is contributed by multiple reasons. The heats are coming from multiple sources. Inside the chip, not outside the chip, inside the chip. And the temperature which is there in the ambience where the chip is operating, right? That temperature is already there. We are not talking about this. That particular ambient heat will be there. In addition, inside the chip, multiple heat sources are there. So we will discuss today all of this. We are just having the introduction right now. A chip may go above 100 degrees Celsius during its practical operation. This is a very important point because in advanced CPU casings, sometimes there are different kind of coolants are also used. Why all those coolants are used? Because the temperature goes high, you have to cool it down. If you do not cool it down, the thing will get damaged. Whether it is a CPU, whether it is a GPU, all these things. You will see there are metal fins on which we have used fans. We use more than one fan in the CPU box inside which we keep the entire motherboard and all the stuffs. However, in the design level, we must take precautions that maximum extent we can prevent all these heatings. Rise in the temperature enhances solid state metal ion diffusion. Since the diffusion coefficient in solids is much smaller than liquids, electromigration in solids occur at much slower rate. This is a very important factor because the diffusion in liquid happens faster, in solid it happens slow, and hence it happens slowly but gradually but continuously over the time. Since it is kind of relevant to the human ages when we run for a long time and we become old, that similar concept is coming here, and that's why we call it aging. The aging of the silicon chip, where the functioning degrades to some predefined values. Electromigration is caused by scattering of the moving electrons with the ions, that is, by momentum transfer between electrons and ions. This is a very simplistic way we have explained what happens inside the electromigration phenomenon by the physics. This ion-electron interaction, sometimes referred to as the electron wind. Someone say it is ion-electron interaction, someone might say electron wind. So you may find different terminology. So I have kept all these things so that you have a proper pointer here. So you can go in any direction, or whenever you are reading any particular article, you will be able to interpret what it is meaning. So we are done with this particular slide. Let's move on. Black's equation. This equation is very important equation. I have explained it in the main episode on which the question was asked. However, I am repeating the equation here because it has a very much important significance. That's why you will come to know. Black's equation is a mathematical model for the calculation of mean time failure, that is MTF, for a semiconductor circuit in VLSI, which is under influence of electromigration. And one thing I would like to clarify, electromigration is not only for the VLSI thing, it happens, it's a basic physics. However, since we are focusing on the VLSI electromigration, we are focusing much more on the things that happen in the VLSI. So here is the equation of the mean time failure. You can see, let me bring my mouse. Here you can see the T factor, that the temperature in Kelvin. This equation you can see at left hand side as Y we have MTF, X is here which is T. So it's simplified way we can say that this is e to the power 1 by x. And if we plot a simple x versus e to the power 1 by x here in a normal graph, this kind of graph will show up. So I have kept only the positive axes. I have not gone in other axes. This is the plus x and plus y axis. So here goes our x and here goes our e to the power 1 by x. So this will be a kind of mathematical representation in the graph. So you can have an idea that how this equation can have a representation. Later we will show how actually this MTF is plotted in graph. Don't worry. So the components in this particular equation are: A is the cross-section area dependent constant, J is the current density, T is the Boltzmann constant, T is the temperature in Kelvin, N is the model parameter. All these things are there. I have highlighted this T with a different color because today in this episode we are focusing on temperature, that is the heating effect here. Hence our focus will be entirely on the T part today. So I have explained the significance of the Black's equation in today's episode as well as in the electromigration. So one more thing here is Q is the activation energy. So we are done with this particular slide. So let's move on to the next slide. Black's equation interpretation in EM or VLSI. Probability of failure is termed as the failure fraction. Now, these are mathematical terms that correlates the mean time failure and how the industry expects all the failures. So in this slide, we will be focusing on these terminologies which are used to judge the failure and represent the failure. And that's how the VLSI industry categorizes and depicts the failure. Industrial markets demand low failure rate expressed as defective parts per million, abbreviated as DPPM, over the entire chip lifetime. Few slides back I have just talked about the aging. So here you can see the chip lifetime. Both are synonymous. VLSI reliability engineers translate this chip level specification to specific fail fraction targets in units of failure in times, that is FIT, on individual resistors. So these things lay well inside your simulator. These are calculated, and sometimes in the figure of merit of any silicon chip, all these factors may come. The classic Black's equation relates the mean time failure. Now you can correlate all the terminologies that I have just depicted in this particular slide. Failure fraction, DPPM, FIT, and now MTF. So all these are correlated. In Black's equation, T corresponds to the contribution from the ambient temperature as well as current induced temperature rise due to the Joule heating. So don't worry, we'll talk about all other components, but for now you can just bank upon that the T corresponds to the ambient temperature as well as the rise in the Joule heating. These two components are for sure there, contributes to T. There are other components come later. Temperature versus MTF. Here in this particular slide, we will be not plotting but kind of visualization. This is the x-axis, which is time. Y-axis is the temperature. So this is a rough idea just for things to get into your mind. Now this green dot represents the MTF. So you can see if the temperature is low, lifetime is large here. As the temperature go high, so you can see the mean time failure point shifts left side and the time span is much less than the previous one. In the similar way, if we go higher in the temperature, the point comes closer in the timeline. And we go and much more higher, the point comes closer. That means with higher temperature, we have a less lifetime of a chip. That means a faster aging. So this is the purpose of this particular graphical representation. So generally we have time here, it is long, so the life is long of this particular chip. And for this particular chip, where the temperature is going really high, the lifespan is much less than this one. So this way you can visualize how the temperature impacts the aging. And behind this, only we have taken consideration of the electromigration. You can recall the Black's equation, you can recall the e to the power 1 by x graph I have just shown you sometimes back. And now I will show you the graph that is used in the industry. This is the graph. Let me point with the mouse. So here we can see the delta T, and here is the ratio, that is MTF by MTF of 300K plus delta T. So this way the industry plots the graph, and don't get confused. This is a logarithmic scale. Okay. So this one is a logarithmic scale, and here is the delta T. So this way in the silicon chip, the MTF is plotted with the delta T. So folks, we are done with this particular slide. So let's move on. Temperatures coexist inside the chip. So far, we have discussed about the Black's equation, the different terminologies those are used to represent the lifetime in the figure of merit, how different companies will exchange data about the lifetime, which all leading to the electromigration, right? Now, we will see the effect of multiple temperatures on the electromigration. Before that, let us take a tour of on what type of sources of the heat inside the chip. First, the metal interconnect Joule heating. So it could be metal, it could be via anything. So Joule heating, we already know that causes the heating, which is a kind of primary reasoning for the electromigration. Next, we have the ambient heat inside the chip. This is obvious. The chip has to operate in ambience. Next is the SOI self-heating. You must know that UT-SOI CMOS are nowadays a lot of popular because of low leakage factor. However, SOI increases the self-heating. It's a huge effect, and I think in many simulators, this self-heating effect is nowadays also getting considered for the EM. And one more thing, the FinFET and gate-all-around devices, some of them are bulk. However, many of them are SOI devices. Whether it is a CMOS, basic CMOS, or the FinFET or the gate-all-around, the SOI impact of the self-heating is there. Nowadays, we also focus for the EM violation. We consider the self-heating effect. Next, high frequency switching operation released heat. So generally we are talking about the electromigration, and nowadays the circuits which we use in our day-to-day operation operate at very high frequency, maybe in the gigahertz rate, or it may be higher. All those high frequency switching operation, you can visualize when it is switching, right? The current is moving to and fro in the metal or the via, and that movement is causing a lot of heat because electrons are moving in opposite direction with the change of the polarity during the switching operation. All those things goes to the basic physics. I think you already know it. Now, all these heating effects are considered together, and we can think that all those are contributing to the T. Here you can see the T. This temperature is the final product of all these heat source that just been explained in this particular slide. So we are done with this particular slide. Let's move on. Heating effects inside the chip. Now we'll discuss about the effects of all these heat sources one by one. Designs at below 10 nanometer node are typically based on FinFETs and gate-all-around FETs. I just mentioned about this even I think in the last slide. FinFET and gate-all-around devices also suffer from significant self-heating effects. As I mentioned, these FinFETs, most of them, and the gate-all-around may be on the SOI devices to reduce the leakage, and hence the self-heating effect coming into the play. One more thing I would like to mention, because the buried oxide layer, the heat cannot dissipate, but for bulk, it can dissipate through the substrate zone. However, for buried oxide layer, if it is there for the SOI devices, the heat cannot go out. So the heat whichever getting generated stays within the chip. That is the self-heating. The high transistor density gives rise in the high heat flux inside the chip. So this is another cumulative effect which we have. Inside the chip, there will be millions of gates, right? So there we have multiples of those millions as the basic transistors. Those all transistors are contributing to the heat, and adding up the total heat inside the chip, the packaged chip goes high. In addition, inefficient heat removal paths give rise to the thermal ambient. I would like to mention one thing here. The chip may have or may not have a heatsink or the filaments that we see usually outside the CPU or something like that. However, the fact is that whatever is getting conducted out of there may not be well connected to all of the path where it is generating the heat. So this is the main theme of this particular line. The thermal conductivity in the confined region of the silicon fin is degraded due to lattice vibrations, that is phonons, plus the addition buried oxide layer in the SOI FinFETs or the oxide that surrounds the nanowires in GAFETs. So here another physics has been touched base because of the lattice vibration. It also generates some energy, right? And some of that energy could get converted to the heat, and which will finally contribute to the temperature. So this phonon vibration can directly or indirectly contribute to the heating effect. You have now a picture in your mind of all the things that is getting the heats generated inside the chip. Let's move on to the next slide. Let us summarize all the things we have discussed so far. All active and passive components and the wire interconnect dissipate heat during the circuit operation. Even in silicon, sometimes we create both kind of devices. High frequency power loss and consequent heat dissipation contributes in increased temperature. This situation is further worsened with addition of high ambient temperatures. All of these above mentioned temperatures reinforce EM by contribution of thermal energy towards the electron wind. This is a very important point of this episode, right? All the heating effects we have talked about, all those temperatures reinforce the EM by throwing energy towards the electron wind. Rise in the temperature enhances solid state metal ion diffusion, which is in turn enhances electromigration effect. Combination of high heat flux and or high current densities driven in the advanced designs, EM can cause more damage in lower metal layers. So folks, with this particular slide and all these points I have discussed throughout this particular episode, things might have cleared in your mind with respect to the physics point of view, that what is the effect of temperature on the electromigration and hence the aging of the chip. So we are done with this particular slide. Let's move on. Here we go with the menu for today. First, we will talk about the electromigration and voltage and introduction. Next, we will discuss about the impact of the voltage on electromigration in detail, and in the next section, we will talk about its mitigation. Next, very important concept, we will discuss what is a stress in VLSI circuits or any of the semiconductor circuits or any of the electronic circuits. Next, we will move on to the next section where we will discuss about the effect of frequency on electromigration and introduction. Next, we will go further deep by discussing the effect of unipolar pulsed DC waveform on electromigration. We will further analyze the effect of bipolar AC waveform on electromigration. Finally, we will move on to the conclusion. So folks, this is the menu for today. Without any further delay, let's begin. In this section, we will be talking about electromigration and voltage. Introduction. Increasingly small IC structures begin to have a significant negative impact on reliability because the cross-sectional areas of the metallic interconnects in the ICs are diminished in size. This is the scenario that is in present days we are going through right now. The problem arises because the required currents cannot be reduced to the same ratio and proportion even by reducing the supply voltage and gate capacitance. So if you are familiar with the ITRS technology roadmap where it is defined for each particular technology node, what will be the gate capacitance, what will be VDD, and all these minute details are there. So even in that particular roadmap, if we go and see, we will find that the currents cannot be bring down in the same ratio and proportion. In digital circuit, the voltage in the rails is constant for a particular technology node. So I just mentioned about the ITRS roadmap, right? If you go there, you will see that this VDD will remain constant for a particular technology node. For multi-VDD power domains inside a chip, the interaction points are balanced by level shifters. Nowadays, a lot of multi-VDD power domain chips are getting manufactured. So there we have generally a power management block which controls all the power going to different sections. They may have different VDD applicable to that particular block. So there we use level shifters. I just touch base this point because in today's scenario, this is also a very relevant information as compared to the previous bullet where I have mentioned for a particular technology node, the VDD must be remain constant. And in present scenario, how we deal with such different situation where we need a separate kind of VDD pair, we use a level shifter. In the digital plus analog mixed signal circuits, voltage level difference at the boundary are balanced by the A to D and D to A converters. Now in present days, the mixed signal chips here and there are a lot in production. If you look into them, what you will find that there are analog blocks which also coexist with the digital block. So the third point where we have said that VDD remains constant, that also get a bit changed because the analog circuit may require a different power supply voltage. And the voltage exchange in between these two blocks has to be exchanged with the interpreter, that is A to D or D to A converter, based on which direction the signal is propagating. So this is another important point. Signal nets are less wide than the power grid nets. I just re-emphasize this fact. For a power grid to function as intended, the voltage drop at each of its nodes should be smaller than a certain threshold. Otherwise, timing violation and logic failures may occur. So now the voltage node means it is a circuit concept, not the physical chip concept. In a circuit, we have different nodes from where the branches go out into different directions, carrying the power to different parts of the circuit. Now, these nodes should remain static in terms of their voltage level. This threshold value, as per the design rule manual, This all comes from the DRM, which comes from the foundry. We are done with this particular slide. Let's move on. Here we will discuss about the impact of voltage on electromigration. In last slide, we have talked about the basic fundamentals. Now we will zoom in further down inside the circuit. In EM process, the voltage dependence of the resistance R as a function of V is expected to be a constant. It may have a positive slope due to the Joule heating. Usually, RV displays a positive slope corresponding to a negative curvature in the corresponding IV characteristic. Over the time, voids may be formed at locations with high tensile stress, which results in a resistance increase and voltage drop degradation. Let me explain this point. Due to electromigration, two things happen. One, a hillock is created or a void is created. Now, if a void is created, what will happen? The cross section of the current carrying metal or via will get reduced, and hence the resistance will increase. If the resistance get increased, the voltage drop degrades. So this is the way the things are happening. The power grid is deemed to have failed if the voltage drop at any grid node exceed a user specified threshold. We refer to this as a voltage failure. This all specifications come from the design as well as from the DRM. These things have to be maintained. The EM lifetime of the grid refers to the time at which the EM induced voltage failure is expected to happen. So this is the entire picture of the failure of a power grid in terms of the voltage. We are done with this particular slide, so let's move on. Let us continue the discussion with few more points. The critical volume of a void is the threshold above which the interconnect is permanently damaged. This is very much clear. The volume corresponds to a critical resistance rise that either two of the condition, let us see those two. First, causes a voltage drop across the interconnect to impair proper functioning of the circuit, or leads to severe thermal damage generating out of Joule heating due to the power dissipation in the interconnect. In addition, the digital circuit are less sensitive to small voltage changes than their analog counterparts. This is we know very well. In digital, we have 0 and 1 level, and in analog, we have exact voltage. So the digital circuits are less impacted by the small voltage change. For the 0, generally we have a small band, and for 1, we also have a small band of voltage. So anything change within that particular band will not impact the particular level. The proper functioning of the digital logic depends essentially on the reliable differentiation between a few different digital logic states. Also, these circuits comprise a relatively small number of different types of subcircuits called gates. We have discussed a lot of points regarding the impact of the voltage on EM. It's a bit different than how the current is impacting on EM. You already know by all the points that have been discussed here. So let's move on to the next slide. Mitigation. When any problem comes to an engineer, the engineer finds a way to resolve it, and hence the term mitigation comes into the mind. In recent times, the wiring material was also changed from aluminium to copper due to its specific property. The lower specific resistance of copper resulted in a lower time constant, which gave rise to the higher signal frequencies. This in turn caused a lower voltage drop and lower self-heating in the interconnects. The changeover boosted overall electromigration robustness. We are done with this particular slide, so let's move on. We are done with the discussion of voltage impact on EM. Before going to the next section, here I will just touch base the concept of phase in an electronic circuit. When a circuit component, either active or passive, or interconnect, that is metal or via, is connected to either or combined under a constant voltage, under a constant current, under a constant temperature, we call it is under stress of that specific kind, whether it is pure or mixed. So this is the concept of phase. You will come across this particular term in the next section. That's why I explained this in a very simple manner. We are done with this particular slide, so let's move on to the next slide. In this section, we will be talking about the electromigration and frequency. Introduction. Damage caused by the electromigration generally due to the unidirectional current. This is nothing but the DC current. So the basic physics on which the electromigration concept stands is derived by the DC current flow. Now, AC causes bidirectional current flow with change in the polarity. That's why it is called the alternating current. In two parts of a AC period, that is on time and off time, the direction of the flux of the electron wind is completely opposite. Those who don't know the concept of the electron wind, please watch the last episode. Here I have mentioned about this particular term, and also I have explained in the main episode. In VLSI designs, such periodic waveform, that is AC, comes from a clock and corresponding dependent signal transmission to the metal or via interconnects. An AC signal can be different nature, that is, of the varieties are unipolar pulsed DC, bipolar AC, and peak current. Each have their own way of response to the electromigration effect for metal or via. Here we are done with the particular slide. Let's move on to the next slide. Effect of the unipolar pulsed DC waveform. We can imagine the minimum void getting created due to the electron wind. This void creation time is less than the on-time period of the signal being transmitted. We add up faster of the growth of the void. Now folks, please remember we are talking about AC, so there will be a on period and there will be a off period because this is a unipolar pulsed DC waveform. On the other hand, if the time of the void creation is more than the on-time period of the signal being transmitted, then it will negatively affect the growth of the void. Negatively affects means that will reduce the growth, or the rate of growth will be less than the previous condition in the last bullet. When we are applying a very high frequency signal, the electron wind cannot react to the on and off periods and only feel an average current density. So by the last 2 points, you understand that a particular electron wind can contribute to a void if void creation time is less than on period. On the other hand, if the void creation time is much larger than the on time, then the rate of void creation will be reduced, and hence such waveform, if it has a high frequency, this means this change is very fast, then the electron wind going through the on and off period feels only the average current density. When the frequency is very low, automatic gradient is built up during the on-time period. During the off-time period, such atomic gradients brings relaxation. However, if the metal or via is much longer than the bleach length, this relaxation is insignificant compared to the EM-induced damage. So folks, we are done with this particular slide. So let's move on to the next slide. Effect of the bipolar AC waveform. If the frequency is less than a critical frequency, that is the frequency needs to react the DC equilibrium, the interconnect will follow DC-EM behavior. This is the condition for the bipolar AC waveform, where we have the AC swing both sides of the y=0 axis. And here comes term that is never heard before in the discussion of the electromigration, that is a critical frequency. When the frequency is beyond the critical frequency, that means the circuit operation frequency is much higher than the critical frequency, gradual enhancement in the mean time failure happens along with the frequency increment. Now, what do you mean by the enhancement in the mean time failure? That means the point of the failure go away from the origin, that is x=0 or time=0 point. In last episode, I have explained this mean time failure with the infographics. There I have explained this. So that point of the MTF will go away further. Such phenomenon results in improved effectiveness of the damage healing due to the reverse stress period. In a AC, right, when the swing is in opposite direction in the two part of the half cycles, the direction of the electron wind is completely opposite. So in one case, the electron will try to create a void, and in the another part of the swing, it will try to heal it. So this is the nature, because the direction of the electron wind is completely opposite, and hence the momentum transfer to the metal ions is also in a different direction. So if that momentum transfer is in different direction, then definitely in first half of the swing or in the positive swing, the void, whatever amount it was getting created, in the second half, that means the opposite swing, those voids be healed a bit. At the beginning of the positive and negative pulses, atoms and voids start to migrate along the grain boundaries or interfaces. This migration is able to recover with the opposite stress. Now here you can see the term stress, which I explained few slides back. And this stress means when a circuit is under operation, right, that particular circuit operates for a long time, and hence any of the stress could happen that I have explained in the last slide. A shorter stress period means a relatively smaller displacement of atoms and voids, which are easily healed. Material migration in one direction can partially migrate back to its original location under beneficial condition. Consequently, the interconnect suffers less damage from the electromigration under AC conditions. Here we are talking about the bipolar AC waveform. That means in the two half of the AC, one swing is completely in the opposite direction. Means that in the first half, if the swing is in the positive y-axis, in the second half, it will be in the negative y-axis. In such condition, the last point applies. So folks, we are done with this particular slide. Let's move on. We continue here with few more points. Under ideal conditions, the magnitudes of both current and time in the positive or negative half cycle, then no electromigration effect would takes place. So this is a very ideal condition. However, in real condition, there will be a little bit difference. Within a quite high frequency range, the damage healing process can overcome all defects which are brought during the other half of the period, and there should be no EM at all. Consequently, the MTF would go to infinity. So if you can recall the slide in the last episode where I have shown the infographics about the shifting of the MTF point, that point here in this particular bullet, as per the condition, will move towards the infinity. The lifetime of a metal or wire carrying alternating currents AC is significantly longer than the wire that with the direct currents DC due to the damage healing properties of the AC waveform that so far we have discussed. However, in high frequency AC current density has a DC offset. The DC component will determine the actual EM lifetime. In addition to this, the thermal stress due to the Joule heating alone will contribute to the degradation in the metal or via and lifetime based on the RMS current density. So even though you can see that the AC waveform has its own healing way of the void creation, however, its associations, the DC component or the Joule heating, both these things will contribute for the damage. The temperature gradients alone brings the metal ion flux divergence and cause the failure. So the void which we are getting earlier moving due to the electron wind, due to the momentum transfer to the ions, they will get the energy from the thermal conditions, and under the thermal stress, this void creation will get enhanced and damage will happen to the metal or via. In addition, the EM effect that is coming from the DC part of that particular AC will contribute to this damage. That's how the overall damage happens in an AC circuit. So folks, we are done with this particular slide. So let's move on to the next slide. Conclusion. At lower frequencies, on each half cycle, metal ions influenced by electron wind have ample time to migrate far out of the hot region into the cooler adjacent wire segments. Consequently, their thermal motion is largely frozen out upon reversal of the electron wind. Thus, damage is added up over the time elapsed. At higher frequencies, the switching time for the electron wind force direction is reduced. The hot junction can begin to experience reversible ion movement under reverse electron wind. However, high frequency AC current density has a DC offset. The DC component will determine the actual EM lifetime. Further damage is caused due to the accumulation of the Joule heating. We are done with this particular slide, so let's move on.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will do an introduction to the concept of the ground bounce. Next, we will do the correlation of power and ground bounce. Next, we will walk through a couple of techniques through which we can mitigate the ground bounce. Next, we will highlight the power gating technique, which is one of the most used mitigation techniques for ground bounce. And our episode will end at this point. Here we are done with our menu for today. Without any further delay, let's begin. Introduction. Power supply noise and ground bounce can cause considerable path delay variation in VLSI circuit. Generally, we have two lines, that is VDD and ground, right, in any VLSI circuit. So noise in either can cause path delay, that is delay in the timing in any of the VLSI circuit. And if there is a delay, then it affects the performance of the chip. So here is the grave importance of dealing with the ground bounce. Ground bouncing noise is the primary cause of false switching in high-speed circuit and a major cause of poor signal quality. This is the immediate impact. This one is the ultimate impact, and this is the immediate impact of the ground bounce. Through the shared ground or power distributed network during the wake-up event, the bouncing noise generated in one of the power domain is transferred to the active block, which will flip the logic states. So in some episodes, I have discussed about the power domain. I'll provide the link in the description. Please watch it for understanding the power domain. Now, when one particular power domain is in the sleep state, that means we have several blocks, right? When a particular block is there and it is waking up because of the external signal, or maybe some sequence of the signals that is already there is coming from a particular block. So during that particular event, these things can go, this false switching and noise, all these things from one block to the another. And it can flip the logic gate state. That means it can flip 1 to 0 or 0 to 1. That means it actually disturbs data transmission inside among the different blocks. And definitely that will be a functional failure. This noise is known as ground bounce noise. Whatever we have talked about, right? All these effects are summed up as ground bounce noise. Generally, any disease is detected by the symptoms. So we have talked about the symptoms, and the disease is a ground bounce. Major component of the circuit noise is inductive noise. Now we are entering into the classification. What type of noise they or impact they within the circuit and impact the circuit. There is an inductive noise. It is a critical and challenging design task to control the amount of the inductive noise that is transferred into the power planes. Here we are done with this particular slide. Let's move on to the next slide. In the next slide, we are still continuing the introduction. Package pins, bounding wires, and on-chip IC interconnects all have parasitic induct. We were talking about one of the root cause, which is the inductance noise, right? So where does it come from? It comes from the parasitic induct. Like we have parasitic R and C extracted during the SPEF extraction or DSPF extraction. Similarly, yes, we can also extract the inductance. That inductance does stay within the VLSI chip, and this causes ground bounce. When an inductor current experiences time domain variation, a voltage fluctuation is generated across the inductor. Now, what is a time domain variation? That means we have a transient behavior. Any circuit behavior that is changing with time that impacts inductor. Because if you remember your class book, right, there is a transient response for the both RC circuit and the RLC circuit. When the RC and L coexist in the VLSI chip, obviously the transient effect will impact all of them, and in return, we will generate some bad effects, one of which is the ground bounce. This voltage is proportional to the inductance of the chip package interface and the rate of change of the current. We are very specific here, nothing more to say for this point. As a result, when the logic cells in a circuit are switched on and off, the voltage levels at the power distribution lines of the circuit, it is also very plain and simple. If we have a noise, it is going constant, right? If we have a noise going like that, obviously this level will be impacted by the superimpose of the noise, that is the stating here.
This inductive noise, sometimes referred to as the simultaneous switching noise, because it is most pronounced when the large number of I/O drivers switch simultaneous. Now we are talking about the chip packaging where the IOs are there and the inductance comes from that particular point, and we coin a term called simultaneous switching. And it is nothing but the inductive noise, right? The IO pads or connection of the wires, they are there, they exist there, and that wires interconnects, they also contribute to. So, apart from the parasitic inductors coming from the silicon, you also have the IO pads, and from where the inductance behind the ground bounds does exist. Now here we are talked about the general concept of the ground bounds through the introduction, and we have given some of the background reasonings why the ground bounds happen. So let's move on to the next slide. We are done here. Correlation of the power and ground bounds. As the noise comes in, the noise affects both the power rails, that means the VDD as well as the ground. So how does it looks? It looks like this, and we're explaining here. So this is our VDD line, this is our GND line, and the noise is occurring there, we generally refer to it as the voltage drop, and if it is impacting the ground line, GND line, then this noise will be termed as ground bounce. The ground bounce is nothing but ground noise. Power bounce is the noise glitch on the power line, is the power bounce. When ground bounce and the power bounce are in phase, is the common mode noise. They will not affect the local logical cells, but will degrade the signaling between the distance transmitter and receiver, that is TX and RX. Generally, if these two are in phase, this one and one is in phase, it will not impact the immediate circuit. Rather, if we have a block here, which is the TX, right? TX, and we have a block at other point of circuit, RX, and right, the VLSI wirings inside a chip runs in the length of kilometers, although the chip had all the routing. So when a trans signal is going on, if we interpret the signal here and here, these two signals here and here may show a difference because of the ground bounce, the power bounce noise. So that in turn impact the signal exchange between the TX and R. When ground bounce and the power bounce are out of phase, differential mode noise, out of phase, they adversely affect the local logical cells, causing jitter in timing circuit. When these two are out of phase, not in the same phase, they will be impacting the local logical cells. That means which are there maybe in the path, or maybe here is our TX, right, and here. This path, it may not be where at all, and there might be circuitry which is processing the signal before going to the RX, and also it can impact the logic cells here, right? Because we don't know how our chip is there, how it is designed. We are giving a general guideline here. You are the best judge when you are working on your chip. You can actually interpret these concepts into your theory. Ground bounce mitigation techniques. Many design techniques have been used to reduce the effect of the ground bounce, such as power gating technique, stacking power gating technique, various empty CMOS technique. These are nothing but multi-threshold CMOS, adding decoupling capacitors, that is decap, having separate ground buses for IO buffers and internal circuitry, widening ground interconnect buses, evenly distributing circuitry among power and ground. Previously, in couple of slides, we have talked about the ground bounce and the visual representation of it and the in-depth impact of it. And here we have listed couple of methods which are used in the VLSI design area for different kinds of needs and different kinds of circuitry to combat as this is a short episode about the ground bounce, we are not able to accommodate all of these techniques and their details. In case you need them, just please write down in the comments. We will create more FAQ episodes per topic basis. That means if you are asking, we will create for each of them here in this page. However, we will touch base one of the most used technique, that is power gating technique. We're done here. Let's move on to the next slide. Power gating technique. We are touch basing here in this particular slide about the power gating technique, which is one of the very popular method to tackle with the ground bounce. Power gating technique is widely used in VLSI to significantly block the leakage currents in standby or sleep mode. Here, a sleep transistor is added between the actual ground rail and actual circuit ground, also known as the virtual ground. Since we are giving a brief description, we are not diving deep, we are just touch basing, so have to survive with all these short and sweet descriptions. And to understand from these 2 points, right, this method is for the sleep mode, right? And how it is done: first we add a sleep transistor between the actual ground rail and the actual circuit ground, also known as virtual ground. During the sleep mode, this device is turned off, cut off the leakage path from the ground. So it cuts off the ground path, hence no noise is coming from ground, and hence the power and the ground bounce, but mostly the ground bounce is blocked, right? Here, power supply causes virtual ground rail to charge up close to supply voltage VDD, which in turn suppresses the leakage. This is another part of this. However, when the sleep transistor is turned on, the virtual ground rail is restored to its act. This way, the restoration happens. That we open up the channel again. This way, we control the entrance of the ground bounce noise into a particular block or into couple of blocks. Here we are done with this particular slide, giving you a brief description of the power getting technique. Let's move on to the next slide.
Now let's take a look at the pointers we are going to discuss in today's episode. First, what is signal integrity in physical design? Second, common signal integrity issues in PD. Third, what is crosstalk? Next, classification, rise and fall glitch. Then classification over and undershoot glitch. Next, what impacts glitch? Range of safe and unsafe glitch, crosstalk delay basics, negative crosstalk delay, then positive crosstalk delay, effects of crosstalk delay, crosstalk and RT level estimation, and finally mitigation methods of crosstalk. So let's move to the first slide. What is signal integrity in physical design? In digital electronics, a stream of binary data is transmitted as signal and it represented as voltage or current waveform. All signals are subject to noise, distortion, and loss. In digital electronics, we use digital signals, that is, these signals has two states, one is 0 and one is 1. And in any practical system, signals goes through noise, distortion, and loss. Signal integrity is the measure of quality of a signal as it travels from one point to another point. So in signal integrity, what we discuss or what we measure is that in a practical and realistic world, when a signal travels in a system, how much its quality degrades within the system while it's traveling from one point to another point. So obviously, when we discuss signal integrity, we must consider the reasons which make quality of signal degrade. Now, signal integrity is crucial as it ensures whether the data transmission is accurate, reliable, and immune to unwanted effects such as noise, distortion, and reflections. Now, when we talk about digital electronics, actually not exactly a single voltage value is considered state 1 or single voltage value is considered as state 0. There is a band of voltage. If the voltage remain within this to this value, we will call it 0 state. And if it's above some certain value and below some certain value, that is another a band of values, we call it state 1. So when a signal in a realistic world goes through this noise, distortion, and reflections, so obviously its value gets changed. We must ensure how reliable the data is transmitted. Suppose due to impact of noise or distortion, value gets decreased. If a state 1 is getting transmitted and then value degradation happens and it become below certain level, so after that it will not get considered as state 1, it will become state 0. So it's very important to understand, to analyze signal integrity issues to ensure quality of transmitted data. Now, if the signal faces above mentioned unwanted effect continuously, it can lead to erroneous data transmission. That which I have just mentioned about that. The continuously, if a signal gets distorted, doesn't remain in the same state as we are transmitting. So it's a diagram from driver, signal is sent and receiver will catch it by that time. This distortion, noise, distortion and reflection, these can happen. These three effects, noise, distortion and reflection, this thing can affect in this part. And when it goes to this receiver, so maybe it might not reach in the voltage level it's desired here. So these are the points we have covered. This point, what is signal integrity and why signal integrity is crucial, and what will happen if some degradation happens. So this is the ideal voltage form, and in real world it doesn't like that. Neither it's so straight here. The signal integrity mainly deals with timing and quality of the signal. Whatever circuit and modules we design, timing closure is there because we deal with sequential components in the circuit. So their performance is time dependent, depends on clock. The signal get delayed, that timing violation occurs, and quality of the signal, magnitude of the voltage that can differ from what is expected. Signal integrity is both an interconnect level problem as well as system level problem. Interconnect, obviously signal integrity interconnect level problem because there are so many issues comes from interconnect level like crosstalk, ohmic voltage drop. These all comes from interconnect level. At the same time, it's system level problem also. Any design have some signal integrity problem, and they generally do not interfere with the functionality of the system by creating excessive until the system deals with high frequency signals. So as we move to high frequency operation, the problem become more severe. No system is ideal. So signal integrity issues are there, but in a manageable amount. Distortions and noise are there. That's why we define noise margin. Actually, this noise margin calculation is within the design thing. So people always design keeping in mind about noise margin and all. If it remains within the noise margin, it will function that way because it's not an ideal system. It's a real world system. But whenever we are at high frequency signals, we are dealing with them. That problem really interfere with the performance of the system. High frequency state of art ICs are, for them, signal integrity issues are more severe. Let's move to the next slide. Common signal integrity issues in PD. In a digital system, signal integrity analysis are done at 3 levels. First, logic level, second, circuit level, third, EM field level, that is electromagnetic field level. In logic level analysis, so 3 level we do the analysis. Logic level, circuit level, and electromagnetic field level. In logic level analysis, signal integrity issues can be easily identified. Circuit level signal integrity analysis is based on interconnect modeling. Interconnect modeling we have discussed in one of our previous episode. Interconnect modeling, and there we calculated delay due to interconnects and all. Here we try to model a piece of interconnect including resistive, capacitive and inductive effect. That is parasitic effect and impact of parasitics, how the interconnects behave and all. And at electromagnetic level, most of the signal integrity issues are reflection, crosstalk, ground bounce, etc. Reflection, we have talked about termination of transmission line and reflection. Crosstalk also we have discussed in the first episode of this series a little bit. Today we will elaborate those points. And ground bounce, we have a separate episode on that. Link is provided in the description. Both link of the video and link of the article in techsimplifiedtv.in. So you can watch the video, you can read the article. This reflection issue, crosstalk issue and ground bounce, these are electromagnetic level issues. Now circuit level analysis obtain a good signal integrity solution at low frequency, whereas for state-of-art ICs with small dimension and high operating frequency, EM level analysis is more accurate to describe the effect. Since we have moved to more smaller dimension devices, so in state-of-art ICs which are operating at high frequency, for them analysis is basically a little bit tougher compared to the previous generation ICs. Now SPICE tools are used to check signal integrity in nodal analysis, and they solve voltage and current in RLC circuit. So SPICE tools are used to check signal integrity in nodal analysis, circuit nodal analysis they do to check signal integrity issues, and they solve equations in RLC circuit. So these are the major issues concerning signal integrity. One is crosstalk delay, crosstalk noise. Today we will discuss about these two. And ringing and ground bounce. Ringing we discussed in last episode. Ground bounce, the link of both the video and article is provided in the description. Now, IR or voltage drop in power line, we mentioned about it in very first episode. And electromigration, we have separate 3 episodes, link of video mentioned in the description. And finally, manufacturing related issues that if not addressed can lead to chip failure, that is antenna effect. Antenna effect, on antenna effect also we have a video and article, links are provided in the description box. So today we will talk about these 2. So there are 6 effects. Now let's move to the next slide. So what is crosstalk? Crosstalk is undesirable electrical interaction between 2 or more adjacent nets due to capacitive coupling. Switching of signal in one net, which is called aggressor net, can interfere neighboring net, that is called victim net, due to coupling capacitance. This is called crosstalk. This one is aggressor net and this is victim net. Switching happening in this net. Switching happening in this net, and that switching due to this coupling between these 2 nets, the coupling between these 2 nets, logic state of this net is changed due to this net. So this is aggressor net and this is victim net. Aggressor is a net which creates impact on the other net. Victim is a net which impacted by aggressor. And crosstalk has 2 effects, crosstalk noise and crosstalk delay. Crosstalk noise or crosstalk glitch. Signal transition in aggressor causes a noise bump or glitch on victim net. This is known as crosstalk noise. Crosstalk noise or glitch or bump occurs when aggressor net switches and the victim nets remain in a steady state. So crosstalk noise or glitch occurs in victim net when victim net remain at steady state, steady 0 or steady 1, and aggressor net is switching from 0 to 1 or 1 to 0. Another is crosstalk delay or crosstalk delta delay. Signal transition in aggressor creates delay in output transition of victim. This is known as crosstalk delay. Crosstalk delay occurs when both aggressor and victim net switch together. So we are done with this slide. Now let's move to the next slide. Now classification, rise and fall glitch. We have discussed about crosstalk noise or glitch. Now let's see which kind of glitch happens when. Now rise glitch. This is the diagram. This is gate 1, gate 2. This is the aggressor net as mentioned. This is gate 3, gate 4. This is the victim net as mentioned here. Now this is the coupling capacitance between these 2 nodes, and this is aggressor node basically, and this is victim node. And C1, these are capacitances by which this net is grounded. Victim net is at a steady low. Now this is the condition, victim net is at the steady low. Its logic state is not changing. Aggressor net is switching low to high, high to low, so low to high. So output here it is low to high. So gate 1 input is 1 to 0, and obviously gate 1 output will change because we can see it's a NOT gate. So 0 to 1, obviously A, it's connected with a resistor, so it's at node A, the state will change from 0 to 1. And since this node V is at constant 0, and there is a mutual coupling capacitance between these 2 nodes, so node A will try to change the state of victim net, that is node V. So node A at changing at 0 to 1, CM starts to get, that is mutual capacitance starts to get charged. Output of gate 3 and node V at 0. Leakage current through that's coupling capacitance create a rise in voltage glitch at V. So though it's at this point it's 0, so if we measure voltage across this resistor, although it should be at 0 state, there a glitch or spike or bump occurs. That is the rise glitch. Now comes fall glitch. At fall glitch, victim net is at steady high. Steady high at, we can see, and this aggressor net is switching high to low. So input it's low to high. So obviously here it will be high to low. So point A is high to low, node A. And at node V it's constant 1. Again, output of gate 3 and node V at 1. Node A switches from 0 to 1 and node V at 1. Leakage current flow through CM from V to A. Previous case it was flowing from here to here. Now it's flowing from here to here and create fall in potential at V. Leakage current is flowing from this direction V to A. So although it should remain at constant or steady high one state, voltage falls. That is fall glitch. So we are done with the slide. Let's move to the next slide. Classification over and undershoot glitch. Well, overshoot glitch, victim net is at steady high and aggressor net is switching from low to high. So when aggressor node is switching from low to high and victim is at 0, that is rise glitch. If victim is at steady 0, that is here at steady 0, and aggressor is pulling it up, so there will be a glitch, but that is not crossing the maximum allowable value, right? And when the aggressor node is high to low, moving high to low, and the victim is at steady 1, that is fall glitch. This one, it was at high and then going down, pulling it down. So aggressor net is pulling it down. So although it's within the range, what happens in overshoot glitch? Overshoot glitch is the aggressor is moving from low to high, although the victim is at steady 1. So it is already at steady 1, and if the aggressor net pull the voltage state of victim, then from 1, if it's move upward, so it is crossing the maximum limit. That is overshoot glitch. Overshooting. And opposite happens while it's in case of undershoot glitch. Victim net voltage is at steady low, it's already in low, and aggressor net is switching from high to low. So when it's moving from 1 to 0, it will pull down the victim net, inducing undershoot glitch by taking the victim net voltage below its steady low. It's even moving from below steady low, below the allowable low. So that is undershoot glitch. So we are done with the slide. Let's move to the next slide. What impacts glitch? Not all glitches are considered unsafe for circuit operation. Safe, unsafe decided by glitch height. Now, glitch magnitude or height of the glitch is determined by few factors, such as value of coupling capacitance. Magnitude of glitch would be higher if the coupling capacitance value is higher. Slew of the aggressor net. If the output drives, slew means how fast this signal, ideally we take like this, but actually it doesn't happen. It takes, there is no instantaneous thing, so it will be something like this and that. This how fast, this rate of change, that is called slew. So if that is very sharp, then the driver of the aggressor net is really strong. It has high driving strength. So slew of a aggressor net defines how strong the driver of that net is. If output drive strength of cell that is driving the aggressor net is high, slew of aggressor net is faster. The faster slew of aggressor net results in high magnitude of glitch. That means the aggressor net is more powerful compared to the victim net. More powerful aggressor net is, it will impact more, the glitch will be higher. So drive strength of aggressor and victim net. If driving strength of aggressor net is high, the magnitude of glitch will be higher, whereas if driving strength of victim net is higher, it's not easy to influence it. It's a comparative one. If victim net grounded capacitances are small, then magnitude of glitch will be large. So these are basically 4 factors which impact the magnitude of the glitch introduced in victim net by aggressor net. Now, what will happen if multiple aggressors are present? So when multiple aggressors are present and they switch concurrently, the impact on victim net is get added. Suppose there are multiple aggressors, multiple aggressor node are there, they are impacting one victim net. Now concurrent switching is an ideal case. All the nets are switching at the same time. That's a ideal case. In reality, what happens, suppose there are 4 aggressor net, 2 switches, one is switching and then after few nanoseconds some other net is switching. So for that time period, any 2 or any 3 or multiple, depending on the number of aggressor net, they are active. Suppose if that is the time, suppose for one aggressor node is steady 1, then after some time another one, when before it's completely switched, go to 0 state, another net is getting switched on. So switching happens. So in analysis of such situation, what happens? So the impact on victim net depends on the contribution of each aggressor node on that victim net for a time window. That time we will consider analysis depending on time window. For which time window, how many nets are active on that victim net or switching. So depending on that, get added. In this case, we do the analysis based on time window. So we are done with this slide. Let's move to the next slide. Range of safe and unsafe glitch. We said that not all glitches are unsafe. Some are safe also, depends on magnitude. So safe glitch has no effect on logic state or victim net. Glitch is there, but it's not impacting. So we'll not get bothered by it. If glitch height is less than noise margin low, NML a safe glitch. So this is the noise margin low. This is the range of NML and this is the range of NMH. Any glitch below this maximum, this is the range of NML, that is noise margin low, we call it safe. And here we can see that noise margin high level, it has within that range, it's obviously unsafe, and this is potentially unsafe. Glitch height is greater than noise margin high, unsafe glitch, and if NML is less than glitch height, less than NMH, an unpredictable case, this one potentially unsafe. Noise margin is a parameter that determines the allowable noise voltage on input without affecting output. How much noise could be there in input so that it doesn't affect the output? It's there, but it's not impacting. That's the noise margin. So noise margin, or basically immunity, expressed in terms of noise margin low and noise margin high. What is noise margin low? That is VIL minus VOL, that is difference in magnitude between the maximum low output voltage of driving gate and the maximum input low voltage recognized by the driven gate. This is the driving gate and this is driving this driven gate. So difference in magnitude between the maximum low output of this driving gate and the maximum input low voltage recognized by the driven gate. This is the calculation. And NMH is difference in magnitude between the minimum high output voltage of the driving gate and the minimum input high voltage recognized by the receiving gate. This is the calculation. So we will go by this one, that the noise level must be within this safe zone. So we are sorted. As long as noise or the glitch above this line, we are not really sorted. There are reason to get worried. And now let's move to the next slide. Now crosstalk delay basic. Till now we have talked about crosstalk noise. Now crosstalk delay. Crosstalk delay occurs when both aggressor and victim net switching. So in case of crosstalk noise, victim net was always at steady state. It was not switching. When both aggressor net and victim net, they both are switching, what will happen? So that effect is crosstalk delay, and that analysis is crosstalk delay analysis. Crosstalk delay occurs when both aggressor and victim net switching, and these may lead up to setup and hold timing violation. It increase or decrease the delay of a cell depending upon the switching direction of aggressor and victim nets. In case of crosstalk delay, we will discuss about that aggressor net, which direction is going, that is from 0 to 1 or 1 to 0, and victim net 0 to 1 or 1 to 0. Like same, they are switching in same direction, low to high or high to low, or opposite, like one is switching from 0 to 1 and another is from 1 to 0, that is high to low. So we are done with this slide. Let's move to the next slide. Now negative crosstalk delay. The small mistake, this waveform would be like this. It is written properly, but it's not. So negative crosstalk, aggressor and victim net switch in the same direction. Both net switches from low to high. So here also it's 0 to 1. Here also it's 0 to 1. There is a small mistake. I have corrected this one. If aggressor has higher driving strength, transition will happen faster. If this aggressor net is strong compared to victim net, then its transition will happen faster. We are assuming that if aggressor net has more driving strength, then this point will be at higher potential compared to V. So node A will try to pull up the victim node. Transition of victim node will have a bump. So it's moving. Otherwise, without any interruption from aggressor node, its transition should have like this. Now, point A or node A is pulling the voltage or the logic state of this node V, so it will pull it. So here the voltage get pulled up, and with its natural slew, it would have been transition would have been at this zone. This transition just happens before, so there is a delta shift. So actually victim net will reach from 0 to 1 earlier and transition time will decrease. And crosstalk will decrease the delay by delta, and the new delay will be d minus delta. So usually it would happen like this. It would have this transition time would have taken. Because of action of this aggressor net, this transition is happening earlier by a small time window delta. Here crosstalk is actually decreasing the transition time of victim net. So it's called negative crosstalk because it's reducing the time. Now we will move to positive crosstalk delay. Here, aggressor and victim net switch in the opposite direction. Here it's 0 to 1 and this is moving from 1 to 0. Yeah, here also a small mistake. Sorry, I have not noticed it earlier. So here aggressor net and node A switches from 0 to 1 and node A will try to pull up node V. V switches from 1 to 0. It was 1 and now it's moving to 0. So transition of victim node will have a bump. It's without any interruption. It would have been like this. And since it's trying to pull it, there will be a bump. If there is no interruption, it would have transitioned here. It will reach 0. And since it's pulling up, this victim net will reach 0 a little bit later. That is delta. That is this delta time is added with the delay. This is called D plus delta. So it's actually increasing. Positive. It's increasing the delay. We are done with this slide. Now let's move to the next slide. That is effects of crosstalk delay. Effect on clock tree. Crosstalk can unbalance a balanced clock tree. Crosstalk delay can change the latency of balanced path and the clock tree become unbalanced. Suppose different branch of clock tree they are balanced, they will reach and perfectly time, and some in one path and between one path delay is introduced. So obviously its total timing, it will not match with the other path. So our balanced clock tree become imbalanced. Now effect on setup timing. Effect on setup timing. For setup timing, data should reach the capture flop before the required time of capture flop. There are two flip-flop. One is launch flip-flop. One is capture flip-flop. That is launching clock path. That is capture clock path. And this is the common path. So suppose here, there are some cells and drivers are here. We have shown that with 1, 2, 3, 4 and 5, 6. If delay is include here and it's a positive delay, so it will reach later. If so, for a setup timing, the condition is that the data should reach at the capture flop before the required time of capture flop. That flip-flop should not wait. Data must flow from here to here. So data is ready. When clock reached, the state will change and it will reflect here. So if delta delay is positive delta delay introduced here, it will reach later. So there will setup violation can occur. Another one is if delay of this clock path reduced. So it will be ready. This clock is ready, although data has not come here. It will come its natural time and it's reduced. So it will be there, and our prerequisite is that data should be present at here before the clock comes. So there are two things. One, increase of delay in data path or launch clock path, and decrease in delay on capture clock path. In these two cases, setup timing violation can happen. And now effect on hold timing. For hold timing, data must be stable for minimum amount of time after the clock's active age. So for hold timing, data must stay there. So if decrease of delay in data path and launch clock, if this clock reduced, this data path reduced, and increase of delay in capture clock, and this clock comes later, then hold violation can happen, because for hold timing, the data must be stable after clock's active age. Otherwise, the flip-flop give ambiguous data. So this delay is reduced. It's already reached there, and this data path, this clock is getting delayed. It's getting positive delay and it's getting negative delay. So it will cause the decrease of delay in data path and launch clock, and increase of delay in the capture clock will create the hold violation. So this way, crosstalk delay can impact setup timing and hold timing. We are done with this slide. Now let's move to the next slide. Crosstalk and RT level estimation. This is basically high level synthesis, logic synthesis, and physical level synthesis. These are three level of abstraction used in this VLSI design methodology. So here we will talk crosstalk and RT, that is register transistor level estimation. How we can do estimation at register transistor level, and why should we think to do it? Because we are doing at physical design. So each design stage has its own model for crosstalk. Trade-offs exist between accuracy and complexity of this different model. So more accurate, it's more complex and time consuming also. The cost involved in detecting errors and correcting them increases by a factor of 10 between each abstraction level as we move top down in ASIC design flow. So as we move every step, so the cost involved in correcting and detecting errors increases by 10 times. So if we can detect any error or correction method or correct anything to correct at higher abstraction level, then it's less expensive. Detecting crosstalk sensitivity at gate level 0 is 10 times more expensive than detecting at RT level. Some level parameters have direct impact on crosstalk noise problem, and those cannot be accurately determined at higher abstraction level. Such parameters are the position of models relative to one another can be determined after floor planning. So we cannot assume it at behavioral level. Then only from floor planning we can assume that. So another is the route of each wire that can be determined after floor planning only. We can only determine it. At behavioral model we cannot do it. The aggressor of a given wire in both the horizontal and vertical planes can be determined after floor planning. So we cannot do at higher level of abstraction. Thus, high level crosstalk estimation includes mathematical and statistical process. And if we can do a little bit of our analysis at behavioral level, then it will be cost effective. It will be easier for us. There are so many research papers and research theses are there, and it's mostly based on statistical and mathematical methods. We will not talk about it detail because our concentration is only on crosstalk in PD. So we are just trying to give you an idea that with even existing models and methods, some researchers are always there to find a new way, making it more cost effective, more time effective. So we just to give an idea about that, we have introduced this slide. So we are done with this slide. Now let's move to the next slide. So mitigation methods of crosstalk: increasing the space between aggressor and victim net. If the distance between aggressor and victim nets is increased, the mutual inductance or mutual capacitance between them will decrease. Insertion of shielding net. Inserting a net which is connected to VSS VDD between critical aggressor and victim net is a method. This new net between works as shield, and this process is known as shielding. Process of shielding stops direct coupling between aggressor and victim net, and since the shielding net remain at constant potential, chances of crosstalk is completely waived off. Upgrading drive strength of victim cell. If we upgrade the driving strength of victim cell, it will not be easy to change its logic state. Downgrading the driving strength of aggressor cell. If we downgrade the driving strength of aggressor cell, its impact on victim cell will decrease. Buffer insertion. Insertion of buffer effectively boosts the victim net strength. Guard ring. Guard ring in the substrate used to shield the analog circuitry from digital noise. So we are done with this slide. That's all we had for our today's episode, that is signal integrity and crosstalk in physical design. We will conclude our episode here today.
Hey guys, welcome back to the computer screen, and in today's episode we are going to discuss the below points. Vertical cross section of a chip addressing the FEOL, MEOL and BEOL layers, antenna phenomenon and its infographics. Next, we will cover the semiconductor CMOS process and the various plasma processes that are being used. Next, we will go through antenna damage action replay and infographics to understand the damaging process. Next, we will cover the physics happening behind the antenna phenomenon, and we will explain a ratio which is called the antenna ratio, closely related to the physics happening behind. Next, we will talk about the present VLSI methods of antenna issue mitigation and some infographics to understand the mitigation methods. That's the menu for today, and without any further delay, let's begin. Vertical cross section of a chip. Here we are using the vertical cross section of a chip. This picture has been taken from Wikipedia. Here I will point out the different layers. First one is the FEOL layer. Here the transistors will reside. Next, there are few other layer components which are very closely spaced with the FEOL, like contacts, etc. Those are called the MEOL layer. And the entire metal routing process through metal and via stack are under the BEOL layers. Now, the reason of keeping this slide is to make an impression in your mind about the different layers, starting from the silicon surface, reaching up to the maximum metal layers. Shortly, you will understand the importance of this slide in upcoming slides. We're done with this particular slide, so let's move on to the next slide. What is antenna effect phenomenon? At present, chemical etching has been completely replaced by hot plasma etching. Plasma-related processes are used for CMOS process flow or etching and deposition. The gaseous plasma contains charged particles inside. This charge gets transferred to the under construction floating metal routes, which may be connected way below up to the gate areas of a MOSFET. At the same time, such metals may not be connected to any diffusion areas in the FEOL zone. Such metal wires act as antennas, that is, charge receptors that pick up electrical charge from the plasma gas. So in this line, you understand the meaning of the word antenna, because here the metal route is acting as an antenna to pick up charge from the plasma environment. Charge accumulation on the metal strip is proportional to its length. That means the larger the metal area or the length is bigger, the more the charge gets accumulated onto it. So here we are done with a short and sweet description of the antenna effect phenomenon. Let us move on to the next slide. Antenna phenomenon infographics. Here we will take the help of our infographics to understand the phenomena during the fabrication process. Here is our silicon substrate, source, drain. Here is our shallow trench isolation. Gate oxide is grown here. On top of that, poly is grown and connected to the metal one. And after the metal one deposition, we have to etch the metal one as per the mask. So the plasma is coming down from the plasma chamber on top of the metal one for the etching process. And in this gaseous environment, many charge are getting accumulated on the metal one surface. Once this amount of charge is sufficiently high, it causes a breakdown of the gate oxide insulator and the charges pass on the silicon. This infographics helps you to understand the antenna phenomenon happening live during a CMOS process. We're done with this particular slide, so let's move on. What is antenna effect phenomenon? We will go through some more points to dig deeper inside the antenna effect phenomenon. Aforementioned metal wires built up high potential difference on the metal side through the piled up charge. As a consequence, high electric field builds up across the gate oxide of the metal oxide semiconductor, that is MOS structure of a MOSFET. Sufficient amount of charge creates a percussion path to the oxide for the drainage of the charge. This percussion path is a small path that is created by high amount of charge, and this is just a beginning. Severe drainage lead to the gate oxide breakdown, consequently damaging the MOSFET. Alternatively, in less severe drainage, non-damaged MOSFETs or electron generation, abbreviated as HCI, may take place, causing faster aging related to the performance degradation of the MOSFETs. Those MOSFETs which are not getting damaged during the application process due to the antenna phenomenon, even here a percussion path may be existing there where low amount of charge is getting accumulated, and these are causing the hot electrons gather in the oxide, causing the aging. That means performance degradation of the MOSFET in the long run. We are done with this particular slide. Let's move on to the next slide. Now, in this slide, we will talk about the semiconductors. It's a brief walkthrough of the CMOS process. So here is a infographics. So first, we do the deposition. Then we use a photoresistive coating. We use the exposure, developing, etching. I have kept a green highlight here to make it separate from any other steps. Then there will be ion implantation, and then there will be the stripping of the remaining mask. So this is a cyclic process. It keeps on operating for formation of the metal routes in the BUL region I have shown in the first slide. The FUL and MUL obviously go through this process. However, the BUL goes through this cyclic process several times, and the step marked in green, etching, is the process step where we are using the plasma, and here the chances of getting the antennas. Don't think that antenna is happening to only metal one. It can happen in any of the metal layers as shown in the picture where I have marked the BUL layers. We're done with this particular slide, so let's move on to the next slide. Different types of plasma process. Now, this is going a bit deep in the semiconductor CMOS process. Here we will talk about 3 different plasma process, and that will enhance your knowledge about how the plasma process is done and what is the respective importance. And we will correlate these things to the antenna damage later on. Conductor layer pattern etching process. Here the amount of accumulated charge is proportional to the perimeter length of the conducting metal strip in above. Etching process splits a conductor layer plates into multiple routing patterns. Perimeters of the pleated routing are directly exposed to plasma. Here we have just touched base one particular type of plasma process. Next, etching process. Here the amount of accumulated charge is proportional to the area of the conductor layer pattern. Etching process remove remaining photoresist layers after etching processes of a conductor layer. Area of conductor layer pattern is directly exposed to plasma. Can you spot the difference? In the first one, the perimeter was exposed to plasma. Here the area is exposed to plasma. Next, contact etching process. Here the amount of accumulated charge is proportional to the area of the total area of the contacts. Contact etching process dig holes between two conductor layers. That means we have metal 1, metals 2 stack, right? We have to dig a hole through it to make the via, right? So there is particular etching process is used. Here the area of all the contacts on the lower conductor layer pattern is directly exposed to the plasma. Now you're familiar with the three different plasma processes that are used in the semiconductor CMOS processing. And in this particular process steps, the plasma affects the metal layers and may create the antenna problem in different ways. We're done with this particular slide. Let's move on to the next slide. Antenna damage action replay. Metal or via stacks are built layer by layer. First metal 1 is deposited and all unwanted portions are etched away by the plasma etching. Then the metal geometries, when they are exposed to plasma, can collect the charge from it. So at this point you may recall the three different type of plasma exposure that I have just talked about in the last slide. Once metal 1 is completed, via 1 is built and then metal 2 and so on. So with passing stage, the metal geometries can build up static electricity. If the charge collected is large enough to cause the current to flow to the gate, this can cause the damage to the gate oxide. Long metal lines are prone to such failures, ending into fabrication yield. That means if the antenna damage happens, the chips that are coming out of a batch, huge amount of chips will be defunct. So those chips which has gone through the antenna damage, those will be non-functional. That means we have a higher yield entire fabrication batch. So we are done with this particular slide. Let's move on to the next slide. Action replay infographics. Here is our expectation. Here we'll go through the expectation in a semiconductor process. Ideally that should happen. Here is our diffusion layer and here is our gate oxide and poly from a MOSFET. Here we are reaching up to M1 and here also we are reaching up to M1. Then we are reaching up to M2, which is connecting the diffusion zone up to the gate area. This is a kind of wiring that is inside the circuit and we expect this thing to happen as shown in the picture to the various process masks in the semiconductor fabrication process. What we have there in the reality? Diffusion layer is here. Here is the poly and gate oxide. You can compare the two things. Here we are reaching up to metal 1. Then here, the plasma-induced charge accumulation happens on metal 1, which may cause the breakdown of the gate oxide. Here is the plasma environment and here goes the breakdown once all charges which have accumulated exceeds a certain limit. So this is the relay. So this way you can understand various different connection inside the fabrication process go through. So even before reaching the realistic process step, where in the above picture you can see the M2 is connecting. In the M1 etching step, the plasma induced charge, also known as the antenna phenomenon, happens and it damages the gate oxide from the right hand side. This is a realistic action replay, means whatever we expect ideally and what happens in actual world. We are done with this infographics. Let's move on to the physics happening behind. Non-uniform density of plasma across the wafer plays an important role in antenna-related damage. Remember, here we'll go deep into the physics happening in the antenna phenomenon. Such non-uniformity can come from non-uniformity in radio frequency, RF current flow, electron current flow, ion current flow. All these are related when a semiconductor process is going. In addition to this, the electron shedding effect can contribute plasma charge. What is the electron shedding? The plasma charging, that is metal, and discharging through oxide can severely degrade or destroy devices, especially metal oxide semiconductor, that is MOS gate diode. This particular problem is becoming more prominent in lower technology node with the thinner gate oxide. The gate oxide degradation occurs by the physics, that is the Fowler-Norden FN tunneling phenomena between the gate oxide and the silicon substrate. Means gate oxide, which is residing between the gate and the silicon substrate, goes through Fowler-Norden tunneling phenomena, and that starts the charge passing, creation of the percussion path, and finally when there is huge amount of charge flux is going through the oxide. In the continuous plasma exposure environment, the gate potential builds up, adjusts itself by the FN tunneling current. The flow of the tunneling current generates trap and interfaces in the gate oxide, gradually degrading the oxide quality and integrity. At very high level of stress or prolonged exposure also ultimately lead to the breakdown of the oxide. In high aspect ratio spaces, isotropic electrons are hindered from reaching out the bottom of the space, whereas anisotropic and positively charged ions are not. This phenomenon is called the electron shading that I have just mentioned in the previous slide, which happens in the uniform plasma when topography exists on the wafer during the plasma exposure. Insulators such as photoresist or oxides are commonly used as masks when etching conductive films. The underlying conductor can acquire a positive charge by the electron shading mechanism. This way, I have pointed out all the physics that is happening behind the scene of the antenna breakdown in two consecutive slides. We are done here. Let's move on to the next. Antenna ratio. So this antenna ratio is a very important point, and you may get this ratio from your design rule manual, and it is very important for your antenna analysis. The magnitude of the accumulated charge depends on the ratio of the floating conducting region area to the gate area. This is called the antenna ratio and quoted in design rule manual. So the antenna ratio is equal to the total exposed antenna area divided by total gate oxide area. It can be equated with the current densities JFN function of Vg and Jp, that is function of Vg. And what are these? Vg is the gate voltage on all the gate oxides connected to the particular wire segment, which is under the antenna effect consideration. The charging current density Jp is a function of the antenna voltage and the tunneling current density. JFN is a function of the gate voltage when the technology parameters are kept constant. The above equation shows the relationship between the antenna ratio and the current density. A higher antenna ratio means a larger Vg, thus a larger JFN and more damage. This ratio very important with respect to the physics happening behind the antenna breakdown. So we're done with this particular slide. Let's move on to the next slide. Antenna issue mitigation. There are few ways to eliminate the antenna effect. Jumper insertion. This is creating a metal bridge, also known as jumper, near the gate of the MOS device, so that this is creating a metal bridge, also known as jumper, near the gate of a MOS device while fabrication. This jumper would take gate connections directly up to the top level metal to stack gears. Here we are talking about the jumper creation in the DOL section. DOL section you can remember from the first slide. Consequently, the gate will not see any antenna due to the breakup of a long metal piece into stacked metal or wear layers. The drawback of the use of stacked vias can lead to routing congestion and hence also the increase in die area. Stacked metal or vias may or may not lead to EM or IR reliability issues. Antenna issue mitigation. We continue here with few more points or few more ways of mitigating the antenna phenomenon. Gate protection diode. Here we connect each gate to reverse bias PN diodes. Using diode provides a discharge path directly to the substrate by contact to a diffusion area. If possible, these diodes are connected to gate with metal 1 so that prevention starts right with metal 1 fabrication. During normal operation, this reverse bias diode will not affect the functionality. However, the plasma-induced charge is discharged through the diodes, leaving the gate unaffected. Drawback is the usage of antenna diodes may increase the die area by 4 to 6%. So we are done with this slide. Let's move on to the next slide. Here we will be showing the antenna mitigation infographics to understand the mitigation process in a more visual manner. Here we will demonstrate the jumper creation. Here is our diffusion. Here is our poly and gate oxide combination of a MOS, and here we are reaching to M1. And then here we are breaking down the long M1 on the right hand side. This we have already shown in few slides back, to recall, and connect the M2 here while we connect the jumper here. So you can see the right hand side long metal piece of M1 is broken and taken through a jumper. Now this jumper connection is a simple connection shown. However, in reality this may spread very high in the BOL stack. Next, here we have the diffusion, and we are showing here a diode method, and here is our poly and gate oxide combination, MOS, that is MOS structure. Here we can think there is a MOSFET. And here we are reaching up to M1. Here we are using the M2, and you can see we are dropping the diode here. So this is the diode method. Antenna issue mitigation. Here we will proceed with two more mitigation techniques. Embedded protection diode. Add protection diodes on every input port of every standard cell. Here we are using a precautionary diode. These diodes are embedded and fixed, hence these consume unnecessary area. Diode insertion after PNR. Fixing only the wire with antenna violation, which will not waste routing resources. During wafer manufacturing, all the inserted diodes are floating or ground. One diode can be used to protect all input ports that are connected to the same output ports. So here we talk about the embedded protection diode method and diode insertion after PNR. We are done with this particular slide. Let's move on to the next slide. Here we will show the infographics of the discussed methods here. So here is our silicon substrate, and it is our STI, source drain, gate oxide, poly, source drain, gate oxide, poly, and here we are reaching up to the metal 1, and then we are reaching up to the metal 2, and finally we are reaching up P, and the stack goes on in the POL zone, and here we are reaching up to the M4. So this is a typical connection that is shown to you, and the right hand side MOS and the left hand side MOS belongs to two different standard cells. Now here what we do, as we have just discussed in the last slide, we keep embedded diodes per cell. That means for left hand cell there will be one diode, and the right hand side there will be one diode. So here goes our diode. Here goes our diode. This diode and this diode are the pre-existing diodes that will take care of the antenna issues, and these are included in the right hand side standard cell as well as in the left hand side standard cell. So this way pre-existing diodes, that means the diodes which take care of the antenna issue, are included during the standard cell. So here we are done with this particular infographics. Let's move on to the next slide. Here we'll go through another infographics. Here is our routing obstacles, and you can see that diode insertion prohibited area. So here we cannot do the insertion of the diode. And here we have routing obstacle. So you can see the layout here, and here also we have the routing obstacle. Now in this scenario, we have to include some antenna diode. What we will do? We'll proceed like this. Here you can see some changes if you compare the left hand side picture with the right hand side picture. And here are the diodes which are inserted PNR level. These are antenna diodes inserted during the PNR or after the PNR level, and this way we cover the two infographics of the discussed antenna mitigation method. So you are done with the particular slide. Let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we'll talk about what is ESD. We will go in detail with two slides. We have much more detail on ESD. Next, we'll talk about the ESD damage and protection, the general topic, and also we will cover various types of damages that can happen to your chip. Next, we will talk about the qualities of a good ESD protector. Whatever ESD protection we are using, what should be the good criterions for that. Next, we will talk about the ESD protection, whatever done in the VLSI design. That means the VLSI design stage where we incorporate the ESD protection. Next, we'll talk about the various ESD protection methodology as per the circuit theory, diodes, stack diodes, etc. Next, we will go in detail for the ESD protection scheme of snapback devices. One of the most popular snapback devices which is used is SCR. Next, we will talk about another snapback device, that is GG-NMOS, that is gate grounded NMOS. finally we'll cover the various ESD protection scheme, that is a type of different clamps that are used for the ESD protection. In today's episode, first we will talk about the ESD damages and qualities of the good ESD protection, and in the next section we will talk about what we do in the VLSI design, and we will go up to the cell level where we use the different devices to protect the ESD, and we will talk about various schemes that are used to protect the ESD. So here we are done with the menu. Let's move forward to the next slide. What is ESD? The most famous type of ESD, that is the large scale lightning, which volts up to 10 to the power 7 volt and currents up to 30 kiloampere. So this phenomena happens in front of your eyes in the rainy season when the lightning strikes. So that is the good example of visible ESD. However, when we are talking about ESD in IC, that is the VLSI, we are talking about the ESD that you cannot visualize, that happens only inside the circuit and at the very miniature level. However, in your day-to-day life, the largest and the biggest ESD, that is the electrostatic discharge, that you can see is the lightning, which has a voltage in order of 10 to the power 7 volt and ampere in order of 30 kiloampere. Now, electrostatic charging of two objects result from electron transfer during the friction. So this is the basic physics that happens for a electrostatic charging phenomena, and once any two objects are under the friction, they are oppositely charged, and that charge could get discharged through the electrostatic discharge process. Here is our circuit, and you can see here we have various components like we have transistor, IC, etc. And whenever your body is charged and you touch the device, suddenly that electrostatic zap, that is the discharge, will enter into the entire circuit board, and it may damage your transistor, it may damage the IC or any other component which is susceptible to the electrostatic discharge. ESD is an electrostatic event which balances the charge potential difference between the two charged objects of opposite polarity, leads to high current in a very short time. This high current in a very short time we will talk about in next couple of slides, where we will show you the graph. In this slide we saw the phenomena that actually physically that is occurring here when you are touching any circuit with your bare hand, and that actually does the ESD. So those electronic engineers who actually do this kind of assembling and handling these circuits, they use a electrostatic strap that they tie to their hand and which is connected to the ground, and with maybe in both hands they have two different ESD straps, so that the human body is electrostatically protected, so that your touching any device will not damage. So such kind of electrostatic straps are used in the electronic industry where electronic circuits are packaged and assembled. This is just for your knowledge. On an average, ESD destroys about 20% of electronic components before they are installed into a system. So this is what I was talking about, that wearing an electrostatic trap in the electronic industry helps the circuit to get prevented from the damage. After assembly, anywhere from 33 to 70% digital devices fail soon after consumer purchase, because ESD may only damage a component, but it opens the door for the further subsequent damages within brief time during the circuit operation. So ESD has two levels of damages. First thing, it damages the circuit. Whenever you are touching this circuit, it may damage this transistor, and it may partially damage this IC, maybe this pin or the circuitry which is tied to this pin. As soon as we connect the power to this board and entire circuit is in operation, this IC will fail within maybe few seconds of operation. That means this one get fully damaged due to the ESD, and this get partially, and whichever component is partially damaged can become fully damaged during the circuit operation. So this is the risk of the ESD, and hence in electronic industry people wear electrostatic straps onto their hands so that the circuit which is getting assembled should not catch any ESD damage. We are done with this particular slide. Let's move on to the next slide. Here we are still continuing on the topic what is ESD, and let us go to the next point. A person can acquire charge by simply walking inside a room. Now this is very, very dangerous. Even you are walking inside a room with the objects that around you, you can get charged electrostatically. When such charged person or object approaches a grounded conductor, for example a pin of a packaged integrated circuit, that is IC, an electrostatic discharge event can occur. This is characterized by high current in order of ampere within few nanoseconds. And here is the graph that I just spoke in last slide. So here, this is the transient response of the ESD, because here in this x-axis we have time and in y-axis we have current. Although absolute values I have not marked here, just for your understanding, you can see initially there will be a first peak where the entire set of charge getting discharged, and there can be a secondary peak. The secondary peak can also be there. So the circuit may first get a high peak, a sharp peak that injects the charges into the circuit, which can damage multiple objects. And there is a secondary peak again, which can damage a secondary level damage to maybe the same component or maybe some other component. So this is the typical transient characteristics of the ESD current. A high current density and or electric field, so sorry, here there is a spelling mistake, can damage the conductor, semiconductor and insulator of an IC. So whatever components are there, anything, whether it is a conductor, semiconductor, insulator, they can get damaged to the ESD event that happens within a fraction of a second. A human sensory perception cannot recognize the several thousand volt that is getting discharged through the ESD. So we are not capable of sensing the ESD. That is our incapability. And that's why if you are working in an electronic assembling industry where you are assembling different circuit boards or soldering different circuit boards or any kind of activities that is related to onto the PCB or actual packaging of the circuit, that time you are advisable to wear an electrostatic strap onto your two hands separately, so that any of your hand is not electrostatically charged and the circuit on which you are working that should not get damaged. The circuit present inside the IC will tend to be partially damaged or might break down when this high voltage pulse enters. This can happen to the IC whichever we are dealing with inside, which is maybe inside in the PCB or maybe inside the phone that is you are handling. Now there is another thing that you can notice day-to-day things, that whenever you are purchasing a RAM, you are purchasing a hard disk, you get in a bag which is maybe of in a graphite color. So those bags are electrostatic bags. Means those bags are electrostatic proof bags inside which the hard disk or the RAM, all these semiconductor things or maybe the computer equipments, all they are packaged in the electrostatic safe bags. So those are also used in the industry for protection. Those are external protection. However, in today's discussion we will talk about the internal protection. That means a circuit should be internally protected from the external ESD injection. So here we are done with this particular slide. Let's move on to the next slide. ESD damage and protection. So let us talk about ESD damage and protection. ESD in an IC usually start with oxide breakdown through percussion path. So generally there is a MOS structure, right? Metal, oxide and semiconductor structure. So this oxide, right? The ESD enters, right? It will create a zigzag path inside it through which the charge will cross, and this is damaged, and the name of this path is called the percussion path. The high current density damages the semiconductor devices through thin film fusing and filamentation and junction spiking. So all these things happen when the ESD event happens in a semiconductor chip or device, whatever you call. The high electric field, on the other hand, can cause the failure through dielectric breakdown or charge injection. So dielectric means oxide here, and there could be some other dielectric which also can get damaged. Not only the MOS structure but several other oxides are there to protect the different parts of the IC. Also those can get damaged. Hence, necessary components are used to protect ESD so that the destruction of a product or a system when touched can be eliminated. That means the inside protection to a circuit is given for the ESD event. However, external protection like ESD straps or ESD protection bags that I have just talked about are provided. Internally, we also provide the mechanism to fight the ESD. Due to this factor, there is a quick packaging, handling and design requirements of suppliers by government and other companies. I have talked about again and again about the different safety measures which I have just repeated with a point here. Here you can see the typical protection method for the ESD. So here we have diodes, here we will talk about later, and you can see there is a clamp, and here is our core of the circuit. Here is our IO pad, VDD pad, and this is our VSS pad, and these are the power rails. These two are power rails. So this way we provide the different mechanism we will explain in later slides. This image is just for your reference, and let's move on to the next point. The right hand side picture shows the typical I/O schematics protected by the ESD cells. These are the pads which are actually connected in the IC periphery. And here is our core of the circuit and clamp. So this is kind of typical arrangement that we have in our ESD protection schemes. We are done here. Let's move on to the next slide. Various ESD damages. Junction burnout is caused by the injection of the ESD transient of sufficient energy and duration to force the junction into secondary breakdown. So junction means it could be a PN junction or some other type of junction which can get burned out. Junction burnout is often characterized by high reverse bias leakage current or a total short. It can be characterized by a reverse bias operation of a junction, or it could be simply become a short. Oxide punch through is the major category of the ESD damage. Now, when you are testing any PN diode with a multimeter, if both sides giving the continuity beep, that means that PN junction diode, the junction that means the P and N junction is short there. Whether it is damaged by ESD or something like that, this is a physical phenomena you can check with your multimeter. Because typically the PN junction should not give a continuity beep in your multimeter. It should give only some value. If it is giving the beep, that means it is short. That means the junction is damaged. So we are talking about such kind of damage here, the junction burnout. Now next point is the oxide punch through is the other major category of the ESD damage. Oxide punch through occurs when an oxide is subjected to ESD pulse of high enough magnitude that can cause the oxide to break down. That means we talked about the percussion path through the oxide. That event will happen and damage the oxide, whether it is the gate oxide or some other oxide. Transient domain of an ESD event, the voltage applied the gate oxide must be very large to initiate oxide breakdown. So here we talk that the gate oxide must be very large to initiate the oxide breakdown. The voltage should be high. So in ESD, that is the voltage is very high and that breaks down the oxide. Metallization burnout is often a secondary effect occurring after the initial junction or the oxide failure take place. So metallization burnout means for the different contacts inside the IC, we have metallization there, metallization contact there. That can even get metal contact can get burnout. So the metallization burnout occurs if the current flowing through the metal forces temperature to rise due to the I²R calculation high enough to reach the melting point of the metal. Three types of ESD damage we have talked about that can happen inside the chip, that is a junction burnout. The next one is the oxide punch through, and next one is the metallization burnout. So these are existing inside the IC, and this type of damages 1, 2 or 3 can happen due to the ESD. So here we are done talking about the various type of ESD damages that can happen inside the IC. Let's move on to the next slide. Characteristics of good ESD protector. So here in this slide we will talk about what the criterions a good ESD protector could have. That means whatever we are incorporating inside the IC, the characteristics that protection element should be here. The good ESD protection element should have the clamp ESD voltage to shunt the ESD stress count. Good ESD protection element should clamp the ESD voltage to shunt the ESD stress current. Next, it can turn on fast enough. That means there should be no delay so that it can act as a passage rather than if the ESD path keeps this particular element and goes to some other part, it can damage that other part. So this part, whatever protector we are using, that should turn on fast enough. Next, can carry large current, so it should have a high current carrying capability. Next, should have very low turn-on resistance and minimum series resistance. So the resistance overall, whether it is a turn-on resistance or the series resistance, that should be very, very low. It should occupy minimum area at the bond pad. There are pads we have talked about, right, in the IC fabrication. So it should occupy minimum area there. It should have minimum capacitance, so the capacitance should be minimum. Stand out robust against the numerous pulses. Not only one pulse, if multiple pulse of the ESD coming inside, it should be able to handle all those pulse, or rather it should able to handle the pulse train or the ESD. And finally, it should not interfere with the IC's function or the testing of the IC. That means the functional testing. This should be the typical criteria a good ESD protection element that is getting incorporated inside your chip that should have. So here we are done. Let's move on to the next slide. ESD protection in VLSI design. Here we talk about the different VLSI steps that we do. First we start here the ESD design rules. So generally we have a physical verification stage where we check the design rules. Here we incorporate the ESD design rules comes as with the ESD document. The protection design implementation becomes complicated for various I/O signal configuration. Also, placement of unrelated circuits near an I/O pad causes unexpected current paths through interaction or may render protection device ineffective. So these are checks that should be done by the designer, and the rules may have some of them incorporated. The same could occur in the internal connection between power supplies, preventing the power supply clamp from operating. All of these issues are covered in ESD design documents so that the product ESD design is addressed properly from the very beginning. All these things should be covered either manually or should be through the rules, the design rules. Whatever DRC engine that you are using, that should be able to check these things. ESD protection is done using several types of I/O cells such as digital I/O buffers, provide high drive up-level shifting output, provide down-level shifting and ESD protection for input. So digital I/O buffers are there to protect from ESD, and also we have analog I/O cells, provide ESD protected analog input out. Two different kind of circuits we generally have, digital and analog, and for both of them we have different type of ESD protection elements in VLSI. So here we are done for our basic VLSI checking step that is here in the VLSI design flow in the design rule check part, and there we check for the electrostatic discharge checking design rules. We're done here with this particular slide. Let's move on to the next slide. ESD protection methodology. The main goal of ESD protection circuits is to provide a low resistive discharge path. We have talked about in the criterion of a good ESD protector. So this we have already talked about. Now here is our typical drawing of various ESD protection unit. Here we are using the clamp. Earlier there was diode, and here is the clamp between the power rails. And this is our pad, an IO pad, VSS pad and VDD pad, and these are our power rails. Figure shows the typical chip level ESD protection scheme in which an ESD power supply clamp is connected between two power rails under the different places. So this is ESD clamp, this is ESD clamp, this is for the VSS and this is for the VDD. We have different type of clamps connected different way as well. We'll go in detail, but however this is just for your FYI purpose. The ESD clamp provides the discharge path for an ESD event that happens between two power rails. So here is a spelling mistake, it is happens, not happens. Clamps should be of category of static clamps and transient clamps. Clamps could be two kind of different type of circuit operation. One is a static, another is the transient, based on the nature of the operation. The static ESD clamps turn on once the voltage across the supply rails exceed triggering voltage and start conducting the current of an ESD event. So this is the static, and it detects the two rails and accordingly it acts. The transient ESD clamp take advantage of the rapid change in the voltage during an ESD event to trigger the clamp using a rise time detector and a delay element to keep the clamping element on during the entire ESD event which is happening. So the static clamp acts in a different way and the transient clamp acts in a different way. Transient clamps acts during a circuit operation, and the static one acts based on the power rails, the voltages in the power rails. If there is a danger level, it starts acting, and in the transient, during the transient operation, if there is a danger level, it acts at that point. Transient clamps are able to react fast. However, this circuit must be carefully designed to keep their leakage to minimum. So this is another design need, because most of the devices now handle and battery operated, so the leakage should be minimum. That is our expectation. So here we talked about the ESD protection methodology, specifically static clamps and transient clamps we have talked about here. Let's move on to the next slide. ESD protection scheme diodes. Turn-on type device, that is the Zener diode. A turn-on type device like the Zener diode turns on after reaching a particular triggering voltage. Once the device is turned on, it offers a low impedance path for the ESD current to flow. The current voltage characteristics for such a device is shown in figure. So this is your typical Zener operation forward bias. Here we are not talking about the forward bias. We are focusing on the reverse bias, and you can see if we draw a perpendicular, right here we draw a perpendicular. At this particular VZ, we generally this as Vz. At that particular Vz, that breakdown will happen, right? At this point, it will offer a path where huge amount of current can pass on. So you can see I is here, minus I is here, and this type of protection scheme can be used in a typical ESD protection layer where the level is characterized by Vz of the Zener diode. So you know, right? Even in our analog circuitry, different Zener diodes are available with different voltages. So Vz is not a fixed one or not a fixed value. It can be varying. According to circuit design, such Zener diodes could be placed and they can act as a ESD protector. So here, how we place the Zener diode? We place like the diodes are shown here in between the pads, right? The VDD pad, IO pad and the VSS pad. One is connected towards the VDD and another one is connected towards the VSS. So this way we can place them. Diodes offer a simple and effective turn-on type ESD protection. They can be used either forward biased or reverse biased configuration since diode have IV characteristics as shown in the figure. So even if we have some requirements where this forward biased voltage is needed for that triggering voltage, we can also use that. So this is we mark it VI and this is VZ. So based on the need, we can either using the forward biased VI voltage or VZ voltage depending upon whatever our circuit requirement is there. They offer a very low resistance path, you know, right? Whenever this is going high, because here the voltage remains fixed and the current goes up, and here the same thing. Here voltage remains fixed and the current goes high. Obviously in the negative I axis I'm talking about. Hence it's a very low resistive path because the R is very less because the I shoots in here because this is a semiconductor. The advantages of this method, it can be simulated using the SPICE. So you can use your SPICE simulation program to check this kind of operation. One limitation is that the fixed diode turn-on voltage which can reduce the application of the diode for this. We have a limitation that we can use fixed level of voltage. I have just talked about based on the design you have to give a fixed voltage. If you are using the forward voltage here or you are using the reverse voltage here, whatever, this is fixed. You cannot change it. It's not dynamic. It's very static. This is the limitation. Here we have talked about diodes. We are done here. Let's move on to the next slide. Stacked diodes. So here we will talk about the next level of application of the diodes. That is, figure shows the ESD protection structure consisting of stacked diodes. So here you can see instead of single diode, we can stack diodes for our better protection. So this can be used. Under normal operating condition, diodes are reverse biased and hence in the off state. During an ESD event, the diode forward bias and divert the ESD induced current away from the internal circuit. The drawbacks of such structure include the relatively large on-state resistance and added complexity in optimizing the interconnect metallization parasitic for advanced CMOS process technology. So this is the drawback here we talked about in the fourth point. However, we can use stacked diode instead of single diode. In that, what will happen? So the voltages will be getting added. So VI or VZ, whatever is there, it will get added and accordingly the voltage will change. So this is the thing that we can also use stacked diode. In some cases of the VLSI, the stacked diodes are also used. So we are done talking here. Let's move on to the next slide. ESD protection schemes, the snapback devices. Snapback type device. So the snapback type protection schemes are capable of handling very high current. So here you can see we have a SCR put here, a PNPN structure here. Rest of the circuit looks very familiar to you. Already talked about, we have two diodes here and we have a SCR here. And rest of the circuit is V8 VDD pad, IO pad, VSS pad and our power clamp. And this is the core of our circuit. Everything remains same, but here we are using a SCR here. You can see PNPN structure. Gate grounded NMOS, GGNMOS and gate coupled NMOS, GCNMOS and SCR, that is silicon control rectifier, are ESD protection devices which work based on the snapback mechanism. So in the SCR slide we show you the graph that whatever snapback means. Now let us see what type of SCRs are used here. 5 different types of SCR are used for ESD protection. Low voltage triggered SCR, that is LVT SCR. Gate coupled LVT SCR. So we have another type of LVT SCR here. Substrate triggered SCR, that is ST SCR. We have double triggered SCR, DT SCR. And we have boundary MOS triggered SCR. So all these type of SCRs can be used in your ESD protection type. So you can see the ESD protection itself is a very big science here that we apply as a technology in our VLSI technology. So here we are done with this particular slide. Let's move on to the next slide. silicon control rectifier. So let us talk about the SCR here, whatever property of SCR we are dealing with and how it is getting used as a ESD protector. SCR which provides high value of area gain factor compared to other protection structures. So here you can see the IV characteristics. Here is the voltage and here is the current, and you can see the graph goes like this, and on certain point Vs the control snaps back to this point and it goes in a very high value current. So that means the voltage actually drops and then the current goes high. So here it gives a path for the current to pass on at a lower voltage, and it's almost here we have like this, but in actual practice you can see this will be almost a line parallel to this current I axis, the current axis. Here is the kind of representation of the PNPN SCR structure, that is PNPN. We have anode and cathode and gate here, and here is the BJT equivalent of this circuit. In theory, we also deal with the BJT equivalence, and that's why I have just given this particular schematic here, although it is not very important right now for our discussion, but just for your knowledge, we have posted it here. SCR is commonly used for ESD protection in advanced process technology. However, a SCR has triggering voltage of approximately 20 volt compared to low holding voltage like 1 to 2 volt. This volt is 1 to 2 volt and this is around 20 volt. So this is triggering happens at 20 volt and it snaps back and the voltage goes back to here and it's 1 to 2 volt and high current flows. So this is the beauty of SCR. SCR is popular for its area efficiency. With the same ESD protection level, SCR occupies smallest area among 3 basic devices. The area efficiency for SCR is very good, and that is we need because in VLSI we need the power, performance and area optimization. So we have an entire episode on TPA. You can go ahead and watch that. And also we have talked detail of the SCR operation in the latch up episode. I have provided the links of these 2 videos in the description. You can go ahead and watch in case you have some interest on. The cross-schematic view and the equivalent circuit of the SCR is shown in the figure, in which the consisting PNPN structure. After trigger, the SCR will exhibit snapback IV characteristics as shown. So here we have shown after the triggering, right? Triggering happens at that point and then it snaps back and the current goes high. This you can see this happens actually during the SCR operation acting as a ESD protector. Typically, SCR has large snapback. So that is what we told, right? 20 volt is a trigger and snapback voltage is 1 to 2 volt. So there is a large snapback here. Gate grounded NMOS, GGNMOS. To solve the ESD problem, GGNMOS, that is gate grounded NMOS, is commonly used for protection device. Here is the kind of schematic that we are using. Here you can see the GGNMOS. The NMOS is here. You can see the source drain is here, and you can see we have grounded the gate here. So this structure acts as a gate grounded NMOS. Rest of the circuit you are very familiar. We have displayed it couple of times from the beginning of this particular video. GGNMOS is easy to design and it is perfectly compatible with PMOS process. However, it consumes relatively large silicon area because of the low current driving capability. So this is the comparison to the SCR, where the area is efficient. Here the area is inefficient of the GGNMOS. Although it is a snapback device, due to GGNMOS has simple structure and it is compatible with the CMOS technology, it is also a popular device for ESD protection. GGNMOS is modified form of the normal NMOS device, as we can see here from the schematic. In GGNMOS, the drain of the NMOS serves as the anode and the shorted gate source and the body contact are tied together to serve as a cathode. This is the structure you can see from the schematics and this is very simple to understand. We are done here. Let's move on to the next slide. ESD protection scheme. Now we talk about the different clamps. ESD protection circuit. There are different on-chip protection methods are used for ESD protection. The rail-based protection circuit is one of them. Rail-based means which is connected to the power rails directly. Placement of the power supply clamps determines the effectiveness of the I/O protection of the rail-based ESD protection. So clamps are generally used for clamping purpose in between the rails, at least one of the rails. Here you can see this is a schematic of a VDD clamp, and here you can see that this is a schematic of a VSS clamp. So these are the 2 different circuits. So let me pin up and let me draw a line in between. So this one is VDD clamp that you can see it's connected with the VDD and also with that ground. For the VSS clamp, if we need for the VSS only, here the clamp is and this one is missing here. These are the 2 circuits. Power clamp. Power clamps are present inside each power supply I/O. So you can see that pads are here and where the clamps are connected. Power clamps. Basically, we're talking about this, or this, not about this one. This is a power clamp. We're not talking about. They are used to shunt current to the ground from power supply lines when an ESD event occurs or any event which can potentially damage the electronic component. So we are talking about this because here, as soon as if it is reaches right, this is the core of the circuit and this is clamp is for different purpose, but this will protect your chip. Whatever things are coming from the pad, that means your human con. The RC triggered power clamp is a simple and efficient implementation of the archive of the same. We also have RC implemented power clamps also there. So these are the power clamps we have talked about. There are two type of schemes are there, VDD clamp and the VSS clamp. We have shown both schematics here. And so far we have discussed so many things on the ESD today in this episode. So we are done here with this particular slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below. And bye for today.